Okay, good morning for the first session today. Our first speaker is Manuel Dries from Bonn, who is going to talk on non-thermal dark matter production.
Thanks for the introduction, and I thank also the organizers, of course, for inviting me here. I want to talk about non-thermal production of dark matter today, specifically the production of dark matter in the decay of, out of equilibrium decay of some very heavy particles. So first give you a brief introduction why this might be interesting. Then I'll discuss the sort of simplest scenario with some approximations, and then go a bit into more detail into the thermalization of the decay products, which will turn out to be somewhat important here. And then I'll summarize. So almost everybody knows that we need dark matter to make the universe as we see it work, of course. Thermal WIMP dark matter is, in minimal cosmology, is still a very great scenario. It's predictive, quite simple, and you have very little UV sensitivity, meaning you're sensitive to the state of the universe only around the decoupling temperature, which is typically like 5% of the WIMP mass, and what happened before, you don't care. On the other hand, WIMPs also are getting squeezed, although not excluded yet, by negative results from indirect and in particular direct searches, so that have excluded a fair number of WIMP candidates, or at least pushed their parameters, squeezed the parameter space. Therefore, people have started looking for alternatives, either for the candidate particle of dark matter or for the cosmological scenario one is considering. And here, today, as I said, I will talk about the out of equilibrium decay is missing of a heavy particle, which I will generically call capital phi. So the basic mechanism is that you have this long-lived particle, and the existence of such particles is, in fact, quite generic in supergravity and superstring theories, for example. Good old Poloni fields from the early 1980s, or in string theories called moduli fields. There are, in fact, many, often too many of those. And at least if they are scalar fields, for the purpose of this talk, actually doesn't matter what the spin is. But if they are scalar fields and the mass is not too large, then they can quite easily get large values during inflation. And then the field will start to oscillate when the Hubble parameter after inflation is of the order of the mass of the field. And this coherently oscillating field behaves like an ensemble of free particles, of these phi particles, just sitting around until they eventually decay. And because the energy density of non-relativistic particles is diluted less by expansion of the universe than that of radiation, if they live long enough, they can dominate the energy density of the universe. Then eventually they do have to decay, of course, before Big Bang nucleosynthesis, because that works in a radiation-dominated universe, as we know. And the dark matter can then be produced in the decay of these phi particles. So that's the mechanism I'm assuming here. So the simple scenario is an incomplete list of earlier references here. You assume that this phi particle decays by, for example, a dimension 5 Planck suppressed operator, in which the lifetime will scale like the third power of the mass of this phi particle times some fudge factor here. And then, because of the long lifetime, it can decay, can dominate the energy density of the universe for a while until eventually they decay at a temperature, it's called the reheat temperature, reheating after this perhaps second matter-dominated epoch. And the reheat temperature is like basically the geometric mean of the decay width and the Planck mass. Also depends on the number of degrees of freedom at the hour. But that's a lesser effect. So during this early matter-dominated epoch, the temperature scales only like the scale factor to the power -3/8, whereas a normal radiation-dominated universe, it scales like 1/8, basically. So the temperature drops much more slowly as the universe expands because the decays keep feeding new energetic particles. Also, for a given temperature, the total energy density, and hence also the Hubble parameter, is much higher than in minimal cosmology, because in minimal cosmology, this would be a radiation dominated. Here you do have, of course, a radiation bath. When you talk about temperature, there must be a radiation. But on top of that, you have the phi particles, which by assumption dominate the total energy density at temperatures bigger than the reheat temperature. Also, very importantly, because these particles decay out of equilibrium, the co-moving entropy density is not, or the entropy density is not co-moving constant. You keep feeding in, producing entropy in the decay of these heavy particles. And this can last for a long time, so an approximation that was often made early on, that the number of degrees of freedom is constant during that time, relativistic degrees of freedom in the radiation bath, that this can often be a quite bad approximation. So in order to describe this sort of setup, one needs to solve a coupled set of 3 Boltzmann equations, whereas normally you just have 1 Boltzmann equation for the number density chi is here my WIMP or dark matter particle, which can, that's the term you always see, this thermal production term, and that's the production term, this is annihilation term. In addition, you have now a contribution from the decay of the phi particle into chi particles with an effective branching ratio, which is really the number of chi particles per phi decay here. And you also have to follow the evolution of the phi particles. They just sit around until the decay, so that's pretty easy and get diluted, of course. And then, yeah, this is the equation to solve for the entropy density. And yeah, we have now several more relevant parameters, the phi mass, the reheat temperature, this b chi here, and that can open up the allowed parameter space considerably. Here is an example. Here the parameters are chosen such that the reheat temperature is just below 1 GeV, so the phi mass is something like 5 times 10 to the 6 GeV. Remember, the decoupling temperature is like 5% of the mass, meaning that you have a reheat temperature somewhat below 1 GeV. For WIMPs with mass below 15 GeV or so, they would decouple after the phi-dominated region. So that is this strip here. This is just the normal thermal WIMP strip. This green means you are roughly at the right relic density. I expanded the definition of roughly right just to make the green strip better visible, basically. But then you also have a large excluded region here to the right. Oh, the branching ratio, I forgot to mention. The branching ratio for phi to chi decays is here set at 10 to minus 4. So if your chi mass is too large, then this will just be excluded from the direct phi to chi decays. And here you have several additional allowed regions down here with quite small annihilation cross-section or production cross-section of your WIMP. You can have just the inverse annihilation from the thermal bath during the meta-dominated epoch. Over here, you have an additional allowed region with very large annihilation cross-section. In this case, the phi decay and the chi annihilation are in equilibrium. And down here, the cross-section is so small, you just produce your chi's in phi decay, and you just don't do anything later on. So this latest contribution, at least here, is just from phi to chi decay. That can be understood quite easily analytically. So you want to calculate the chi mass density. You always normalize this to the entropy density. So that's just this number you want to calculate, this ratio. And the number density of chi's is equal to the number density of phi's at TR times this b chi number of chi's produced per phi decay. And n phi you write as rho phi divided by the mass of the phi. And then rho phi of TR can be translated as scales like TR to the 4th after the decay. This scales like TR to the 3rd power. Therefore, this ratio will scale like TR, and you have this 1 over m phi factor here. And of course, the branching ratio appears. And if you now make this assumption, or use the fact that TR scales like the square root of gamma phi, and use this dimension 5 decay, so that gamma phi scales like m phi cubed, then the relic density will scale like, so here like the product of the mass of the WIMP, the branching ratio, and square root of m phi. Okay, and you can apply this to supersymmetry, for example. looking for a parameter space where you get right relic density for a Beano-like dark matter. Beano is nice because it has relatively small direct detection scattering cross-section, so it passes the stringent constraints from direct detection, but it also has a small annihilation cross-section, so in standard cosmology, you will tend to have way too many of them. So with this scenario, you can hope that you get the right density. This is now for again, a phi mass of 5 times 10 to the 6 GeV. On the left-hand side, the branching ratio is 10 to minus 3. On the right-hand side is 10 to minus 5. And for 10 to minus 3, you see these red points are always Beano-like dark matter. You will have too many of them. For a branching ratio of 10 to minus 5, you can get the right relic density from this, in this case, from this inverse annihilation production. So here's some parameter space where you can get good Beano-like dark matter in this kind of scenario. However, we made some assumptions in this calculation. First assumption is that the phi decay products thermalize instantaneously, so you have only phi and you have radiation and your WIMPs, of course. And also, we allowed ourselves the freedom to vary the WIMP annihilation cross-section and the branching ratio independently. Now, from the point of view of just particle physics, when it looks like a decay of some heavy particle, you don't know what it is. You can just parameterize the branching ratio at will, you might think. However, as we'll see, if the branching ratio is much less than 1, this isn't really true anymore. And remember, we needed always branching ratios like 10 to minus 4, 10 to minus 5. Otherwise, you get too many of your WIMPs. Okay, but within this approximation, it has been shown some time ago, you just take any WIMP and you put your properly engineered phi particle and you can make this WIMP cosmologically safe. However, its assumptions are, as I will show now, not really tenable. So let's now come to the main new part of this, or newer part of this talk. This is the thermalization. So with that, I mean you start with an energetic particle, inject it into the thermal bath at an energy much bigger than the temperature of the thermal bath. And this has to turn into approximately E over T particles with energy approximately T. Of course, that's what thermalization means. So how does this work? So notice I'm assuming here that there is already a thermal background with which the energetic particles can interact. Okay, you might think naively, the leading order process, that's the one that will dominate, so does 2 into 2 scattering. S is your energetic particle, B some bath particle. Just interact via gauge boson exchange. Well, this will be, forward scattering will be even infrared divergent, but this is in the thermal background. So there will be a thermal mass of this boson of mass squared of order alpha T squared here, alpha being the coupling constant. So the total, because of that, the total cross-section actually is of linear in alpha, not quadratic, over T squared. But the typical energy loss per scattering is also only of the order of the thermal mass of the gauge boson, so root alpha times T, which means that the energy loss rate, which is this cross-section times the number density of this target particles, bath particles, times energy loss per scattering, that goes like alpha to the 3/2, this root alpha times that alpha times T cubed. You have 1 over T squared here, you get, so T squared, sorry, you have a 1 over T squared here, you have a T cube here, and this T over there altogether gives you a T cube factor, which means the thermalization time scales like m phi over T squared times 1 over alpha over 3/2. So that's quite a long time because of this m phi over T, which is a very large number by assumption. So now let's look at 2 to 3 scatterings, of course, one order higher in perturbation theory. However, if these two daughter particles, S prime and S double prime, they can have roughly the same energy, meaning the parent particle loses half of its energy in a single step without anything being far off shell, if these two are collinear. Okay, and this propagator and that propagator can have virtuality of order alpha T squared, and still you can have very large energy loss. Okay, so naive guess, if you did this sort of in vacuum, or pseudo vacuum if you wish, you would get this alpha cube over alpha T squared from the power counting here, and 1 over E of this gauge boson here, emitted gauge boson, just the typical Bremsstrahlung sort of spectrum. Okay, and from that, you can calculate the energy loss rate, which goes like the parent energy times temperature times alpha squared, which would lead to a thermalization time, which is 1 over t times only the logarithm of m phi over t, rather than m phi over t itself. And that, of course, is a much, much smaller number, and that overcompensates the extra half power of alpha here that you have in the denominator. So these 2 to 3 scatterings dominate by a large factor. This has, in fact, been shown more than 20 years ago. However, there's a complication that people have started to realize only relatively recently in this context, the so-called Lpm effect, which has, in fact, been found by Russian physicists, or at least Soviet physicists, in the 1950s already, and applied to this context first by Harigaya et al. Starting about 10 years ago. So the point here again is that this particle here is still nearly on shell if this splitting is collinear, which means that even though it's a virtual particle, it can sort of live for a long time and then undergo multiple scatters on the thermal bath. And it turns out that this leads to destructive interference. That's the essence of this Lpm effect. And that, for this kind of splitting here, we are both assuming that all particles have gauge charge that are involved here. Then you find that the rate is suppressed by the square root of the temperature divided by the smaller of these two energies of the two daughter particles. And that then leads to a thermalization time after this Lpm effect, which goes like 1 over t times square root m phi over t. Not log anymore, but it's a square root. That's a much longer time than without Lpm, but it's still lots faster than 2 to 2 scattering. So this is now, as far as we know, really the correct estimate for the thermalization time. Okay, so what does thermalization, what does that lead to? It means you have a spectrum of non-thermal particles. So during thermalization, they have energy less than the injection energy, but still a lot more than the temperature of the thermal bath. And these non-thermal particles, they can be themselves the source of non-thermal relics when they scatter, either on the thermal background, that's called hard-soft, or you can, two of these non-thermal particles can scatter or annihilate each other in hard-hard scattering. So that has been pointed out a really long time ago, that it can be a source of dark matter, for example. So in order to calculate the spectrum of these non-thermal particles, you have to again solve a Boltzmann equation, this time really one for the spectrum, not just for the number density. So this is a real spectral Boltzmann equation here with an injection term and a depletion term. The injection comes from the phi to phi decays directly into the non-thermal particles, and also the feed down from more energetic particles at momenta bigger than p can contribute to the spectrum at p. And of course, then the particles with energy p can radiate themselves and lose more energy. That's then the depletion term. Now, the thermalization time is still a lot faster than the Hubble time, and therefore we can drop this second term here, this Hubble term, and one finds that injection and depletion will very quickly reach a steady state or quasi-steady state. It's not exactly steady because it depends on the temperature, and temperature changes slowly, but that time scale for that is a Hubble parameter, Hubble time. Okay, and then you find here this is the injection. This is the primary injection from the phi decay. This is the feed down from heavier faster particles down, or more energetic particles down to p, and this is the loss term, so these have to cancel out, or have to balance out. You can switch now to dimensionless quantities, normalize this whole thing to the basic contribution from the input feeding is a number of phi particles times the decay width of the phi particles, and to normalize also to the total thermalization time, basically, of your particle. Then, for a single species, so if you look at the pure glue situation, for example, then one can actually solve this, get a sort of analytical handle on this. You get more or less a universal function after multiplying with 1 over root xm. Xm was the mass, basically the mass of the phi particle divided by temperature. You see here it's a long e to the minus 3 half tail, and here's a spike from the, at very large energies from the initial phi decays. So the Lpm suppression that has two effects. One is this suppression factor depends on the energy, so it changes the spectrum also, the form of the spectrum. More importantly, it reduces the thermalization rate, which means that particles spend more time as a non-thermal particle, so the flux, overall flux of this non-thermal particles gets increased quite a bit. That has a sizable impact on the production of relics. So here's an example with very heavy 5 particles 10 to the 13 GeV. The real temperature is just set by hand to 10 to the 5 GeV. And we're looking here at very massive relics being produced. This dash curve here is the old calculation without the Lpm effect. If you put it in, you get much higher non-thermal production from this source. Okay, so this was just for the single species cascade. Now, more recently, we have also included the full spectrum of standard model particles in the cascade, not just gluons. Then you have, of course, for each particle that you include, you need a separate Boltzmann equation. They're all coupled. It becomes a bit messy. You also did the Lpm suppression a bit more accurately still, including sort of so-called Coulomb blocks. Here we used results from heavy ion collisions where this has been used for 20 years or so already, or worked out in great detail. And the point I want to make here is that you will have this non-thermal chi production from these non-thermal particles whenever the chi interacts with the bath, no matter what it is, really. So even if you have, for example, the phi particle decaying only into gluons, and your relic only couples to SO2 singlet leptons, say the most extreme case, nevertheless, you have a splitting of gluons to quarks. Quarks can radiate a hypercharged gauge boson, and that can split into right-handed leptons. So eventually, these right-handed leptons will also appear in your cascade, and you can then be used to produce chi particles non-thermally. So here's an example of exactly that. So here we have chosen the phi mass to be 10 to the 4 times the temperature, and assumed indeed that phi only decays into 2 gluons. So then you have here the gluons, of course, they will dominate the spectrum of non-thermal particles. This is the green curve, dashed is the total spectrum. But then the gluons can split into quarks, that is then this green curves, left and right-hand quarks more or less the same. The quarks can emit the hypercharged gauge boson, this is this blue curve that's further down, which can split into the singlet leptons here. So the leptons are suppressed, but not by as much as you perhaps might naively think from just counting powers of coupling constants, because they also thermalize more slowly, precisely because they have weaker coupling. And if they thermalize more slowly, that increases the spectrum, as we saw, right? They spend more time as a non-thermal particle. So that you do really have, within the factor of, say, a couple orders of magnitude, the whole spectrum of standard model particles will be part of this non-thermal cascade, and then can contribute to your dark matter production. Which means that whenever the dark matter couples to something, effectively this counts towards the branching ratio of your phi into chi, because all this thermalization should really be included when you calculate this branching rate, effective branching ratio, which has not really been done yet, though. So my time is more or less up. Here is my summary. Period of early matter domination is not unlikely, at least in supergravity or superstring scenarios. And if it happens, it will greatly affect generically the predicted dark matter relic density, unless your phis are so heavy that the reheat temperature is above the normal freeze-out temperature. And this has been known for quite a while. More recently, then there have been refinements. You have to treat the relativistic degrees of Riemann properly, and it's an order 1 effect. It's not small. And yeah, this spectrum of non-thermal particles, you also have to calculate more accurately. One part of this is done, as I just told you. However, what you really also should include is the showering of the primary decay products. So here we assume that the gluons just stay gluons with a delta function energy. That's not true, of course. They make a jet, and it should feed this jet into your Boltzmann equation, really. But that, because the Boltzmann equation is linear, that should not be such a big deal. And also, it has been also pointed out already 20 years ago, higher order phi decays will also generally exist if the phi interacts with something in the thermal bath, and that will also contribute to the effective branching ratio. So goal finally will be to put all this together for a realistic calculation of the really smallest allowed effective branching ratio, and then see, for example, whether they can still have nice Bino-like dark matter or not. Thank you.
BBN constraints on this decay Fi are included in the...
What constraints?
BBN constraints.
Yeah. The real temperature must be bigger than a few MeV.
Okay.
Then BBN will work as usual. So what is dimension 5 decay? That means that the Phi mass should be bigger than 30 or 40 TeV or something like that.
Okay, that's included. Okay, thank you.
Thanks, that was a really nice talk. Can this mechanism be made to work in realistic or pseudo-realistic supergravity models?
I'm not sure what pseudo-realistic supergravity models are. If you give me a modulus field or some other long-lived stable, metastable particle, one has to see. But again, to check this, really one also should complete this program here to include all these effects. Because, again, for a Bino-like dark matter, for example, you really need the branching ratio to be of order 10 to minus 5 or less. And it's a small number, so many high-order effects can get you beyond that easily. So I'm not sure.
Since, as you said, all this stuff has to happen before a temperature of few MeV, the thermalization time is quite short then. So the showering of primary decay products really happens pretty fast. You don't need to worry about it.
Yeah. It will change the spectrum of the particles I feed in.
Sure.
It's not the time that changes, but
yeah.
Here we just fed in the delta function at m5/2. That's not realistic, right? You have to put 20 particles with some smeared out spectrum.
Yeah. And what do you mean by higher order decays, higher dimensional operators?
No, just more than 2 particles.
Oh, I see. Okay.
So, yeah.
That should
For example, in case of SUSY, if your primary decays into 2 gluons, one gluon can split into 2 squarks, for example, right? And then you have already, from the squark decay, you have your neutralinos eventually.
Okay. Thanks.
Sorry, so just a follow-up point to Steve's question. So I don't know, maybe more realistic or not, but I can also imagine some, in early universe, some primordial black hole dominated era, and that can mimic this kind of early matter domination.
Well, they decay very differently.
Very right. Fast, and also it goes from matter to radiation domination very fast, right? So,
no, but they will have a thermal spectrum already into everything to begin with. Mm-hmm. So the branching ratio will probably be order 1 over G star, mm-hmm. which is already too large. So that I think would not be a very, very useful scenario.
I see. Okay.
For this purpose, at least.
Thank you.
If there is no other question, let's thank the next speaker is
Good morning, and first let me thank the organizers of this nice conference for giving me the opportunity to give a talk. here. It's always a pleasure to visit Greece. It's a wonderful country, beautiful country, and I'm very happy to be here. And my talk will be on a work that was a paper that appeared that was done with Nathan Berkowitz and his 2 students, and which work is in continuation is in progress with one of his students and my student Wenqi Qi, who is somewhere here in the audience. This is the title of this work, this paper, but if the title seems a bit fancy and maybe frightening, but what I will spend most of my time is to try to give the basic story that motivates this work, and so it's very simple stuff, so everybody should be able to follow. So let me go back to 1936, so nearly 100 years ago, and with Dirac, because Dirac is Dirac and he is very influential in the field. And so in one of his papers, he wrote at that time that the elementary particles known to present-day physics, so in 1936, the electron, positron, neutron, and proton each have a spin a half, and thus the work of the present paper will have no immediate physical application. All the same, it is desirable to have an equation ready for the possible future discovery on an elementary particle with a spin greater than a half, and for approximate application to composite particles. So for that, at that time, there was no particle with spin more than a half, and for him, higher spin was any particle with spin bigger than 1/2. Excuse me? You can read, that's what he has written. So, and further, even if it is not to be applied for some particles that we know, the underlying theory is of considerable mathematical interest. Okay. Nowadays, what I mean by high spin is spin bigger than 1. So, and I will be talking about spin 3/2 and spin 2. People were discussing, the name has changed with time. People were saying massive higher spins and massless higher spins, and then people start saying just higher spins, meaning massless. But here I'm interested in massive higher spins. So when I tell you this, you say, okay, for spin 3/2, I know it's Arita-Schwinger, and for spin 2, I know is Fierce-Pauli. And in this paper, he also said he can put in an electromagnetic field with just, as you know, with a minimal coupling, we change the covariant derivative. So you all know spin 2 is Fierce-Pauli. This is something that Kostas Bachas has described for you already yesterday. And the equations of motion, so you take this symmetric tensor. It has 10 degrees of freedom a priori. And this is just a Klein-Gordon equation. And you have 2 constraints, which remove 5 degrees of freedom, and you remain with 5 degrees of freedom. So we all know this. And Fierce and Pauli wrote the Lagrangian from which you can derive this. It contains 2 parts. One is just a linear expansion of Einstein-Hilbert, which is the kinetic term with the derivatives. And then mass terms. There are 2 mass operators that you can write, and they found that if you take this combination, then you can eliminate the right number of degrees of freedom, and you get these constraints. So, however, now, if you go to the Fierce-Pauli paper, what you find is that this is not what really was the interest of Fierce and Pauli, but in the title they have that arbitrary spin in electromagnetic field. So they want to couple this massive spin 2 to electromagnetic field. For them, in the absence of external field, Lagrangian was easy to get. And so they write it was it was there found possible to set up a scheme for second quantization in the absence of external field. But the problem, and this is why I'm here to talk to you today, is that the difficulty of this problem is illustrated by the fact that most immediate method for taking into account the effect of electromagnetic field proposed by Dirac leads to inconsistent equation as soon as the spin is greater than 1. And this is what is the topic of my talk and why I'm giving this talk today. So what happens is that if you take these equations and you just put, as Dirac suggested, replace the partial derivative with a covariant derivative, then you just make this commutation of the covariant derivative with the equation of motion, and you find the new constraint, which means that the theory is pathological. The number of degrees of freedom that are propagating by this tensor is different if there is a magnetic field or if there is no magnetic field. And this is not correct. So there is a problem. In the 60s, so people, because, Fierz and Pauli tell you this is a difficult problem, Dirac says it's a difficult problem, people didn't work on this. In the 60s, some people tried to solve the problem. So, Federbush proposed to add to the Lagrangian some term, which is a coupling. This is the spin 2. At that time, people used to use this capital A. Now we use H, but this is the coupling. And he writes, however, if the field is coupled to an extramagnetic field minimally, in general, the number of propagating field becomes 12 because there are 6 complex rather than 5 complex. This is what I described to you. So he adds this term, and this, he says this solves the problem. In fact, when you can add a term of that form, so I write it here. With this is the electromagnetic charge, and this is the gyromagnetic ratio. And you massage the equation of motion, and you get this equation. And you see that if G is different than 1/2, then there is an equation of motion for the longitudinal mode that starts to propagate when the magnetic field, electromagnetic field is non-zero. So you are led to take that the gyromagnetic ratio is 1/2. And this is what Federbush did in his Lagrangian.
May I ask you something? Sorry. Why is it a problem, a priori to have a propagating degree of freedom, an extra propagating degree of freedom?
No, you just take a particle, it has a certain number of degrees of freedom that are these particles, and then you put it in the magnetic field. The magnetic field cannot create extra degrees of freedom for this. And you will see that they are pathological. These degrees of freedom, they start propagating at speed bigger than the speed of light. You get a system which is not hyperbolic. You get all kinds of pathology. And you try to solve one, and the other appear. So you cannot do that. So, but this Federbush Lagrangian has a problem. One is this, I come back to this value of the gyromagnetic ratio, and the other one is that if you compute what is the fastest speed at which the signal can propagate, you find that it is bigger than the speed of light, because even a small magnetic field makes this ratio bigger than 1, and so you have superluminal propagation. So while it solves the problem that longitudinal mode, which is a ghost, does no more propagate, it has 2 issues. Now, Dirac was saying that there are no, at that time, particles which had the spin bigger than 1 that are known. But in the 60s, we discovered this omega minus particle, for example, which has spin 3/2, so bigger than 1. And when it was discovered, it was propagating in a magnetic field in a bubble chamber. So it propagates for about 10 centimeters here. So it's quite a long path. And you should be able to describe it as a localized particle. In fact, for the history, the fact that it has spin 3/2 was only shown really experimentally only in 2006 in Babar experiment. Now, as what I was saying, and was, let me cite Stanley Deser, who worked a lot on this topic, and one of his papers in 2018, so a recent paper, and he says, whatever the formal problem these models encounter, effective higher spin theory must be constructible, since approximately localized higher spin particles exist, like this omega minus, okay? So you should be able to write a theory for these particles. So he tried with his collaborator to write this effective theory, and the conclusion, even though he really says you should find it, and he says our study of causality shows that there are no models containing the correct degrees of freedom, avoid sharing the pathology of the minimal one. So they tried to add any kind of terms, and they didn't succeed. So, and it seems it's not possible by this way of getting a Lagrangian for these things. Now, this is where string theory can help. So let's go to bosonic open strings. So open strings, let's take just the bosonic ones. So open strings oscillate, and open strings you can put charges on the boundary, on each boundary with a charge, and so the open string will describe a state which has the charge, which is the sum of the two charges. So the first massive open string, you can construct it, and it has a spin-2 state and a vector state, okay? And in 1987, these people were able to to construct this theory of open strings in the magnetic field. So there you see you have a charged spin-2 state that is described by this massive oscillator, and that you can put it in an electromagnetic background field. So Argyres and Napi in Princeton say, okay, let's see what this theory gives us for this charged massive spin-2 state. So they took this spin-2 state, which is HMN, and they are lucky that this extra field, the spin-1, is just a suitable field for HMN that you can show. And so you remain only with the spin-2 state. And they were able to write the Lagrangian using string field theory. You write the Lagrangian for this spin-2 state. And you find the generalization of this Fierce-Pauli with this big HMN is some contraction of the tensor that Fierce-Pauli had with some combination with this epsilon is, you can take it, it describes the magnetic field. And you have some, the covariant derivative is replaced by some other derivative which is constructed by contraction also with the matrix which is made by the magnetic electromagnetic field. So you have similar equations, and you have this Lagrangian. This Lagrangian is good. It solves the problems that I told you about, which is called the Velos-Wanziger issue. There is no problem with causality anymore. And also this is, they were lucky because they were able to write this Lagrangian by considering only the first massive level, and it's only in this case that the states that are in this level decouple from the other states of different levels at a two-point function. So they were lucky, and they were able to find the Lagrangian with just a spin-2, which is really has no pathologies. So it is good. Now let's expand it in powers of an electromagnetic field. This was done by Massimo Porati, his former students, and Augusto Sagnotti. Sorry. Let's see what kind of terms. You know, I showed you that when you write the first term that couples the electromagnetic field with the spin-2, then you have to have this coefficient, which is the gyromagnetic 1/2, gyromagnetic ratio. However, if you expand the RGS-Napi Lagrangian, you find that the gyromagnetic is 2, as you would request from unitarity. But then you have an issue here, and is that you knew, I showed you the equation, that no ghost implies that you should have this coefficient here. It's 1 and not 4. So what happens is that in the RGS-Napi Lagrangian, you have to continue expanding in powers of the electromagnetic field strength, and at each order, you get a problem which is eliminated by these extra terms. You need the infinite series of terms that is this function, which appears also in the covariant derivative, in order to avoid having this problem with the ghost. And this is all, so this Lagrangian works very well, and the fact that you need an infinite series of terms explains why Stanley Deser and his collaborators were not able to find it, because they were always trying to do some filtering approximation with keeping a finite number of terms. However, this Lagrangian is valid only in 26 dimensions. So we were starting with the problem of 4 dimensions. And this was done in the open string framework. So the question is, what happens in 4 dimensions and what happens in superstrings? So, and this is what we have done with, in our paper with Nathan Berkowitz, and we looked at what happens in this situation. So our strategy was take string theory in 4 dimensions that is described by hybrid formalism that was introduced by Berkowitz in 1995, which has the target space, so the space-time action manifestly supersymmetric. This allows us to get, at the same time, the Lagrangian equation of motion for spin 3/2 massive charged and spin 2 massive charged. The strategy, just what I will not describe the detail here, it's not the place, is to use string field theory. You have to build the Beres operator and compute the action. So after a few hundred pages and about 2 years of computation, you finish by getting the Lagrangian, which describes the system. The system, in contrast with the open string bosonic string that RGS and Napi did, describes more states. Not only there is a spin 2, but because of supersymmetry, you have a spin 1, spin 0, and with spin 3/2, you have also extra spin halves. So this makes super multiplets, and this makes a super multiplet. This is of spin 2, and this is of spin 1/2. Okay. So I told you after a long computation, you find this superspace Lagrangian, and you are very happy because you solved the problem. And as a side remark is, if you switch off the electromagnetic field, you find some theory which was written in 98 by Nathan Berkowitz. But the problem is, where is the spin 2 and where is the spin 3/2? And they are in all these superfields. These are combination of VM with contracted by some matrices which have the magnetic field strength. So it's an awful thing. And even in the case where the electromagnetic field is 0, no one expanded it to find the Fierce Pauli and the Rarica-Schwinger. In fact, if you put it on a computer, you get something like, Mathematica, you get something like 1,000 terms. So we have to arrange this. So this is what we have done last year with my student Wenqi. And we got rid of all the auxiliary fields, all the extra fields, and you get the Lagrangian. The Lagrangian looks a bit similar to the one of our GR-SNAPPy, but it's different. And it has this coupling with, this is effectively one scalar described by some vectors with constraints. This is the constraints, and this is the equation of motion, and the equation of motion is the same form as the one GR-SNAPPy found. So in this case of spin 3/2 equation, you get something in two components, which is quite complicated, but it's the first time anyone wrote equation of motion of massive spin 3/2 coupled to magnetic field. So this is generalization of Reiter-Schwinger. And yeah, here if you put the electromagnetic field to 0, you will see that you find the Fierce-Pauli Lagrangian that I described in the beginning and that Kostas Bachas described to you yesterday. So I don't want to say much more. I can tell you that the equation of motions, if you put the spin 1/2 to 0, you get the equations of motion that are valid for any dimensions. So, okay, in 4 dimensions they are valid, and you get so what you look for. But Lagrangian is complicated, I don't write it. Just let me conclude now. So I told you what Dirac wanted to have these equations of motion and Lagrangian for this massive spin bigger than 1 in electromagnetic field and Fierce and Pauli also, and it was a long problem. So where do we stand now after since Dirac? First, we know that higher spin, we know the composite states, many hadrons, I gave the example of omega minus, exist in nature, so we should describe them. And as physicists, we should be able to describe anything in nature, and we are not able to do it for the time being. We know that minimal coupling, which is the thing which was proposed by Dirac, doesn't work. It leads to many pathologies. String field theory helps to construct some equation of motion Lagrangian for this massive state. So string theory might be helpful to do something for phenomena, to describe something which exists in nature, and which is one of my main motivation to get into this topic. And we got some equations of motion Lagrangian for this spin coupled to lower spin ones with my collaborators. And this work is in progress. Thank you.
Thanks for the nice and interesting talk. I think in the background of an electromagnetic field, the coordinates of the open string, at least the endpoint coordinates of an open string, become non-commutative, right?
Yes.
So does this play any role here that you are dealing with the theory in a non-commutative target space?
It makes your life harder when you do the computation, but except for this, no. The computations are, you have every place, you have things which don't commute, and you have to be careful. So.
But besides that, there's no other effect, so to say.
No.
Okay.
So.
Okay, Karim. So the higher spin states in nature are composite. So,
yes.
So in principle, you want to construct an effective theory.
Yes.
Let's say below the compositeness
yes.
cutoff. So does it change anything in the general framework? The fact that you are thinking on not on a fundamental theory, but on an effective theory?
No, no. This is what was the argument on Stanley Desert, who spent, I mean, many papers, many years, and I mean, on Massimo Porati also, who spent a lot of time working on this topic, which dissected all these problems, and yeah. So you see, this was the motivation that if you go at low enough energies, you should be able to consider these composite particles like localized, and you should be able to write an effective Lagrangian. But okay, it can have a cutoff, and I'm just looking at 2-point functions. I'm not looking at interaction, and even with this, we are not able to do it. So it's a complicated problem.
Okay, thanks.
The form factor doesn't appear in this approximation, if this is the question. John is asking a question.
Sorry, sort of following a little bit on from what Mariana was asking about. So, of course, the omega minus is indeed composite.
Yes.
Okay? So I would imagine that the equations that you've written down would give a sort of characteristic prediction for the magnetic moment, the same way that Dirac had a prediction for the magnetic moment of the electron. Right?
Yes.
Now, we know that baryons, of course, have anomalous magnetic moments. Like,
yeah.
And so my question is, have you thought at all about what is the sort of the sort of elementary prediction for the magnetic moment of a spin-3 half particle? And have you thought at all about how that could be modified, for example, in the sort of composite model that actually describes the omega hyperon?
I mean, this paper discussed this in, it has, this paper discussed this, has a section on this issue. And at this really leading order, you want to have gyromagnetic ratio equal 2. For this composite states, you would prefer to have that because of unitarity and the growth of the forward cross-section. Of course, you will be happy to have corrections, maybe radiative corrections because of the form factor, but this is really, we are really at the simplest level of trying to write the simplest Lagrangian, and we have difficulties. So we are not at higher order correction. I'm not sure if I answered your question correctly. I mean,
well, I guess
they discussed that
perhaps
you
I didn't
might
formulate my remarks very clearly. I mean, there must be a prediction for what it would be if it was an elementary particle. And then there's a question of how one would treat the possibility that it's a composite particle, in which case you get deviations from that prediction.
We know there is, we know just for elementary particles that we want to have G equal 2. This was introduced by Weinberg in 1970 in a lecture, and then was shown by Sergio Ferrati-Legdi and Porati, in the 90s, I think, for elementary particles. But for this composite omega minus, no, we don't know. I mean, this paper discussed we might relax the G equal 2 to something else because you don't know, but I don't think there is an answer for a prediction for what should be the magnetic moment of omega minus. Or I don't think it's not measured for sure. I mean, we don't produce enough. I see even the spin was measured in 2006. So it's yes, but the problem is the amount of particles you produce.
Karim, thanks for the nice talk. I have one question and one comment related also to the question of Dieter. First, I mean, in supergravity, when you gauge R symmetry, you do couple the gravitino to the electromagnetic field.
Yeah, of
so
course.
So you have a coupling. So how does it compare? I mean,
Okay.
It looks much simpler than this one. So.
Yeah, okay. In fact, in the 70s, the early 70s, that's the first thing people thought about because people knew about this, and it was John Mador. Maybe you know him. He was in Orsay, who wrote a paper on, I think it's the first paper on this, and other people wrote papers on this. And he said, okay, we know supergravity has spin 3/2. You gauge R symmetry, which makes the spin 3/2 the gravitino charged. So let me take this one. And you get two problems. Either you have a cosmological constant, which is of the order of the Planck scale, to get something which is causal, and you don't want that. Or you find a way to not to get rid of this cosmological constant of the gauge. And then you find that it works only if the mass of the spin 3/2 is m Planck. Okay. Not even 0.3 m Planck.
Okay. I have another question, if I can. I mean, Dieter asked you about the non-commutativity.
Yes.
And I think, I don't know if, I mean, I asked my question, it's not just the fact that the computations are complicated, but you should be able to reformulate it in terms of Moyal products and the non-commutative field theory. Does it reflect here, or the fact? I mean, also in your Lagrangian, you have non-polynomial couplings with the magnetic field because epsilon is the arctangent of. So can you rewrite it in terms of a simpler Lagrangian, but with Moyal product?
I don't know.
No,
I didn't try.
So, Karim, yes, coming back to my comment previously.
Yes.
Actually, if a photon propagates in matter, it acquires an extra degree of freedom, right? So, what I'm saying is that this is, of course, an effective approach. We know that these degrees of freedom comes from the couplings with the rest of the matter it propagates inside. So it is not, in a sense, so surprising. I'm not saying that there is no problem, right? I'm just saying that it is not so surprising that you create, when you couple to something external, that you create further degrees of freedom. And related to that, another comment is the following. When we say we talk about a background field, this is also a view, right? There is no things in elementary physics such like background fields. There is a quantized field, and it's our view to say that under some conditions, effectively, we have a constant magnetic field.
So, let me take, so, I told you the problem of Fierce and Pauli, I told you about, and Feder-Busch wrote this paper in '60, and Velos-Wanziger wrote papers later. They were Johnson and Surdashin who wrote the paper that they have problems with quantizing the theory, and then in the '60s, people divided into, let's say, 3 parts. One is like Schwinger and Weinberg, who says that these theories don't work, we don't know how to do. And they make footnotes saying this. The other ones are people who try to find what was going wrong. And it took a lot of pages, many years, and to find that what happens is that in fact, these equations generalized. Some of this equation, the coefficient becomes 0, and that you get some modes that either too many modes or not enough modes, and that are propagating in a pathological way. And there are people who say, okay, there is no problem, and they try to do things, and it never worked. So you always got something which didn't make sense.
Okay. I want to thank the organizers to give me this opportunity to talk at this conference, and again to join a conference live with other people. The title of my talk will be concerned with the flavor sector of the standard, which contains most of the parameters as we know them. The title of my talk will be that I want to address this problem via something that's known as modular flavor symmetry, and I will do it from the string point of view, where modular flavor symmetry appears naturally. So let me see. No. Can you explain me how this works?
The middle one is the laser.
It's the laser, yes. And this is one, too. Okay.
Let me just go first. Let's go forward.
Okay, good. Thank you. Sorry about that. Okay, any case, the outline of my talk will be that I will discuss first the flavor structure of the standard model. Then I will discuss what is known, what we call traditional flavor symmetries, will lead to modular flavor symmetries, and something combined of that which we call the eclectic flavor group. On the way, we will find something which one could call local flavor unification, where flavor symmetry depends on the location of the fields in extra dimensions. And this local flavor unification will in some way be the reason why we can create hierarchies for masses and mixing angles in the quark and lepton sector. This will bring me then to a question about lessons from the top-down model building compared to what people have done in the bottom-up approach. And I will also give a local fit to the lepton masses and mixing angles, so this will be the main part of the talk later. What is important in this case is that this is a localized structure of extra dimensions, is very important for the properties of these models. So this is work done with these people over the last few years. And let's start with the bottom-up approach. There have been quite a lot of approaches with discrete symmetries from the bottom-up perspective based on various groups like S3, A4, delta 27, delta 54. And it has been shown that typically the lepton sector is easier to fit than the quark sector. So it seems that there seem to be require some different mechanism in some way for quark and lepton sector. The main reason is that we have small mixing angles in the quark sector. All mixing angles are small, whereas in the lepton sector, some of the mixing angles are large. In addition, of course, flavor symmetries have to be broken. This requires the introduction of so-called flavon fields. Their wave breaks the symmetry, and this leads to additional parameters. And all of that has been to put together to fit the data, because by now we, of course, we have essentially all parameters measured, so we do not need to predict the top quark mass. And as you remember, this had been something which was not done very successfully over the years. So, but in any case, so in this bottom approach, there are many reasonable, let's say, models which fit, and there is not a clear picture emerging. So therefore, I think we are missing still a top-down explanation of flavor. And I will now think, you see, the source of the symmetries will be in extra dimensions, and I will also use string theory in this top-down approach. So we have to talk about the geometry of the extra dimensions. So I will immediately start with the string geometry, because it's more general than what we have in quantum field theory. So what we have in quantum field theory is that we have the symmetries in the extra dimensions, which have to do with the properties of this usual symmetry. So this we would call traditional flavor symmetries. But then string theory also has duality symmetries, which connect ultraviolet stuff to low energy stuff. And that in some way, these string duality transformations will be something new, and it will lead to modular flavor symmetries in the low energy effective theory. So this is an important thing. Also, modular symmetries had been also discussed in the bottom up. It was introduced by Ferruglio in a very nice paper of 2017, where he actually, for bottom up approach, very nice paper. In the following, I will try to illustrate these symmetries in a simple example. It will be a twisted two-dimensional torus. We start with a two-dimensional torus. We have to twist it in order to get chiral fermions. But this will be relevant for many compactifications, even Calabi-Yau, so relevant for those compactifications which have elliptic vibrations, and there are many of them. So now let's get first to the traditional flavor symmetries. We first discussed the Z3 orbifold. And the Z3 orbifold, you see, has we take the plane divided by lattice vectors, E2 and E1. They have the same length, and there is an angle of 120 degrees between them to be able to make a Z3 twist. So if you look at the light shaded area here, that is the torus. Yeah, you have to identify this line with this line and that with that. And now when you do the twist, the Z3 twist, you actually get to this object here. There are 3 fixed points of the twist, which are X, Y, and Z. This point is the same as this. And the Z3 orbifold is the object where you fold this along this line, flip it over, and glue it at the edges. That's the Z3 orbifold in this case. And it will have 3 fixed points, and there be in string theory they can be fixed points. At these fixed points you can have chiral fermions, localized chiral fermions at this case. Now in this case here, this actually leads to a discrete symmetry which is known as delta 54. There is an S3 symmetry from the interchange of the 3 fixed points, and from string theory selection rules, and actually from conformal field theory selection rules at that level, we get a Z3 cross Z3 symmetry. And then these 3 groups in a multiplicative closure lead to a group which is delta 54. It's a non-abelian subgroup of SU3. So for the flavor physics, it's as good as SU3, but it has not the disadvantages that for SU3 you have a continuous group and you have to worry about some other things. So for example, this could be a flavor symmetry of 3 families of quarks. When the quarks are triplet, delta 54 has triplet representation, so if it's a triplet of delta 54. So this is what we could call a traditional flavor symmetry. Now let's come to the modular flavor symmetry, and this is based on string dualities. For example, if you consider a particle on a radius r, you have a discrete Kaluza-Kind spectrum, and the spectrum is given by m over r. Heavy modes decouple when m goes to 0, when the circle goes small. So that's what we get, typically. But now consider a string. Of course, again, you have Kaluza-Klein modes, m over r, but now strings can wind around the cycle, and these winding modes, they go like n over r, winding number times r. The bigger r is, the heavier is the winding state. But you get massless modes when r goes to 0. That's the duality that you, if you got to small r, a tower of state comes down. So this is T-duality, known as T-duality. It exchanges momentum and winding modes, and simultaneously r going to 1 over r. It maps a theory to its T-dual. And it's a symmetry at the self-dual point, r squared, which is 1 over m string squared. Now, if the string scale is large, the low energy effective theory describes the momentum states and the winding states are heavy. So you might ask the question, well, can T-duality play a relevant role for flavor symmetry? And in fact, it can do. It actually gives you some ultraviolet information on the low energy effective theory by that symmetry. So let's now go from the circle to the torus, because we wanted to look at the twisted tori, so now strings can wind wind around 2 cycles in this case, and we get to the so-called modular transformations, which are the group SL2Z. It's generated by two generators S and T, where S24 is equal to 1, and the modulus M transforms as under S as m going to minus 1 over m, and t goes to m plus 1. So you see the inversion, the T-duality, which we had before on the circle, is the role is S. It takes the modulus to its inverse. There are further symmetries here. They include m to minus m going to minus m bar, and also mirror symmetry between Kähler and complex structure modulo. I want to talk about this time, but this is the source of CP violation in the model. So given that, the modulus lives in the upper complex upper half plane, but if you divide out by the symmetry, you get the fundamental domain, which is given as the dark shaded region here. And so this, of course, extends to infinity, and it has some fixed points which you have this. So this is the modular group. The fields which we have now transform under modular group. So the modular group can be written as gamma, going in this way. This is a different representation of A, B, C, D, and integer, and there's this relation. Now the matter fields transform as representations rho of gamma of this group, but there's something more to it. There are so-called automorphic factors which come with it, which are multiplying these fields. So we have two things here. According to the normal symmetries, you have a representation. That's it. And this is rho of gamma. But here you have more, because you also have this parameter k, which is the modular weight. It's known as the modular weight. So these modular symmetries, they have some more ingredients than we will have the usual one. Now let's go to the orbifold and see what are the modular flavor symmetries of the orbifold. Again, now of course what we have done is in order to do the orbifold, we have to have E1 equal to E2, and we have the angle to be 120 degrees, and that restricts of course the moduli. So one of the moduli, the complex structure moduli of the torus, is frozen because of this, and then we will have modular transformations on the Keller modulus T, MT, and so this is now governed by a mod 3 subgroup. So you take SL2 set, but instead of set, you take 3 set, so you shift by 3 units. This is known as gamma 3. It's a mod 3 subgroup of SL2 set. And now you can take SL2 set, you mod out this subgroup, and this gives you a discrete flavor group. This is called the discrete modular flavor symmetry. It's gamma 3 in the simplest case here. And in fact, you can work it out, and gamma 3 in fact is A4. It's isomorphic to the even permutations of 4 objects. But in fact, there is more to it. In fact, it's the double cover of T prime of A4. A4 is the one which acts on the moduli, but the matter fields can have to even transform non-trivially. So there is, this is the double cover in the same way that the matter fields, they, like when you have SO3 and SU2, when you would have only bosons in SU3, you would, SO3 would work. That's just A4. And T prime is the double cover. That is where the matter fields transforms non-trivially. So this is then the group T prime. So this A4 has 12 elements. This has 24 elements. And this CP transformation completes the picture. It leads to the modular group GL2, 3. And that's a 48-element group. So this is the flavor symmetry which we have here. So now we have a traditional flavor group, which is universal in moduli space. It's delta 54 here. And we have a modular flavor group that transforms non-trivially in moduli space, here T prime. Now the eclectic flavor group is defined as the multiplicative closure of these groups. So for the example which I showed you, we actually get the group omega 1, which is a group of 648 elements. It's from delta 54 and T prime. If you include CP, you get a group with 1296 elements. Now this eclectic group is the largest possible flavor group for the given system, but of course it's not completely linearly realized, because it's, you see, the T duality is a map. It's not a symmetry, it's a symmetry at some points, and this we will discuss now as next. When you look at this moduli space of gamma 3, this is now the light shaded area included the dark shaded area, so this is bigger, it's a subgroup. And in fact, you will see that there are fixed lines and fixed points according to this transformation. So we have here S going to -1, T is the shift symmetry, and U is this inversion M going to -M bar. So when you go, for example, on this line, it's a fixed line under TU. TTU. If you go to this point, it's fixed under S. This circle is fixed under S times U. So if you have and if you have three lines miss here, this is a fixed point which is given by ST. So you have there fixed lines, fixed circles, fixed points, and these are the places where the flavor symmetry is enhanced. The traditional flavor symmetry is enhanced. So the picture is the following: in this flavor space, in this space, a moduli space, delta 54 is universal. So everywhere you have delta 54, but at certain points and lines you have an enhancement of the group because of the modular symmetry, which is linearly realized on this line. So here you get groups of 108 elements if on lines or circles. When you have when a circle and a line meets, you have a 260 element group, and if three lines meet, you have actually a group 324 with 324 elements, which contains delta 54 as a subgroup. So the point now is that you see when you move in moduli space, you break this group, for example, with 108 elements to delta 54. And if you are close to the line, then this is weakly broken, and this can then create, in a certain way, small numbers in the flavor sector. So just to summarize at this point, we have the traditional flavor symmetries, we have which are universal, we have the modular flavor symmetries which are non-universal, and this non-universality in moduli space it leads to something which you call local flavor unification. At certain points in moduli space, you have enhanced flavor groups, so they govern, they play the role of the flavor groups for quarks and leptons. You get hierarchical masses and mixing angles if you are close to these fixed points in some way. And of course, you get also potentially different pictures for quarks and leptons. So where are we at the moment? So we are, so far I've discussed a simple example where we had just one modulus in the set 3 orbifold. This has been generalized to more moduli in the set 2 case. We start typically with two moduli, the complex structure moduli U, T. U is frozen in the set 3 case, but in the set 2 case, this is not the case. T and U are unconstrained, and in fact, if you include Wilson lines, you also get symplectic groups like the Siegel modular group SP2ZOZ. So this has been worked out. I will not discuss that. I will not discuss that here in detail. I want just to go and give you. We now tried to get an explicit model to see whether in the top-down approach we can actually get something which works. And how restricted, because the top-down approach is much more restrictive than the bottom-up, where you have a lot of choice of parameters. When you see whether it works, whether this gives us some guideline. So what I'm doing is I'm working on a real constructed string model, which is based on the set 3 times set 3 orbifold. That was done some time ago by these people from Mexico. And they actually give you examples, several examples, not only the delta 54, but T prime, but also for other groups. So what we have now, you have T prime. T prime is broken by the modulus. We need flavon fields, and it's the interplay of the breakdown of these flavon fields of delta 54 and T prime that can create hierarchies. And actually what we see from the beginning in this model, that the large angles in the lepton sector are possible, and the seesaw mechanism is in a somewhat inherited, as I will explain in a moment. In fact, we also find out that it's similar, it's easier to construct the lepton sector than the quark sector. Any case, so now out of this class of models which they have, we selected the simplest one which we could have. This has, let's say, representations which are 3, 2 of delta 54. So delta 54 has 3 different three-dimensional representation. It's a 1 plus 2 prime of t prime, and it has k equal to minus 2 over 3. This is this parameter k, which is important. In bottom-up model building, k is used for various fields. So, and also many of the approaches use triplet representations of t prime. So in some way, in this model which we have here, in these models which we have here, we actually cannot reproduce one of the models which has been discussed in the bottom-up approach. So it predicts a seesaw mechanism in the lepton sector. It comes from the fact that the dimension 5 Weinberg operator is the lowest dimensional operator in this case. The Yukawa couplings later come from this higher sector. So what it predicts, also a normal hierarchy. This will be the outcome, as I'll explain. It predicts a normal hierarchy for the neutrino masses. It gives severe restrictions on super and Kähler potential. And in fact, we will show that the Kähler potential is typically controlled by the traditional flavor symmetry. But when you break it, you also get non-trivial structure in the Kähler sector, and that, in fact, will be used in order to fit the quarks. So we made a fit based on this model, just wanted to fit the data, and then we saw that in some way we find that moduli are close to the fixed point, because we have to explain why the muon is 200 times heavier than the electron, so we need small numbers. And in fact, in this fit, this is found in this fact that we find this actually 2 solutions which are of similar quality, and they have the properties that they are close to 0, the real part, and they are at imaginary part equal to 3, which is essentially infinity, because this comes in the exponential. So if you have 3, this is also, it's not far from infinity. So it's not far from that fixed point which you have at imaginary part equal to infinity. So these are the solutions. It gives the normal hierarchy for the neutrino masses, so it actually predicts the electron neutrino mass will be something like 4 times 10 to the minus 3 electron volts. The muon will be a factor 2, and this one will be a factor of 10. So these are closer together, and the third neutrino is heavy. So this is known as the normal hierarchy. It fits the mixing angle, so this is our fit, according to the chi-squared, which we'll get. And this is actually, the other lines are experimental data from the fit of the experimental data. So we actually can reproduce that very well, but we did a fit. One non-trivial statement now of things which have not been measured, that it lies in this. So this is the Majorana mass, effective Majorana mass, and this is M1. M1 we have seen is somewhere here at milli-electron volt, 4 milli-electron volt. So it is here, and it actually is, so this is the region which in some way is allowed theoretically. These are the experimental data, and so we are actually close here to the upper limit of, so it gives you rather sizable Majorana masses for the neutrinos. So there is some hope that in future experiments you will be able to come down to this region, and that might be tested. So it's a high value of the effective Majorana mass. So this brings me to the end. So I discussed the top-down approach. Now we had the simplest models, and in this simple model we even succeeded. We succeeded with the leptons, with the quarks. I have not shown the picture because of lack of time. We actually had to work harder, and in fact we needed non-trivial structure in the Kähler potential. So these non-trivial terms in the Kähler potential which come when you break the flavor symmetry are important to fit the quark masses. So this might be one message here. In the bottom-up models, people usually do not consider, they consider a canonical Kähler potential, canonical kinetic terms, and they assume that all the non-canonical terms are absent. Here, they are forbidden if the traditional flavor symmetry is exact, but once you break it, they come back. And it seems that for the quark sector, they can give you a fit. Now, on the other hand, I had hoped that in this simple model would not work, so that string theory might lead us to some cases. It works. So in that sense, of course, we still have to wait to identify maybe a general picture of what the top-down approach can give you as a view how to understand the flavor symmetry of the standard model. So I think I stop here. Thank you.
Yeah, thanks very, very much for the nice talk. In a given top-down explicit string construction, you typically have, besides the three massless quark and leptons, also other massless fields like exotic fields, color exotics, or whatever comes there. So these are typically around. Do the additional massless fields somehow change or affect the modular flavor symmetries, or do they then lead to even bigger representations, or what is the role of the other massless fields which are typically there?
I think they are typically in these models which we have here, the massless field they typically come in three classes. Triplet 1, I can only talk about this model with delta 54.
Okay.
Yeah? There are triplets, 1 and 2, both of them. There's a non-trivial singlet. There are singlets under flavor group, but there are no doublets. Now, delta 54 has the triplets, 2 anti-triplets, 4 doublets, a singlet and a non-trivial singlet. The doublet states do not appear at low energies. They are actually winding states. So, of course, if you could make them massless, but then, of course, you would get additional U1 symmetries, which, of course, we do not consider. So, in fact, for the massless state which we have, all of the hundreds of states which we have, the vector-like exotics and all that, they all come in these classes. They are not, they come in these 4 classes of representation. Other questions?
Are there examples in which you can also take into account moduli? Do you hear me?
Well, we hear you, but don't understand you.
Now, yeah. So, are there studies in which you study explicitly moduli stabilization and the cancellation of cosmological constant, just putting everything together?
Well, we at the level were just happy to have that. Of course, people have discussed already in the 90s question where modular symmetries are broken, and it seems that there are many cases where modular stabilization actually likes to drive, you see, fields to these fixed points of the modular group. So in fact, that we get solutions which are close to this fixed point would not be a surprise. But I think in these models here, you see, we have not discussed that yet. There have been some more general discussion what can happen with such a potential, but given this one, it's too complicated. It's hundreds of fields which we have at low energy.
So regarding, can you hear me? Yeah. Regarding experimental test of this framework, you mentioned this neutrino-less double beta decay that is close to maximal. You mentioned neutrino-less double beta decay that is close to maximal, because you want to test eventually this experimentally, right?
Yeah.
Because if not, imagine that they don't see neutrino-less double beta decay. What happened? Is this framework
well,
out?
I guess, you see, we took out, even out of this class of the Z3 orbifold, there are 5 classes, and we took the simplest ones. And the simplest ones only has doublets and has this k equal to -2/3. So then we fit the data, and that's the fit. Now, if If they don't measure this one, then the fit is irrelevant. We have to look for a different model. So we are at the moment, you see, as I told you, I would have preferred not to be able to fit, because then I would have hoped. So taking the simplest model, even possible to get a fit in a certain way is nice, but on the other hand, you might have preferred the other way around.
The real problem with all the framework is that it's very difficult to decide experimentally if you are fulfilling the framework or not, right? Because eventually you have very loose predictions.
Well, as I told you, we have weighed one fit. Now, this is the first top-down fit. There have been many bottom-up fits, but this is the first one, and we get a result. So at least I can only talk about this one.
Also thinking in possible test of this framework, is there any preferred solution to the SUSY flavor problem, like alignment, universality?
Supersymmetric flavor problem. You mean the soft terms? No. You see, yeah. No, this doesn't address the problem. So in a certain way, we assume that the flavor which we discuss here is given by the Yukawa couplings. Yeah. So you could. It's even not so much a supersymmetric theory, because you know the superpotential. You see, for the quark, for the flavor sector, it gives you the Yukawa couplings. Yeah, and of course the SUSY flavor problem has to do with soft supersymmetry breaking terms, and there we assume that they are irrelevant here. They might give corrections to it, but we are in a certain way here concentrating on this question of the Yukawa couplings.
At some point during the coffee time, we will have the conference photo. So please wear your masks and then just take them off only for the case of... Thank you.
Αυτό το χτυπάς εδώ. Ναι, το κάνω για να πηγαίνω να κοινωνήσω. Όχι, έτσι. Να το κάνω ένα παράδειγμα.
Howard Haber, who's talking about the anapole moment of a charged electron.
Can you tell me how this works?
This one will change.
Oh, the arrow.
Okay. I'd like to thank the organizers for this invitation and their encouragement for me to break my sort of over 2 years of isolation in Santa Cruz. It's great to be in an actual live conference again rather than sitting in front of a screen. So let me just try to motivate this talk. So the first thing you could say is, well, there's been quite a lot of discussion about the magnetic, anomalous magnetic moment of the muon and the electron for that matter, which perhaps suggests the presence of new BSM physics, and also the electric dipole moment of the electron is measured. No evidence for its existence has been seen yet, but the experimental limits are pretty good. Well, that leaves one moment that I cannot find in the particle data group's book of particle physics. So one might ask, what about the anapole moment? And why give this talk at a supersymmetry meeting? And well, the following paper I noticed appeared in 2019 that purported to compute the anapole moment of leptons in the MSSM. You'll see the reason why I ended up coming across this paper as we go through this talk. And I became convinced after a while that there's something not quite right in this paper. It hasn't been published, and perhaps this is part of the reason. So I'll make some comments associated with some subtleties when you include the full electric sector at the end of the talk. But there were certain parts of this calculation where there seemed to be just bits absent. I'm not sure how they got a finite result, in fact. Meanwhile, Herbie Joyner, Steve Martin, and I, back in 2001, contracted to write a book called, well, now titled From Spinors to Supersymmetry, to be published by Cambridge University Press. We, I believe, set the record for the most deadlines missed of any book published by the physics division. But in fact, we finally delivered our manuscript last month, although it's going to take a while before we actually have a book in hand. They tell us spring of 2023. The book contains a lot of discussion of the two-component spinor technology, which is what you want to use if you're doing a lot of supersymmetry, but can also be used for standard model processes and BSM processes. I mean, any system of particles that involves chiral fermions, we argue that the two-component methods are as easy as the traditional four-component methods that one learns as a student. And so one of the many things we do in this book, this is a pedagogical book for a course in BSM physics, for instance. So lots of examples, lots of explicit calculations. And in fact, we do the one-loop computation of the muon anomalous magnetic moment, and softly broken SUSY-QED is one of the examples in the book. And when we wrote that section, it occurred to me, gee, we have all the stuff we need. Why don't I go ahead and work out the anapole moment? And so just for fun, what I wanted to do in this talk is walk you through that calculation. Except I'm not going to use two-component fermions. So you'll have to buy the book to see how to do it. I'm going to just, well, mainly because most people know the four-component methods much better. And so I decided to redo it for myself and to present here. The outline of this talk is I'll review the structure of the electromagnetic vertex, show you how one interprets the form factors. The computation, the way we did it was called the projection operator technique. I'll show you how that worked, and then I'll just go through very quickly how one gets at the anapole moment. And I'll end with just 2 slides about challenges of a more complete calculation. In other words, not just SUSY QED, say the full MSSM if you want. And I'll ask and not answer the question of whether the anapole moment of the electron will ever be measured and some value or some bounds appear in the PDG book. Okay, so let's get started. There's the electromagnetic vertex, and at the bottom you see the expansion of this thing in terms of the 4 form factors, and this F4 is the quantity of interest for us. That's the anapole moment. There, just to summarize some of the properties of the various 4 form factors. These are its transformation properties under PC and T. 2 of them are chirally flipped, 2 of them are not. And the way I'm going to calculate this is I'm going to take a static electric or magnetic field, and I'll just pass my charged particle in that field and measure the scattering. In the limit, in the non-relativistic limit, as the momentum transfer squared goes to 0. And that will isolate the static moment that I'm interested in. I'm going to put a little tilde on the Fourier transforms, and for a static electromagnetic field, A mu doesn't depend on time, so I get to integrate over T trivially. That pops out an energy conserving delta function, and then there's my definition of the Fourier transform. So how do we interpret the form factors? Well, we're doing a non-relativistic scattering. So you can open up your quantum mechanics textbook and find this formal formula, which is exact, where this P plus obeys the Lippmann-Schwinger equation. But in fact, we're going to just work out to leading order in the potential. So when you stuff this back in here, you can actually throw this away because that's higher order in V. And so then we can identify the matrix elements of the potential as this object here, where there's your Fourier transform here. And as I said, the energy conserving delta function imposes the fact that energy is conserved. So I'll quickly go through the 2 possible cases. You either have a static electric field or a static magnetic field. If you have a static electric field, all we're going to do is we're going to do the non-relativistic reduction of this guy here. All the formulae are conveniently located in an appendix in our book, so it makes it easy to do. This is what you get. We're using covariant. The only difference between this and what you'll find in your standard non-relativistic quantum mechanics textbook is we're using covariantly normalized states. So we have factors of like that in front of our plane waves, et cetera. So in any case, you get this result here. And you get the sigma dot E because there was an integration by parts, and you've related phi to E by the standard formula here. And so now you compare both sides of this equation, and this is the non-relativistic potential that comes out of that, and you recognize the first term is just the interaction of a charge with a potential, and the second term is the electric dipole moment. And so comparing this with this, you see that the charge of the muon is minus E times F1 of 0, which means F1 of 0 is 1, and the electric dipole moment is proportional to F3 of 0 by standard formulas, S being the non-relativistic spin operator. So for the case of the antipole and what's coming up, we're more interested in a static magnetic field, so that's what I'll do next. And you do it's basically the same sort of calculation. You'll end up involving the Fourier transform of the magnetic field, which is related in this simple way, Q times the gauge field A vector, its Fourier transform. And you just go through the same argument of the non-relativistic reduction, and out comes this formula. And I was amused when I derived this. I derived this because I was trying to be maximally pedagogic in the textbook. And I've never seen anyone write out this first term, but of course it has to be there because that's the standard term you get in your quantum mechanics book for the potential of a charged particle in an electromagnetic field. But in addition, you get that, and of course, recognizing this as the interaction of a magnetic dipole moment, you get the famous result that F2 of 0 is equal to the anomalous magnetic moment. But then you get this extra term here, and I think on the next slide I actually wrote out the steps. I won't dwell on this, but just to show you how that potential is derived, it just takes a couple of lines in doing the non-relativistic reduction. And so in analogy with the magnetic and electric dipole vectors, I'll define an antipole vector by this formula here. And when you do that, well, the potential due to an antipole moment moving in a static magnetic field is just given by minus A vector dot J vector. So because J is the source of the magnetic field, remember this is a static field, this is just Maxwell's equation. And so to summarize, what I've shown you is that we get a potential magnetic moment, magnetic dipole moment, electric dipole moment, and then this funny antipole moment, and it's dotted into J. This makes it kind of challenging to figure out a way to try to measure the static antipole moment of an electron, because you would have to do this in an environment where J is non-zero. It's a very nice review here which discusses some of these issues. Okay, so how do we isolate the form factors? And the way I like to do it is through what I call a projection method. And so I've written this formula, and these are identities. If you choose G1, G2, G3, and G4 appropriately. What I mean by this is if you plug in for gamma mu, that expansion in terms of F1 through F4, and plug it into these formulae, you'll get F2 on the right-hand side if G1 and G2 are chosen in this way. And similarly for G3 and G4. Now this gamma mu in a computation is just going to be the evaluation of some Feynman diagram. And so my method, since I'm going to want to compute F4, for instance, is to compute the Feynman diagram and then stuff it into this formula, and out will come F4. Now, I want to be careful and do this first in D equals 4 minus 2 epsilon dimensions, because along the way there will be divergences, but they have to cancel because we're talking about physical quantities at the end. The overall multiplicative factors here, this 1/2 D minus 1, you can just as well put D equal 4 there because it's just on the outside multiplying something that will eventually be finite. But in fact, this guy you have to keep around if you do the magnetic moment, anomalous magnetic moment calculation. Again, in our textbook, we keep it around and show that this exact form exactly is needed to make everything work. Okay. So one thing I want to point out is that there are these funny singularities that q squared equals 0 and q squared equals 4m squared in these factors that are going to appear here. Those are not real. They can't, at the end of the calculation, they must disappear completely. And that's why I like the projection method, because it serves as a great check of your calculation of your algebra, because if they didn't cancel out, you know you've done something wrong. And moreover, the final result, of course, must be UV finite. But in fact, I was worried for a moment. I've never seen this discussed in textbooks about what could you get finite results from an epsilon times 1 over epsilon in the middle of your calculation. Turns out the answer is no. This does not happen at all. So those are two important checks of your calculation. Quick remark. This talk is about the moments of the electron or muon. If you were to discuss a neutral Majorana fermion, then F1, F2, and F3 are exactly 0. So the anapole moment is the only form factor that's relevant. This was actually discussed in a very nice parallel session talk on Monday. So you might want to look at that. And it's actually quite relevant for direct detection of Majorana fermionic dark matter, because it's the way it interacts with the electromagnetic field. Okay, so now we get to do the calculation. So here are the two diagrams that contribute to F4. And this trace is because I'm doing the projection. I'm projecting out F4. So it's a straightforward loop calculation. My PRs and Ls are the standard left and right projection operators. L here refers to the left-handed muon. R is the right-handed muon. Remember, we're in supersymmetric QED. Gamma tilde is the photino. And so when you you compute the trace, you end up getting this particular integral to evaluate. And if you're familiar with Passarino-Veltman loop functions, you can immediately write down this result here. Notice I've kept d not equal to 4. And at this stage, these functions, theCij's, all have these arguments. In the next slide, I'll just remind you what these Passarino-Veltman functions are. So this first term is from the left-handed muon, and then there's a second term, the right-handed muon. And by the way, if the left-handed muon mass is equal to the right-handed muon mass, and this term is exactly the same as that term, it cancels, I get 0, and that's what I would expect, because remember, I need parity violation to get an anapole moment form factor, and there's parity violation in softly broken SUSY QED if ML is not equal to MR. Okay, so now this result should disturb you a little bit, because if you know the Passarino-Veltman function, C24 is divergent. So if I were to throw away the right-handed muons, I would have a divergent result here. So just to review quickly, here are the Passarino-Veltman functions relevant for this talk. Here's the divergent quantity. The only divergent quantities are C24 and B1. B1 hasn't shown up yet. It will in a minute. So those are the formulae. So given the fact that this is divergent, there's still this q squared equals 0 and q squared equals 4m squared singularity in there. So I must have missed something. And when I did this calculation for the book, I spent a couple of days knocking my brain saying, where did I make the algebraic error? And then it suddenly dawned on me that I left out an important contribution. And the contribution is self-energies. And here are the self-energy graphs. If you've done the magnetic moment of the muon calculation, your first reaction is, what the hell do we need self-energies for? Well, in the magnetic moment of the electron or the muon, the self-energy is, when you project out F2, you get 0, because these graphs would just correct F1. But for F4, these are parity violating if ML is not equal to MR. And so you need to include them. Now, you really shouldn't think of these as Feynman diagrams because this guy here is on shell. There's a way to make sense of this, but the usual way to do this is by LSC formalism. In other words, you replace your spinner with a z to the 1/2 times that spinner for an incoming fermion line. For an outgoing fermion line, there's a z bar. Z bar is related by z like so. And in general, you can decompose z and z bar into left-handed and right-handed pieces. By the way, in the two-component formalism, this is so natural. You don't even think about it. It just falls out. So I like the two-component formalism for this particular calculation. It's very straightforward. But in any case, so I therefore make this replacement here, which means the one-loop self-energy diagrams that I had previously really just give me this. And so basically my task is to compute these delta ZL and delta ZRs by evaluating the 1pi self-energies in the on-shell renormalization scheme. So here I'll mostly follow the results of this paper here, which give very nice derivations of these delta ZL and delta ZRs. This is the diagram I'm going to compute. This is its decomposition. You'll see in a minute that for this particular contribution, these terms actually don't exist. So here it is. Here's the calculation, very simple. So the sigma d, sigma bar d is 0, and the sigma L and sigma R are these B1 functions that I flashed up for you just a minute ago. And so having done that, I'm now ready to put everything together. Here's the final version. Well, here's the self-energy term in terms putting this thing into the projection. So there's the trace. And this CL and CR are just those wave function renormalization corrections. And when you plug that all in and use the sigma L and sigma R that I had on the previous slide, this is what you get for the self-energy contribution there. And so now I have to add that to the vertex. Here's the final result. And you immediately see C24 plus 1/2 B1. And if you recall their divergent structure, that's UV finite. So indeed, I get a nice cancellation of the divergences as I expected. What about these mysterious singularities at q squared equals 0 and q squared equals 4m squared? Well, here there happen to be a couple of very useful identities involving these Passerino-Veltman functions. I've written the two that you need. You plug this in here, and miraculously, you get factors which cancel those two terms, and you end up with the final result that looks like that. And indeed, these singularities go away. It's finite. So when I got this, I knew I had at least gotten the right answer up to perhaps some typographical errors. And indeed, it vanishes when ML is equal to MR. So now let me set the muon mass equal to 0 because that's much smaller than all the other masses. Then those C functions become very simple integrals. Here it is. And I've given you two particular limits. I wrote this one limit because earlier in this conference we heard that the compressed SUSY limit is one of the areas where you can get the SUSY contribution to the muon anomalous magnetic moment. So I figure that might as well do the same limit. This is what you get for F4 0 for the contribution to the anapole moment. Yeah. Okay, so That's just SUSY-QED. You would like to do this for the full MSSM, but when you do it for the full MSM, you have to bring in the entire electric sector. And in fact, you don't need supersymmetry. There would be a contribution just from the standard model because W's and Z's violate parity when they interact with fermions. And there's a long literature on this subject. And it's very confusing because in the 80s there were papers like this, is the anapole moment a physical observable? And here it's stated, in contrast with the charged magnetic dipole moment and electric dipole moment, the anapole moment is not an intrinsic and well-defined property of an elementary particle. People found gauge dependence and similar problem, by the way, with the neutrino charge radius. Then this paper by Robert Stewart and this fellow here claimed to have contradicted those papers. So I quote here, the result, despite earlier claims to the contrary, is demonstrably gauge invariant observable in principle. Then I was amused by this paper here, which followed 6 years later, which says here, the situation with the anapole was also unclear because of the wrong statements of various authors. And he's referring to these two papers here. These guys are serious guys, so it's not completely obvious what's going on. In this paper here, the pinch technique was used to claim that the charge radius of the neutrino was a well-defined object. But this leads me to my penultimate slide. Will the anapole moment ever be measured? I think one really needs to clarify this issue of, if you're going to propose an experiment to measure it, you better understand exactly how it's defined in a sensible way. And just as an example, in this paper in 2003, after all those papers claiming, yes, it's a physical object, they wrote a paper about the weak charge of the proton, which is being measured directly at Jefferson Lab. And they say the latter, there was a term in their expression for the weak charge of the proton, they called it delta E prime. The latter, which corresponds to the anapole moment of the electron, depends on the choice of electric gauge and is not by itself a physical observable. So it's clear that this is still perhaps not a completely settled issue. And just as an aside, I might mention there's a pretty large literature about measuring anapole moments of composite systems, of nuclear states and things like this. And in fact, in this very nice review article by Haxton, and he shows that the cesium-133, the anapole moment has actually been measured and found to be non-zero based on the measurement of the hyperfine dependence of atomic parity violation. But there are lots and lots of effects that go into this. And I don't know whether one can extract a static anapole moment of an actual elementary particle out of all this. So my final slide, the conclusion is, I think it's really desirable to clarify the meaning of what it means to be a static anapole moment of a point like charged lepton. You know, if one can make a sensible definition of this, it would be an important quantity to measure, as important as the electric dipole moment of the electron or its anomalous magnetic moment. There should be something that appears in the particle data group eventually on this object. It's amazing that there doesn't seem to be any experimental information whatever. I've shown you in this talk a very simple calculation and also advertising the book to appear next spring, where, at least in the SUSY-QED calculation, there are no issues of gauge degree, the gauge parameter or anything. It's a completely gauge invariant calculation. So completely physical in that simple theory. And I've shown you that you have to include the self-energy corrections as well as the vertex correction to get a physical result. To extend it to the full MSSM and see whether that paper from 2019 is correct, or wrong. I think one has to address some of those issues in point 1 above. Thank you very much.
So if I understood correctly, so then if you're away from the sources, then this vanishes.
Yeah.
And then how do you imagine to propose an experiment that includes a muon among...
Well, I think muon is probably hopeless, but electron...
Maybe the electron, I see.
I would at least be happy if someone could propose a viable experiment for the electron, but I don't have any great...
Because the advantage of all the other moments are that, well, maybe this is not even physical, you mentioned, but is that you just can be away from the sources. And,
yes.
And this is a problem.
That's one of the challenges.
Yeah, this is a real problem.
Yeah.
Can you hear? So, another property, I don't know whether is there as well, is in the exact supersymmetric limit, the magnetic moment and electric dipole moment is 0, I believe.
Correct.
You must have checked that as well, right?
It's in the book.
Is it in the no, for your calculation.
But originally, Remedi is the fellow, there's another one. Remedi and
So this is for anapole moment as well, right?
Yeah, because the anapole moment requires parity violation. So in supersymmetric QED, for instance, the exact supersymmetric limit is a parity concern.
Yeah. So that's one question. So the next question is, of course, I believe you can.
Wait, the first question. So what about the standard model? Supersymmetric standard model?
The same thing should happen.
Yeah, I haven't checked that. I suspect probably the same argument
Yeah.
that Remedi for RK would also apply to the anapole moment, but I should check that. It's easy to check.
Okay, I mean, this is just, I like very much your technical, I mean, maybe technical, but very insightful talk. I believe that you can easily transfer all your calculations to a Majorana fermion, because so far,
yes, right.
Which is more interesting.
The diagrams would be different. In fact, for the Majorana fermion, you don't have the vertex, the self-energy correction, because the Majorana fermion doesn't have a tree-level interaction.
Yeah, that's maybe easier to isolate the...
For the vertex correction, there are actually two separate diagrams for each left and right-handed slap up. So, yeah, but yes, you can do that.
And the final, I don't know, comment, whatever, is that related to what Carlos mentioned. I think you need to devise or develop a similar formalism what is done for the neutrino charge radius. You have a scattering, a complete true S matrix, and see how the gates dependence communicates or is inside these box graphs, or that's what I believe will come, and try to find projection techniques of using Legendre transforms, whatever. I think this is what done by this paper by Bernabeu, Papavasiliou, and so on.
So let me just say one word about that. So the key question for gauge invariance is whether there's an interpretation of a universal static anapole moment for a particle independent of the source about how you ended up checking that vertex. So for instance, if you insist on replacing the static and electric and magnetic field with, say, a heavy nucleus, so then you're scattering off a heavy nucleus, and then there'll be actually additional diagrams, like box diagrams and things like that you have to take into account. And that was the whole point of the pinch technique, because then there you are able to, the extra diagrams, you can divide up into two pieces, and et cetera, et cetera.
They give some projections.
Right, but what I think is very important is to develop a concept of the
static anapole moment that's independent of the production of the fields in which the particles move. So it should be universal.
Okay, so I see no other questions. Let's thank you. And the next speaker is Nick Mavromatos, and the title will be on the screen.
Hidden. Thank you very much. I would like to thank the organizers for inviting me to this very interesting conference and place, of course. I'm going to discuss something which usually is not made use of in cosmology, namely gravitational anomalies. And the outline, first of all, of the talk will be the following. I will motivate, I will explain the main framework where this cosmology will take place, and that's the running vacuum model. This includes inflation, which is due to non-linearities of gravity, so you don't have external inflatons, but as we will show, there is a scalar field associated with some condensate. I will embed this model to string theory, to low energy string-inspired gravitational theories with torsion, which will correspond to axions, but also it will include gravitational anomalies, which I will explain. They are not necessarily bad things. In fact, I will say that if you have primordial gravitational waves, then they can induce condensates of anomalies. And then it's something that could connect me to the previous talk, because I will have a Lorentz sensitivity violation, of course, by torsion action. Not that I will do that, but all the anapole moments, the electric dipole moments and magnetic moments, once you have Lorentz violation, which induces CPT violation, and that's not bad. It's like having a Lorentz violation if you have a constant electric field in QED. If you have a background in QED that violates Lorentz symmetry, then you may get an induced anapole moment, and that's how actually you impose very stringent bounds on Lorentz violation from quantum gravity or whatever, using this anapole moment or dipole moment formalism. I'm not going to discuss this in the talk. And then the final thing that I'm going to discuss in this talk, because unfortunately I will not have the time to see how Lorentz sensitivity violation is associated with the fact that we exist. So in other words, we do exist. The point of this talk is that we do exist because of gravitational anomalies that induce Lorentz sensitivity violation, and therefore you get unconventional electrogenesis. The final part is something that I have been doing recently with Ioannina Stamu and Vasilis Panos, which is these cosmologies will lead to some potentially observable effects in enhancing the primordial black hole densities. Now, so this is up, I'm going to only discuss up to that point. Now, what is the connection of supersymmetry? It's a subtle connection in the sense that supersymmetry, as I will argue, can lead to the sufficient production of primordial gravitational waves that could lead to the condensate of anomalies, and also the second part that I will discuss is this enhancement of the cosmic perturbations and the densities of primordial black holes that could affect the profiles of the gravitational waves at the exit of inflation with, in principle, detectable differences in the LISA. So the motivation is standard. I don't have to say anything. Lambda CDM seems to work very well, but we understand nothing of it in the sense that we don't have any microscopic understanding of the cosmological constant. We also heard, if you accept this point of view, that the lambda may affect, may lead to some models in the swampland. I personally don't want to discuss this further. We don't understand the nature of the dark sector, but also we don't understand microscopic models of inflation. For instance, is inflation due to an external field, or is it due to some hidden scalar fields or other non-linearities? I will also add to this, as my motivation, that the lambda CDM appears to be recently in tension with the measurement of the Hubble parameter, but also with some galaxy structured data. In connection, this usually you don't see it as a motivation to look for non-conventional cosmologies, but in my case, for obvious reasons that I discussed earlier, is associated with a microscopic understanding of matter and antimatter asymmetry in the universe. The standard way is, of course, CP violation with the Zakharov's condition that creates the necessary conditions for having dominance of matter over antimatter. But of course, in the standard model, as we know very well, in the hardware sector, the produced baryogenesis is 20 orders of magnitude below the required one. And that's one of the reasons why you need to go beyond the standard model. I will try to argue that maybe this has a geometric origin in the sense that this spontaneous CPT violation that I was talking about, due to some flux fields that will acquire constant values in the early universe, maybe you can get this. So let me give my overview. In fact, I paraphrased the log of the conference here in the sense that instead of having the one and everything, I will have parts and the whole. So parts in the sense that replaces not the one, but each one. And these are inseparable. This is not Heraclitus, of course, this is Werner Heisenberg, just in case you confuse him. So, what I will argue is the following. Deviation from the lambda CDM and alleviation of cosmological data, tension, and observed matter-antimatter asymmetry can be, in principle, linked with these microscopic inspired models which involves gravitational anomalies and torsion, which manifest itself as an axion. And you have anomalies you have condensation of anomalies which, through gravitational wave condensation, which leads to Lorentz and CPT violation, and hence you produce this matter-antimatter asymmetry. The axion, on the other hand, the dark matter in this model has a geometric origin because it's associated with a dual of the torsion that, as we see, happens. So the various parts are here, which I've just talked about, and of course, the whole is this stringy running vacuum model, which now I come to describe. So this is, what is this framework? Is a framework, is a phenomenological framework, which for a dark energy setting, in which the energy density of the vacuum is not a constant, but it is a function of even powers of the Hubble parameter that comes from general covariance, because a curvature is proportional to h squared. But it still satisfies, despite its time dependency, still satisfies the de Sitter type equation of motion between pressure and energy density. Of course, you would say that I may have h dot. That's fine, but at an effective field theory level, the h dot can be related at each era with a cosmic deceleration parameter, which may be assumed approximately constant, so you are back to this formalism. Now, I should say that before these people, in non-critical string theory, which time was interpreted as a renormalization group scale of the worldsheet, we had such an equation. And of course, you can understand its connection with the running vacuum in the sense that the running vacuum has been was postulated phenomenologically to be described by this Vita function equation, where all these masses come from integrating out massive fields here. And the role of the renormalization group scale is played by the log of the Hubble parameter. In non-critical string theory, this can be associated, but I'm not going to discuss this now. Now, having a time-dependent vacuum energy, you can write down the continuity equation for matter, and then arrive at this equation. And this is how inflation arises dynamically due to non-linearities, in the following sense, that you have a solution of this differential equation. Notice here that these values are these coefficients, h squared and h to the fourth. The entire phenomenology of the universe is sufficiently described by truncating this series to h to the fourth. h6 and higher is not necessary. So, what you have is in this solution, in the early, this is the scale factor of the universe, I assume I showed it up here. In the early universe, where this is much smaller, you get dynamically a de Sitter phase, which as we shall see microscopically is unstable, and then you have the entire evolution of this solution, and in today's era, you have this coefficient of the h squared term, which is dominant, and this now in the modern era doesn't play a role. The zeros here means values evaluated today, but this does. You can fit it with the data, with these values, and also this provides a running vacuum energy today, a deviation from lambda CDM, in principle observable, which you can fit to the data by having, for instance, this sort of, you can, in the original model, they assume even a mild time dependence in addition to the age of the cosmological, of the Planck constant, of the gravitational constant, to fit both data, the growth data and the H0. But, as I will argue in this talk, if I have the time, or at least I mention it here, due to gravitational anomalies, you may have an RVM form which this mild T dependence in the dark energy will be expressed as an effective Planck constant, not constant, but Planck parameter, which has logarithmic dependence of the H square. So let me start very quickly. I mean, in this audience, probably you don't need that. We heard in previous talks that actions could be associated with torsion. Well, actually, we didn't hear that. We heard that actions can play the role in gravity, but in the standard string theory, you have the massless multiplet, in superstrings at least, in which in addition to the dilaton and the spin 2 traceless tensor, which is the graviton, you have this Kalb-Ramond and the symmetric tensor field in the closed string sector, which is associated with U1 gauge symmetry. This is like a gauge field with two indices. The low energy effective action of string theory up to this order is given by this term here. This is the field strength of this B field, which in view of the Green-Schwarz mechanism for anomaly cancellation is modified by the gravitational and gauge Chern-Simons terms. And this plays the role of torsion in the sense that you can absorb up to order alpha prime, by the way, fourth of the derivative that we're going to discuss in this talk. It can be absorbed in a generalized connection where the Christoffel symbol is not symmetric, and that's torsion. Assuming dilaton throughout, I don't have to include Gauss-Bonnet terms in this effective theory, but because they are total derivatives. But if you have a non-constant dilaton, you have to include them. So this is the connection of this field with the torsion. Now what's happening with action, why this is action? Because you can take its dual, which you can implement, you can take the Bianchi identity I mean, this definition implies if you take the D, the exterior derivative of this term, this is 0, but this gives you this RR tilde term, which is the gravitational anomalies. This is the standard. If it would be electric field, it would be electric times magnetic field, and the analog in the gravitational sector is this. You implement it in the path integral, and essentially you arrive, including fermions, in this effective action, where classically the dual of this H field is the action. That's the so-called string model independent action in string theory. And that's its geometric origin. Now, notice that this term, by partial integration, if you assume that boundary terms play no role, would also produce, again, this anomaly term. That's the Riemann tensor, and the duality here is defined by this dual tensors here, which, as I said, if this is the electric field, then its dual is the magnetic field. If that's the electric, this is the magnetic, and the corresponding one in curvature. These are the terms that usually are ignored. In the standard Robertson-Walker term, this is 0. You don't have it. But if you have parity violation or CP violation, this term is not 0. If you also have a axisymmetric space-time, like a rotating black hole, a Kerr black hole, this also sources this term. So in Robertson-Walker background, this term would be 0. An important point by integrating out this H field and passing to the dual formalism is that you always have a repulsive axial fermion-fermion interaction term here, suppressed by Planck scale. Therefore, you will not see it in the effective theories. And of course, as I stressed before, our action here are associated with torsion through this relation. Now, so this is our model. It includes all fermion species. Now let me concentrate on the anomaly terms. Unlike the FF dual term, which does not contribute to the stress tensor, because its variation with respect to the metric gives 0, this term does. And that's what people think in principle is bad, because if you consider contributions of this term, which is the gravitational Chern-Simons term, or Hindenburg signature as it is called, if you consider the variation of this with respect to the graviton tensor, you get the so-called cotton tensor, some form of the cotton tensor appearing in the fundamental paper of Jakiv and P. The cotton tensor is always proportional to the derivative of the action. Why? Because, of course, if the action is constant, then this is a total derivative, like the FF dual. So these terms are total derivatives, and therefore they wouldn't affect the variations. But it spoils the conservation of the stress tensor, if it is there, and also contributes even negative contributions to the stress energy tensor. And here it comes its relation with the other topological invariance, the Gauss-Bonnet, which is non-zero in the presence of dilatons, because like in the Gauss-Bonnet, when it contributes negative contributions to the stress tensor, as we shall see. Here we have 0 dilatons, so no Gauss-Bonnet, otherwise you have to include it. In the Einstein's equation, the presence of the cotton tensor, due to its non-conservation, unless you have backgrounds that are anomaly-free, affects the conservation of matter, But that's not, and some people say, okay, this affects the diffeomorphism invariance. That's not the case. This is fully diffeomorphism invariant. Simply it expresses, because you can always define an improved current by placing that on the right-hand side. That's a conserved tensor, which simply expresses the exchange of energy between the action and the gravitational sector, nothing else. Now, let me go to the role of supersymmetry, which might be of interest to this conference. Of course, my supersymmetry, as I am naive, is broken at a pre-inflationary phase. So you will not have any phenomenological consequences. I don't know if that's bad or good. I mean, so far we haven't seen it, so I'm still consistent. So you cannot claim I'm consistent phenomenologically. Now, let me make the basic assumption we made in this work with Joan Solin and Spivos Vasilakos, that in the early universe at 3 level, only gravitational fields from the string multiplet, only strings from the gravitational lowest energy multiplet of superstring appear, like in the bosonic sector, the axion and the graviton and a constant dilaton. The total derivative of this term is written in this form. This is minus because I partially integrate. This is the gradient of this topological current. Now, before if you don't have formation of structures like primordial black holes or gravitational waves that violate parity and therefore would contribute to this RR tilde, then the action only assumes a stiff equation of state, and it could dominate some pre-inflationary era of the universe. For instance, this is a reminiscence of Vesseldovich's original idea that baryons could form such soft matter. Now, how supersymmetry comes in? It comes as a provider of a potential origin for gravitational waves. How? Remember, in our assumption, we assume only that fields in the gravitational multiplet of the string are present, and gravitino is, of course, the partner of graviton, so it belongs to that multiplet. Now, the gravitational waves arise from domain walls that are formed, unstable domain walls, that are formed, for instance, if you have a condensate of gravitinos which break dynamically supergravity, or some gauginos. This, of course, it would take me a whole new lecture to explain, but roughly speaking, you form a condensate of gravitino fields in supergravity. Let's take, for the sake of concreteness, n equals 1 supergravity. Of course, because you break supergravity, this is not at 0, it's at positive value. And this, eventually, the condensate has a double well potential, so you have 2 vacua. You may assume that it's stabilized, and that's a big question, because here you don't have to pay attention, but that's the effective potential of n equals 1 supergravity if you consider this Goldstino formalism of Wess and Zumino. Actually, if Fotis Farakos could be here, unfortunately couldn't due to illness, he would have talked about some Goldstino work that he was doing in which he is using this Goldstino not on this form, but to break supersymmetry in an analogous way. The important point to notice is these terms, logarithms, which if the sigma exceeds the f, then you get imaginary parts. And that's the instability of the vacuum. For any other value is stable, and that's why if you have the f, which appears as in the Wess-Zumino original Lagrangian, for the Goldstino, then you don't get imaginary parts, and you may be thinking that this is stabilized. However, we don't want this to be stabilized. What we want to be stabilized is the RVM vacuum, the running vacuum, which I will come in a minute to explain. Now, what's happening is the following. Once you may have a bias of this double well potential, which is such that it could be due to a statistical bias, for instance, due to unequal populations that occupy the 2 vacua. This could happen in some models, for instance, that Zygmunt Lalak, Bartov Lola, the late Graham Ross, and Steve Thomas have been looking at, percolation effects. Here, I'm not going to spend the discussion here, but you will see that in this particular context, you have these populations which are not equal to 0. You can perform these diagrams. This is the gravitino condensate for us. Notice that in an earlier work that I have done with John Ellis, here you can have a first hilltop inflation, not necessarily slow or running, and that's the Hubble constant of inflation, and then the system goes and stabilizes the condensate. And another, if you don't want this scenario of broken n equals 1 supersymmetry, you may have gaugino condensates, where again you have an R symmetry which breaks as Z2n in as you engage sugar models to Z2, and then you get an unequal energy shifts because of this number here. Again, you will produce unstable domain, yeah, very nice, unstable domain walls. Now, so very quickly, what's happening, you get the imaginary parts, this system will move to this RVM vacuum, which now I'm going to discuss. So, the first inflation is important, and therefore supersymmetry is important, that's what I wanted to say in this talk, because you have spatial inhomogeneities, and they are washed out by the first inflation. Then you have the stiff matter era, and then the gravitational anomalies. So let me go very quickly to how the CPT arises. If there are gravitational anomalies, you may have a condensate of this term plus quantum fluctuations, which would appear as a cosmological constant-like, almost one. It's time-dependent, so the Swampland is avoided. It's time-dependent here. And then you can also write it as a total derivative. Let me see how I can estimate this condensate, because that's a full quantum gravity problem. You cannot assume, you can only assume some weak gravity computed, deduce an RVM vacuum, and then get the inflation self-consistently. So, assuming inflation, I can compute this condensate by graviton modes, assuming that I have a proper number density of gravitational waves, which is here. I assume B dot field weakly coupled, and I arrive B dot is the action. I assume homogeneity, and I will arrive at a self-consistent picture. So here is the gravitational wave equation, which stems from this derivative assuming isotropy and homogeneity. You can solve it, and in principle, usually generically, you can see that it decays exponentially unless you fine-tune these values, the ultraviolet cutoff of the graviton modes and the Hubble parameter. You can fine-tune it in such a way that this, despite a mild time dependence, is approximately constant. And this is where spontaneous CPT violation arises. Why? You see, look at the action equation of motion. If you have a condensate, the current, the topological current is constant, which is due to a condensate, that violates Lorentz violation. There are no Transplanckian modes, and you can try to estimate the B dot approximately constant, and if you want to have Planck data, there will be of epsilon. This is a parameter that you get a string scale in some ways, but you can always absorb the restriction to the O1 data. So now I'm coming to the final part of the talk, how inflation arises. First of all, let me say that I have this effective action. If I get an almost constant condensate, I get a linear action, which is like action monodromy potential. You may think that you have a problem. I can get this approximately constant if the solution of my action is such that this is much bigger than this term at the end of if holdings. That could, you could start thinking that you could violate, because it's necessarily bigger than Planck scale, that you could violate the Swampland conjecture, and you might try to solve it this way. This phi is a generic action monodromy, but you don't need it in this particular case, because that condensate is essentially, in our anomaly, the linear potential is also equivalent to a B dot to the derivative times the topological current, and that is Planckian, so the distance Swampland conjecture is avoided. With this condensate, you arrive at a RVM form. You see the h to the fourth, the h squared, and that's, you see the anomalies. What you can check the equation of state, that it is, the total energy is minus P, and you can get the condensate really, it passes from a phantom matter that you would have by having alone the Chern-Simons term to this. So that's how you get the inflation. And you don't, when I argued before how you get it without external inflaton fields. The important point is that here is a different role of CP violation. That's perfect, thank you. This is just to say that in contrast to the standard RVM that it was, this coefficient assumed positive, this is what I said before. The RR tilde term, because it's a fourth order gravity term, like the Gauss-Bonnet, gives contributions which are negative. This could play a role in leptogenesis, which I don't have the time to discuss. And now I'm going to come to the penultimate top, very quickly, topic of the talk, by enhance how these models can enhance gravitational waves. This is, originally, you can see that this is a linear, you can have a linear axion potential of this form, which you could also get from other reasons, from string compactification. But here, I remind you, this is a total derivative term. Now, this is the work that I've done with Stamu and Spanos. If you have this linear term, you may have worldsheet instantons in which, in addition to the linear potential, you would get also cosine periodic modulation of the potential. In this particular case, if you in string theory you have many actions. If you consider two actions, B and A, for simplicity, then that's which you could also get in other string models, then you would have this sort of potential. The linear terms, also every action would couple to this gravitational universally with its coupling constant, and you would get the modulation. Assuming that the leading modulation comes from the cosine term, in this work we have examined two cases, and you get enhancement perturbations. In the case one, where you have this hierarchy of scales, lambda 1 is the cosine, lambda 0 is our scale of the anomaly, you see you start having in the action step-like features, and you get a high number of the R, of the ratio of the tensor to scalar perturbations in this particular case. I don't know exactly what's the minimum one. We didn't do an exhaustive search for the parameter space. What we know is that the periodic modulation of logarithmic, they seem to be fitted by logarithm of k. And that leads to a resonant peak in the gravitational waves. And that is in various cases. This is in agreement with some work by Fumagalli, Witkowski, and Renaud Petel. Phenomenological work. So this is our results. This is the primordial spectrum. These step-like features due to the periodic modulation. Sorry, can I take 20 seconds of leave this? And they lead to these seesaw features. And this can lead to significant enhancement of the primordial gravitational waves. In the other case, which was discussed by Zhu, in the other hierarchy, you don't have this feature. Forget about the numbers, you don't have this feature. This is a smooth feature. But still you get primordial waves. And that is my penultimate transparency. You could have a distinct between these two cases. If you are in the running vacuum case, you may have, because of this seesaw type, periodic modulations. I don't have the time, as I said in the beginning, I finished actually. I don't have the time to discuss post-inflationary physics, but I could stop by giving you my conclusions and outlook that we discussed the cosmic cycle here, where we started from actions and torsions, we invoke anomalies, and we ended up in a running vacuum model, and the framework that we discussed was the string theory. Thank you very much.
Thank you for this very nice talk. I wanted to ask, you considered this stiff period after your first inflation. What's the significance of that? I missed it.
Yeah, the stiff period is that actually there's no significance of the stiff period. The stiff period comes because the action is massless. It still hasn't developed a mass. What is important is that this pre-inflationary phase, this first inflation that washes out all this stiff period, and this stiff period, essentially you can study what I said, you can study the percolation effects. So the stiff matter can lead to percolation effects of this bubble formation. But you could have it with other, you don't have to have a stiff action. In this particular case, I'm trying to find, yeah, here, you see the fact that it's a stiff action, this, you can get, once you stabilize the condensate, then the actions appear with this, in this, is a dominant phase. So it's a consequence of the fact that the action is massless rather than.
Thank you. Any other questions?
Thank you very much for a nice talk. So, I'm sorry, I don't know much about the condensation of gravity anomaly, but I do have an example in the Yang-Mills theory. So if you mentioned also the instantons, and in the Yang-Mills theory, if you're including the non-perturbative instantons, then after integration, if you don't have a quark mass in your theory, then this kills the condensation of, for example, the gluon condensations.
Right.
So do you have any comments on what happens
Yeah.
in the gravity?
The gluon, of course, is not FF dual. The gluon is FF, right? The condensate is FF. In our case, we assume that we don't have gauge fields in the early universe. We only have the RR tilde. If we have gauge fields, like gauge in or sugar, for instance, then in principle you may have FF tilde condensation. You may have, that would be corresponding to the instanton number, which would be related to what Elias was talking about yesterday. But we don't have these gauge fields here. But it's not related to the gluino condensate, because that is the, the gluon condensate, because that's the FF. Is G mu nu rather than the anomaly.
So ceremonial.
New opportunities for electroweak variations.
Okay, so good morning, Kalimera. So it's a pleasure to be here. Also my first conference in 2.5 years in person. So the organizers asked me to talk about electroweak baryogenesis, so here I am. So I will do a very brief introduction. So the mystery of our asymmetric universe. Antimatter is governed by the same, by the same interactions as matter. The observable universe, as we know, is made of matter because we are here. And we only see antimatter in cosmic rays or produced in the laboratory. And so with precision cosmology, we have information from abundance of primordial elements, from the Big Bang nucleosynthesis, and also from CMB. And we have baryon abundance of the order of 1 part in, less than 1 part in a billion. So what generated the small baryon asymmetry? And it was initial conditions or during the evolution of the universe. So we know that in the standard model, baryon number is conserved at the classical level, but violated at the quantum level. And this is because we know that for gauge theories, one finds violation of the classically preserved symmetries due to the actual quantization process, and this is what we all well know as the ABJ anomalies. The point is that for the chiral weak interactions, then the gauge symmetry preservation yields the non-conservation of baryon and lepton currents, as written here. And we see that the instanton that is actually defined as the semi-classical probability of tunneling between a vacuum with one baryon number and another is related exactly to the integration of this right-hand side. So there are basically, the instanton is defining these different vacuum of quantum numbers of different baryon and lepton number. And so anomalous processes violate both lepton and baryon number, so B plus L, but B minus L, as we see from here, is preserved. So these anomalous processes can proceed via an Sphaleron configuration that is made by a configuration of Higgs and gauge fields, and we define the height of the barrier that divides two non-inequivalent vacua as the Sphaleron energy, which is on top of that related to the vacuum expectation value of the Higgs. Okay, so this, I guess, is all very known. So this is a nice picture that I think is somewhere in Russia, but I like it. Not picture, a sculpture. So, so the mystery of our asymmetric universe, baryons and antibaryons and photons were equally abundant in the early universe, we think. And so to remove partially antimatter, the CP asymmetry related matter and antimatter must be violated. And of course, we need net baryon number if if baryon number, no net baryon number would be there if baryon number would be conserved all times. So this is the starting conditions for baryogenesis from Sakharov. Baryon or lepton number need to be violated if the universe is star-symmetric. C and CP violation is needed so that baryons and antibaryons are treated differently to remove antimatter. And of course, we need out-of-equilibrium conditions to suppress whatever the inverse process, so otherwise we will wash out whatever we are generating. So these are the three requirements that are actually, all of them fulfilled in the standard model. And I will go back to that in a sec. So there are many possibilities for baryogenesis. I think Apostolos will talk tomorrow about the nice opportunity of leptogenesis. Today I will concentrate on electroweak baryogenesis. Baryon number violation at 0 and finite temperature. So at 0 temperature, we know that these numbers of baryon number violating processes are quite suppressed. This violation rate is something like 10 to the minus 120 or so. At very high temperatures are highly unsuppressed, but at finite temperatures they are only Boltzmann suppressed, and this is the exponential of the minus Sphaleron over the temperature, where this Sphaleron, as I said, is proportional to the vacuum expectation value of the Higgs at the temperature of the phase transition. So if we start with B equal L equals 0 at some high temperature, then what happens is that there is, if there is a first-order electroweak phase transition of this type, so basically it's defined the critical temperature when the two vacuum have the same depth in the potential. So what happens is that the universe tunnels from this situation where the Higgs is off to the situation where the Higgs is on via bubble nucleation. And so these bubbles expand almost at the speed of light, and the process is, near the bubble wall is highly, highly abrupt. So what happens is, if we look here at the bubble wall, that particles flow into the expanding bubble wall, and if there is CP violation, the first thing that happens is that the wall exerts different forces on particles and antiparticles, so there is some reflection and some transmission that is different, so this is what we are trying to say here, so this is different effect of reflection and transmission from particles than antiparticles, and that generates what is called a chiral asymmetry, as it is shown here, so this is as you see, of course, if I add these two terms, there is no net baryon number generated, but we are generating a chiral asymmetry. Then our good friends, the sphalerons, which I remind you only see left-handed particles, will transform whatever quarks into antileptons because they violate B plus L, but conserve B minus L. So quarks into antileptons, and antiquarks into leptons. However, because we have generated this chiral asymmetry, there are more quarks than antiquarks, so this process is faster than this one. This violates baryon number by 3, and the other one by minus 3, so you generate a net baryon asymmetry, and this is what we see here. And this is what I try to explain here, so we start with this chiral asymmetry, delta, and so the right-handed is not touched by the sphalerons, but the sphalerons are changing some fraction f of these quarks minus antiquarks into leptons, and so we get a net baryon asymmetry generated this way. And of course, baryon asymmetry and lepton asymmetry are generated at the same time by the sphalerons. Okay, so the sphalerons help us to generate this baryon asymmetry. We generate that at the moment of, let's say here, of the electroweak phase transition. Then the problem is that the sphalerons are working for a short period, and then we need to shut them off quickly to prevent a washout. And if we consider we solve the right equations for that, we see that whatever baryon asymmetry, this is MB over the entropy, is generated at this critical temperature needs to be the one that we want to have today. And so for that, this exponent has to be of order 1, which means that this value here has to be much lower than 1. And this implies that E over T critical has to be quite large, of order 50 or so, and this connects to V over T of order 1. And what we see here is nothing but requiring that the rate of baryon number violation becomes lower than the Hubble constant. This is exactly what is asked. This relation is what is asking that this is much lower than 1. So when this happens, baryon number processes are frozen, and whatever we generated in the process that I described to you before is what we have today. Okay? Okay, so to preserve a baryon asymmetry demands a strong first-order phase transition. And this is usually what most of the calculations do when you decide to define electron biogenesis. However, this is not the end of the story, and one of the examples I will try to show you today will go into the direction. In reality, the transition into this broken phase does not occur really at T-critical, but at the moment where bubble nucleation is really occurring, and this is the temperature T nucleation that usually is a little small than T-critical, can be smaller, much smaller than T-critical. So the actual transition, really what you are trying to do is you are trying to consider what is the nucleation rate per Hubble volume per Hubble time to be of order 1. And if you do that requirement, what you obtain is that transition from the false vacuum to the real vacuum to be completed requires that this bounce action, the bounce action is basically the three-dimensional Euclidean action in phase space, in field phase space that connect to vacua. And so we require that this bounce action over the temperature, the nucleation temperature, is of order 140. And if what this means is that if you are in a situation where there is no temperature larger than 0 for which this S over T is of order 40 or smaller, so if always is larger than 140, then there is no nucleation possible. Okay? So let's go back for a second to the standard model. So unfortunately, electroweak baryogenesis fails in the standard model, although all three Sakharov conditions are fulfilled. So baryon number violation, we already discussed, anomalous processes through sphalerons. CP violation, in fact, is very interesting. The fact that we have three flavors is totally linked to the fact that we have CP violation in the CKM mass matrix, but it doesn't seem to play a role in baryogenesis. And of course, we have non-equilibrium process if we have the possibility of the electroweak phase transition. But it has to be first order. So with the value of the Higgs mass, it turns out 125, we see here, that for 125 GeV, the phase transition in the standard model is just a smooth crossover. And if we look at the CKM, so this is the delta, the CP violation phase, well, what happens is that in order to get CP violation, basically you need to get some argument of the mass of the top quark, that is the one that couples strongly to the Higgs, to have a CP violating phase, and the top quark mass has a complex contribution on all at very high order in loops, and so this delta CP in the standard model is very small. Okay, however, that's what we are here, and as theorists to make a living. So electroweak baryogenesis needs new physics, and in particular I will walk you through three examples, hopefully. One is, so there needs new physics, and in particular in most models of extended electroweak baryogenesis, you may have other particles, other scalars, but you always have some type of extra Higgs particles. So this is to render the electroweak first transition first order and to provide new sources of CP violation, both things that the standard model cannot do. So I will talk about these three things in red, but there are many, many possibilities. So I will first talk about the singlet extension of the standard model, because that's the simplest case you can think of, okay? And show that we can have a first order phase transition by perturbing the Higgs potential. Then I will try to make a point, since we are in SUSY-2022 here, looking at the NMSSM, that is the simplest extension of supersymmetry that can actually allow for electroinvergences. The MSSM is ruled out because of Higgs precision measurements and the fact that you need light stops. And then finally, I will talk. So these are two cases where I will tell you about how we change the electron phase transition. But as you see, electron baryogenesis has two pieces. We have to generate the right baryon asymmetry, and we have to keep it up to today. So these are going to tell us scenarios where we can keep it by having a strong first order phase transition. And this is an interesting model where CP violation is there and generates the right baryon asymmetry. Okay, so let me just remind you that, okay, we have to look at the Higgs potential. And so this is what happens at finite temperature in a very simplified way. So this D term at high temperatures is what produces the electron symmetry restoration, and this term at finite temperatures is what produces for sure a barrier. Of course, some models that I will talk about may have a barrier at 0 temperature, but this is the minimal case. Okay, so if we do the due diligence with this potential, we see that the strength of the phase transition is controlled by this trilinear Higgs term E over the quartic coupling lambda. And this is why in the standard model, this term only receives contributions from the gauge bosons, and this is proportional to the Higgs mass, and that's why we cannot have this larger than order 1 for a Higgs mass of 1.5 GeV. Okay? Of course, then there are, so what means we can think about tree-level effects. So this is a simplest case. Tree-level effects means we can ask extra degrees of freedom, singlets or doublets. I will walk you through the doublets, that basically can lower the value of this lambda to some lambda effective and enhance the phase transition. Or there, I will not go into that unless you ask me. So, and then there could be 0 temperature loop effects. We know that we can have new degrees of freedom will enter in the Coleman-Weinberg mechanism to do the one loop effective potential at 0 temperature. And this also can lower the value of this quartic coupling. And of course, there are thermal effects that could enhance, as for example in MSSM with the stops, could enhance this value E. So both cases, lowering lambda or enhancing E, would help us with the strength of the phase transition. So the simplest case is a singlet extension. This is even the simplest case where you don't have any explicit C2 symmetry breaking. And I will not go into a lot of details due of time, but there have been a lot of literature considering the explicit C2 breaking, the C2 preserving case, where basically the extra scalar that I'm putting. So if it is explicit, I can write this type of terms that will give me much more freedom. If it is C2 preserving, then I imply that the vacuum expectation value of the singlet is 0 at today. And a very interesting case is this spontaneous C2 breaking, because it's the most constraining in the sense that you have some vacuum expectation value of this singlet, and it's most constraining because all what you are trying to do when you put extra singlets is to change the contributions of the way the Higgs and the singlet talk to each other. But in the case of spontaneous C2 breaking, which happens if you want to think about a dark sector and dark matter, naturally, in the case of explicit C2 breaking, the problem is that the quartic coupling between the singlet and the Higgs, that is the one that you need to enhance the phase transition, is actually related to the mixing between the singlet and the Higgs, which is strongly constrained by the H. Okay? So normally one would think that it's hard to get it. So, sorry, yeah. So normally we think it would be hard to get this scenario, and so I'm trying to present you the hardest case. So now, of course, I'm not going to go to the details, but we have to have the 0 temperature, 3-level potential, the one loop or Daisy Resam corrected one loop, or RG one loop effective potential, and the finite temperature potential. And so what happens here, so the first question we could ask, so is it possible that the electroweak symmetry or the C2 symmetry is basically non-restore up to very high temperatures or very high energies. And the answer is, for the electroweak symmetry that I won't talk, but there is very exciting work in that direction, you will need like 100 singlets, so it's not so appealing. And, or you can have less singlets, but then some inner doublet, and there's a lot of interesting things of the UV completion of these models. For C2, it's very easy. So here's the high temperature, and this is where we are today. So there are two cases. With symmetry restoration at high temperature, so we have 0, 0 here in this field space of the singlet and the Higgs. And it's possible to do this type of transition where you have the first transition does not break the electroweak symmetry, and then the one that I care about is when the electroweak symmetry is broken and needs to be strongly first order. Or I can start already from symmetry non-restoration, so the S has a vacuum expectation value, and I do a one-step or a two-step phase transition, where again I can have a strong first-order phase transition. I will not go through that, but basically we have done in this the full analysis of the thermal potential, three-level potential, thermal potential, and the one-loop Coleman-Bamberg with daisy resummation. And we obtain the same as I showed you before, V over T. Now we have this, I wanted to say maybe this, in 1 second. So in this scenario, basically you have 5 physical parameters. 2 of them, the electroweak vacuum expectation value and the Higgs mass are oh, really? Oh my God. Okay. Okay. Well, I won't tell you so much then. Okay, so let's speed up. So basically here, the electroweak phase transition has been enhanced and is only occurring, the enhancement for very light singlets. And I will not tell you all this, but I will tell you that it's very interesting that with LHC data, one can look to exactly the case of the Higgs. So the Higgs will decay to these singlets that are strengthening the phase transition. And we can look, and there are all these are current searches of the Higgs into something that goes then to the case of this singlet into standard model particles. And so at the moment, this is a 16%. All this area is excluded. All this area is being probed by LHC. And if you look at this is a nice no-mass paper, you can see that all these regions that are here are regions where you have electroweak symmetry breaking and are going to be probed by LHC and high lumen LHC in a wide region of parameter space. So the simplest case, we have a strong prediction for a light singlet that can be searched for at LHC. So I don't want to, well, I won't go through that because I want to say something about other things. But in the NMSSM, you are having 2 Higgs doublets and a singlet. And one thing I want to show you is we have to be in alignment, but let me just go and show you here the final result. Oops. The final result is here. So the final result I want to show you is 2 things. First of all, as I told you before, we can look at the vacuum structure and T critical, and we can see all the points that are dark here are good points for in some region of parameter space of this 4-dimensional parameter space that we are left with in the NMSSM. And these regions are all for a strong, would be a strong first order phase transition if we only look at V over T critical. However, because what happens is that the tunneling is governed by the height of the barrier that you have and the distance between the minima, if you do the proper calculation with the temperature nucleation, which of course is much more demanding, then you see that many of the regions of parameter space through the tunnel probability are excluded, and there is quite a difference if you look at a given model, so these are millions of models, if you look at the vacuum structure versus the tunneling probability. You should consider the tunneling probability when you have a 3-level barrier in your analysis. So finally, I have the last few minutes, I guess, to tell you about a new model of dark CP violation. The reason we work on this model is because one of the biggest problems is that we have electron EDMs that are constrained very strongly. In fact, the last measurements are for electron EDM of 10 to the minus 29. And if you do a back-of-the-envelope calculation, this is the main contribution, this bar C diagram, this would be 10 to the minus 26 times whatever is the CP violating phase. And for new physics models that are reasonable, this CP violating phase is of the order 10 to the minus 2. So you see that this is already, most models of CP of electron variations would be excluded because the CP violation that you need to generate the desired Bion asymmetry is excluded by searches of electron EDMs. Okay? So the idea is how you consider models where the CP violation is in a dark sector, and so it's transferred to our sector in ways that are much more efficient. Oh, sorry. So we have a model here, a new mechanism for electroweak baryogenesis that works pretty well. And so this is our world here, and this is the dark sector. So originally, we generate the CP violation through the dark sector. There is a Higgs portal that is both sourcing the CP violation and also enhancing, helping in the phase transition. So there is a scalar, a dark scalar that connects to the Higgs. And so this makes possible a first-order phase transition in ways similar, not exactly, of the ways I described before in my simple model. And at the same time, because of the way this turns on and this turns off and this turns on, the Higgs also is sourcing the CP violation. And then there is a set portal that is important, that is, for example, a U1 lepton of a set prime that will transfer the CP violation from the dark sector to the standard model sector. Okay? And so, of course, it's quite complex to make this model work, but in reality ends up being much more simpler than we expected here. So the interesting point is that the leading order EDMs are at least at 3 or 4 loops. And so you can easily be okay with the current bounds of CP violation. I won't have time to tell you a little bit much about, but the idea is that you have the Higgs couples to this scalar, and this scalar couples to some dark fermions. These dark fermions actually happen to be a great dark matter candidate. And as you see here, so this scalar has a profile through the bubble wall that goes down as the Higgs goes up. And because of this profile, here, if these two, if there is a relative phase between this mass of the scalar and this coupling that makes when the scalar gets a vacuum expectation value, gives another mass term. So if there is a phase between M0 and Y here, then as this changes the profile at the bubble wall, a bit the same as the top quark acquires mass when the Higgs turns on, then what happens is that we can generate a chiral asymmetry in this dark sector. So we generate a chiral asymmetry in this dark sector, and then I won't go into details, but I will tell you that this chiral asymmetry in the dark sector is used to generate some static electric potential of this set prime, and because this set prime also talks to the standard model leptons, it generates a chemical potential, and at the end it generates a thermal equilibrium symmetry in the standard model leptons. So we generate basically CP violation in the dark sector. We transmit that through the set prime to the standard model to the standard model sector, and we generate some equilibrium number of asymmetry in the lepton side, and of course then our sphalerons will change that into baryons. The only interesting thing here is that I put a lot of fermions there, and I put a U1, and this U1, of course, for example, is a U1 of lepton plus electron plus tau. That, of course, is anomalous, so you need to generate the right anomalons there. And you need that the anomalons decouple in the thermal bath to basically give a non-zero value of this delta and L. And I don't have any more time, but I want to tell you that looking in this G prime of the U1 L as the function of the C prime mass, there is a lot of restrictions here. All the blue dots give us successful baryogenesis, and there are regions of parameter space where we can have we can probe, and we are testing. So these are the last thing I want to say is that all these models of baryogenesis have the good feature that can be tested in many, many experiments that we are doing now. Okay? So finalizing, I won't say much here, but I would say that I didn't say anything about gravitational waves, but okay. So electroweak baryogenesis is an appealing system, mechanism for the matter-antimatter asymmetry. We need physics beyond the standard model, and we need to tackle the two problems that the standard model has: enhancing the strength of the phase transition, doing the right calculation of the tunneling probability, and on the other hand, generating this 10 to the minus 10 baryon asymmetry that we measure. And I think this is an exciting possibility for new physics models. Thank you.
Thank you very much.
I saw a glimpse of gravitational wave analysis. We didn't plan this, yeah, but I'm curious what you wanted to say about this.
Yeah.
It was one slide, I believe. No?
So in the particular case that we look at, that I have it there, but I obviously, as usual, I prepare a 3-hour talk. Okay, so this is for the model of C2, spontaneous C2 breaking. Okay, and there are, of course, as you well know, a lot of things that enter, like the velocity of the wall, the strength, the real strength of the phase transition. In general, there is a tension between having a strong first order, the stronger the first order phase transition, the stronger the gravitational wave signal. But if it is too strong, then you don't have time for the spirons to be active. So there is a tension there. And putting all together, in this I skipped because these are two cases where we cannot test particularly this scenario through gravitational waves. This is LISA. And these things here should look exciting, but this is before doing the full Coleman-Weinberg Daisy resummation. When you do that, the results are these red things. And we think that the real analysis, if you do a randomization group improvement, would be somewhere here. So probably BBO will have a chance. And there is another Einstein telescope here, but basically in this region of parameter space, things like MAGIS or BBO could have a link there.
Since we are running very late, please keep very short.
It's very short question actually, and it's an answer. So maybe you already said, but I missed that. In the standard model, we already know that electroweak baryogenesis does not work. I missed what was your conclusion for the minimal supersymmetric standard model. We have definitely ruled out this, or it's just still some very big.
If the stops, you need to have one stop that is super light and has become insufficiently strong to the Higgs, and you put all together, that will give you a Muon fusion to the Higgs that is 3 times what is in the standard model and is excluded by precision measurements of the Higgs.
Okay, so you need to go to more extended scenarios.
Try very hard to make it work.
Yeah, I know you did that. I know. Okay, but I did not see the conclusions. That's my problem. Thank you.
Yes, very nice talk. A very quick question. Do you rely on B minus L conservation in your models?
That's a very good question. Thank you. For example, if you have any model that is anomalous free, you will not be able to use this mechanism because then this delta n in equilibrium, because of the SU2, is going to be 0 and you generate nothing. So you need to have a model that is anomalous And then you need to decouple from the thermal bus some of the anomalons, so that at the critical temperature you have effectively an SU2 anomalous interaction for the solids. Yeah, thank you for that question.
Thank you.
I propose more questions. Maybe you ask privately to the speaker, because we have to keep lunch. The last speaker is Marios Petropoulos. And his title, you can read it.
Thank you. So this is probably not the mainstream subject in the conference, so I maybe perhaps with the exception of Sabrina's talk yesterday afternoon. So I try to remove most technical issues, and I hope that what's left is still understandable. So let me therefore start with motivating every somehow word of this title, so that at least we understand where I want to go to. So first of all, why asymptotic symmetries and charges? Well, I'm here referring, of course, to Einstein's equations and solutions to Einstein's equations, and the charges are, you know, can be a mass or angular momentum or not charge. So first of all, these asymptotic symmetries and charges are universal features of solutions to Einstein's equations. So this is an important part somehow of understanding what is behind. And it hints towards holography, and in particular within this talk towards flat holography. Now, actually, irrespective of this holographic correspondence, a solution to Einstein's equations is captured by a set of fields, and these fields are defined on the conformal boundary. Now, the conformal boundary, even though it became popular with anti-de Sitter CFT, was already, of course, known since the work of Penrose in the mid-60s. So the idea of existence of a conformal boundary in conformal compactifications. Now, what is new with holography is the idea that we can put on the boundary some dynamics and describe in this way either the bulk or really a genuine correspondence between the bulk theory and the boundary theory. Now, a question that is actually the one that I will address here is, can we compute the charges, the ones that correspond to a bulk solution, from a purely boundary perspective? And the answer is yes, and this comes with a combination of symmetries of the boundary and the dynamics which is on the boundary. Now, why Carolian dynamics? This is something that will appear in the Carolian dynamics will appear along the talk. And why Carolian dynamics? Well, we are dealing with asymptotically flat space-times. Well, that's my aim. And those have a null boundary, and as such, this boundary is naturally equipped with what is called the Carolian geometry. Now, what is the cotton? Remember, in the title there was the word cotton. What is the cotton? Actually, I'm happy that Nick Mavromatos gave the previous talk. The cotton is a covariant derivative of the Einstein tensor. This is defined in general in Riemannian geometries, and it has it plays a particular role in 3 dimensions. In addition, it admits Carolian relatives. Again, these words will be explained later. You have Riemannian geometries, Carolian geometries. The cotton is defined on the Riemannian geometry, but you can also take the limit and build pieces which are defined on the Carolian geometry. And to summarize somehow the messages of this talk, let me put things in the following way. Among other things, on the boundary of a 4-dimensional Ricci flat space-time, we have energy, momentum, and cotton. These actually pieces generate an several infinite towers dual towers of charges, which are determined directly from the boundary. And, well, these include, for example, the mass and the nut. The mass is electric and the nut is magnetic, as it will appear later on. However, these data carry only a part of the data that you need to put on the boundary in order to describe the bulk. these set of data that you need to put are infinite in number, and this infinite information is what you need to reconstruct the bulk. So this is somehow the summary, and let me directly move to describe what I have called previously as Carolian, right? So we here start with anti-de Sitter and go to flat. So this is performed by taking the lambda, the cosmological constant, lambda, to 0. Lambda is expressed with a k. K is a parameter which is basically the inverse of the radius of the anti-de Sitter, and you send this inverse k, you send to 0, which means that the radius of anti-de Sitter is sent to infinity, and this is how you go from anti-de Sitter to flat. Now, if you describe the Penrose diagrams, you move from a Penrose diagram which has a conformal boundary, which is a vertical hypersurface, so this means that this is a time-like hypersurface, and when you send k to 0, so you go to the flat bulk, this becomes a null hypersurface. So this is a main difference between asymptotically anti-de Sitter bulk and a rich and asymptotically flat bulk. Now, as I said, from the point of view of the bulk, k is the inverse radius of the anti-de Sitter, but from the point of view of the boundary, this k appears as the velocity of light. So sending k to 0 to go from ADS to flat means that from the boundary perspective, send the velocity of light to 0, and this is known as the Carolian limit. So this precisely k, playing the role of boundary velocity, k to 0 is what is called the Carolian limit. This is to be opposed to the Galilean limit, where the velocity of light is sent to infinity. Of course, this is always compared to some typical velocity in the system, right? Of course, this is a dimensionful parameter. Good. And therefore, the null boundary, which is here, is what is called the Carolian geometry in n-1 dimensions, n being the number of dimensions of the bulk. So what is a Carolian geometry? So the name Carolian is borrowed. Actually, it was given by Lévy-Leblanc. Lévy-Leblanc and actually Sen-Gupta discovered the possibility of contracting the Poincaré group in this Carolian version, which is the opposite of the Galilean contraction. And this is the name was given by Lévy-Leblanc. So the basic ingredients in a Carolian geometry, remember in a Riemannian geometry, the basic ingredient is a metric. In the Carolian geometry, it's a little bit more, it's richer because of the following. There is a metric, but this metric is degenerate. Remember that you would have naturally put here, instead of 0, minus k squared. That's how the velocity of light appears in a description of a metric, which is rather standard. This is a typical expression for a bulk, for a metric in d+1 dimensions. These are the space directions, and t is the time, and there is a minus k squared. K squared goes to 0, this drops, and the rest is, of course, degenerate. It has 1 0 eigenvalue. This, the vector associated with the 0 eigenvalue, the kernel, is what is called in this language the field of observers. This is a vector which is just has 0 length. And the dual in the sense of cotangent tangent space, of course, dual not with the metric. The metric cannot be used any longer to raise and lower indices because it is degenerate, is called the Ehresmann connection. These are the basic ingredients of a Carolian geometry that replace the pure metric of a Riemannian geometry. And now the general covariance in this framework is expressed as the covariance or invariance under Carolian diffeomorphisms. Those diffeomorphisms have time, which is the new time is a function of time and space, whereas the new space is just a function of space. This translates what is called the absolute nature of space as opposed to time. And this is the dual of the Galilean case, where time is absolute and space can be mixed with time. Now, what are the consequences of this Carolian nature of the boundary in asymptotically flat space-times? Well, I have tried here to summarize them in 2 items, actually. The first is that if you want to reconstruct this Ricci flat space-time in n dimensions, well, it should this reconstruction should be based on Weyl invariant and Carolean covariant with respect to n-1 boundary. So whatever you construct, the solution that you describe should be from the boundary perspective Weyl invariant and Carolean covariant. Weyl invariant because we are talking about a conformal boundary. And well, we have to use a specific gauge for that. The gauges that usually appear are Bondi gauge or Newman-Unti gauge, and those are not covariant. I mean, there are choices which are made, they make not covariant. There is one gauge which is covariant, which is the Pfefferman-Graham gauge, but this is not valid in asymptotically flat spacetimes. It is singular when lambda goes to 0. In ADS, it is covariant, but we cannot use it here, so we have to use some other gauge. The second feature is that flat holography, of course, if such a duality exists, calls for what we should call a Carolean conformal field theory on an n-1 dimensional boundary, as much as ADS-CFT calls for a conformal field theory on a Riemannian n-1 dimensional boundary. So, for example, if you deal with Ricci flat spacetime, this should be dual to a Carolean conformal field theory in 3 dimensions. So let me say a few words about dynamics. So dynamics in the general sense. So you have, we suppose that we have an arbitrary Riemannian spacetime, which ultimately will be the boundary in d+1 dimensions, and there is an action, and you can define an energy momentum tensor varying the action with respect to the metric. I mean, there is a coupling, and you assume that this is a general covariant coupling, and there is a metric which is responsible for that. Now, if you assume that this system is Weyl invariant, then you end up concluding that this energy momentum tensor should have 0 trace. If you assume general covariance, so you assume that the variation of the action with respect to any diffeomorphism is 0. So any diffeomorphism means that the generator is any vector, depending on any arbitrary vector, any component is an arbitrary function of time and space. This invariance implies that the energy momentum tensor should be covariantly conserved. Now, if on top of that you have some symmetry, some global symmetry, so I'm here referring to conformal symmetries, even though we could do it in general, but since the whole framework is conformal, let's not do more. So if this Riemannian spacetime has a conformal killing field, then you can contract this killing field psi with the energy momentum tensor. You obtain a conserved current, divergence-less current, and you build in this way a conserved charge by integrating the dual of I on any hypersurface, space-like hypersurface. And this gives you a constant, which is a label of the dynamics. Now, we could try now to repeat the same pattern, and that's what we are supposed to do for the Carolean case, which is the case that appears in asymptotically flat spacetime. So in that case, as we said previously, you don't have a metric, well, a non-degenerate metric, so this sort of definition is not good. Well, you have to use the various pieces of information that you have for the geometry in order to build the momenta. So these momenta are here what I should call the energy stress tensor. Ij are just spatial components. This is a variation with respect to Aij. Then you remember we had Bi that was appearing in the Ehresmann connection, and omega that was one of the components of the kernel. Well, this variation will give for you the energy flux and the energy density. These are the elementary fields, the elementary objects that translate the dynamics in a Carolean setup. Now, if now you assume that you have some symmetries, well, if you have Weyl covariance, this will tell you, well, the equivalent of the absence of trace, but this is translated here in Carolean language. And if you assume Carolean covariance, so invariance under diffeomorphism generated by vectors, but now the vector, for the spatial component has only space dependence because we are doing Carolian diffeomorphism, so space is mixed with space only. In that case, when you do that and you put you demand that from the action, what you find is a set of two equations. Well, time and space are now separated, of course, rather than nabla t equals 0, you find these two equations. The details are not important, so what is important here is that this resembles an energy equation and this resembles an Euler equation. Notice, by the way, that this is not 0, this is the divergence or the time derivative of something new, which is not defined through the variation of the action. This is something new in this framework. This is a momentum. So the momentum appears here as an object that has to be there, but is not defined as the variation of the action. So let me say that this can be done, can be done exactly in the same way in the Galilean framework, and you obtain the Galilean equations, so which are similar but different, though. Now, in the same fashion, now you may now discuss currents and charges. You remember this is what we have done previously. Now, the Carolian current is, remember, a current is I mu in general, but here time and space are split, so a Carolian current is made of two pieces, a scalar and a vector, and you can define the Carolian divergence, which is very similar to what we have in Galilean case, is the time derivative of the scalar and the space divergence of the vector. And you can define the charge by integrating an appropriate combinations of kappa and k on a space-like hypersurface, and this is conserved if the divergence is 0. So far, so good. The main difference, and this is an important difference, appears when now you assume that you have an isometry or a conformal isometry plus a dynamics, and you try to merge these things to obtain conserved charges. You can repeat the pattern. I will not do it in detail, of course. The important thing is that you have to define what is a conformal killing vector in Carolian space-time, and this can be defined indeed. And once this is obtained, you combine in an appropriate way the killing or the conformal killing with the dynamics, so with the momenta, and you obtain a current, and the surprise is that this current is not conserved. Well, it is conserved if one of these two factors vanishes. And this is exactly, actually, again, what happens for Galilean physics. In Galilean physics, if you consider a Galilean fluid, so an ordinary fluid like the air in this room, and you want to see what is, if any, conserved charge associated with the boost invariance of our space-time, so we have Galilean boosts, well, you find that there is no such an object, unless the fluid is at rest or unless there is vacuum, there is no fluid. So this is not surprising, but it is different from the relativistic case. Now, another remarkable property is that there is a quantity which is called the geometric shear. It's typical of what's going on in Carolian geometry. If this vanishes, then you know what the Carolian conformal isometry group is. So this is a very powerful property. This is something which is known. You can show that this conformal group is a semi-direct product of a supertranslation part and the conformal transformations of some typical metric. This implies actually that the metric, the time dependence is factorized. So what is left there is what enters here. So what is boxed is what we should remember for this talk. If you are in 3 dimensions, 2 + 1 Carolian space-time, the conformal Carolian isometry group is always SO3,1 semi-direct product with supertranslations. This is the famous BMS4 for Bondi, Messner, Sachs. And this is something that appears very naturally, of course, in this Carolian framework. Let me summarize at this point, before going to the next steps, what are the main messages. So, null boundaries, which appear in asymptotically flat spacetimes, are actually Carolian geometries, where the speed of light is 0. Carolian geometries with this psi ij vanishing have an infinite tower of conformal killing fields, and in 3 dimensions this is the BMS4 group. And conformal killing charges do exist, but they are not always conserved, as opposed to the case of relativistic. Let me now try to apply these things in a few words, first in the case of ADS, and then in the flat case to answer the main questions that I have asked in the beginning of the talk. So I will here consider pure gravity. So pure gravity means that the basic field is a metric. Capital indices are just space-time indices. N is the space-time dimension, and this is d plus 2, since d plus 1 is the boundary dimension, all right? So the usual coordinates that are here are r. This is the radial coordinate. T, the time. T should be actually spelled u as a advanced time. But since there is a u that appears later on, I keep it t. And xi's are the angles. Now, once you have that, you have to gauge fix n plus n conditions because you are in n dimensions, and then you write things in an expansion in 1 over r, you put this expansion in Einstein's equations, and then you try to figure out what the solution is in terms of some independent fields, which I have here generically written F, which depend only on boundary coordinates. Boundary coordinates are t and x. Now, the gauge choice is important. I remind you it is important for 2 reasons. The first is that we want everything to be manifest Weil invariant and Carolian or general covariant from the boundary perspective. So this is what we want to have. And then we want to be able to define the charges from purely boundary considerations, not referring to the usual bulk computation. So this is what happens, for example, in Einstein spacetimes. So Einstein spacetimes are those which are anti-de Sitter, asymptotically anti-de Sitter. And if you do that, a good gauge is what we have called here the incomplete Newman-Unti gauge. The details, again, I cannot give. The thing to remember is that there are 3 basic pieces of data which are defined on the boundary. Mu nu are boundary indices, and boundary here is Riemannian because we are in anti-de Sitter. G mu nu is the boundary metric. T mu nu is the boundary energy momentum tensor. And it's conformal, so it is traceless. And u mu is a velocity field. Again, as I said, the gauge is incomplete, and this u mu actually betrays the incompleteness of the gauge. These are the only data. So no matter at which order you look at the expansion of your solution, you will always need this data. And only those. Any new piece will be described in terms of these former pieces. And once you have that, the only equations of Einstein which remain are just expressed in the form of divergence of T mu nu equals 0. Now, T mu nu, with the help of the field U, can be actually decomposed in longitudinal, transverse, and mixed pieces. Well, this resembles a fluid energy momentum tensor, but you don't have to talk about any fluid. This is a writing. Now, the important thing in 4 dimensions is that there is a cotton. I mean, well, wait a minute. In 4 bulk means in 3 boundary. So we are in 3 boundary, and there is a cotton tensor. Well, the cotton tensor is defined in any dimension, but in 3 dimensions, it can be dualized into a symmetric tensor, and this is the expression valid in 3 dimensions. So this is symmetric, it is traceless, and it is identically conserved. So be careful. The tensor, the cotton of Nick was not conserved because he had a torsion. Here, we don't have a torsion. This is Levi-Civita. No torsion. It is identically conserved. And it can also be decomposed, of course, as the energy momentum tensor. So you see there is a real parallel between these 2 objects which appear here. And now what we can do with this cotton tensor in a 4-dimensional bulk, 3-dimensional boundary, is, of course, the following thing. The first that I want to stress here is that the cotton tensor in 3 dimensions plays a little bit the role of the Weil, because there is no Weil in 3. The cotton measures whether the space is asymptotically, is conformally flat or not. I'm talking about the 3-dimensional space, which is here the boundary. So from the boundary perspective, is whether the boundary is conformally flat or not. And from the bulk perspective, is whether the bulk is asymptotically globally anti-de Sitter, this is when the cotton vanishes, and locally anti-de Sitter, this is when the cotton doesn't vanish. Now, we have two tensors, the cotton and the energy momentum tensor, and they are both conserved. Well, the cotton is always conserved, the energy momentum tensor is conserved on shell. With those, we can build two currents, and with the currents, we can build charges. And this is how the two sets of charges appear here from the boundary. These are the electric charges, which are built out of this energy momentum tensor, and those are the magnetic charges. Actually, these magnetic charges that are here constructed in this way from the boundary coincide precisely with the famous magnetic Komar charges. Those are the electric Komar charges. The first are conserved on shell, the former are conserved anytime. So, well, there is a deeper role, actually, of this cotton and a deeper relationship between the cotton and the energy momentum tensor. By setting a relation, a closer relation, which is here just given roughly, you introduce what is called a self-duality. And this, actually, self-duality is what allows to construct the integrable sector of Einstein's equations, where you can resum the series and find some closed form. But this is not the aim. So the important thing to remember is that the reason that these two tensors appear is because both appear in the asymptotic structure of the bulk Weil tensor, and this is the natural way that things come. Now, you may say this is all fine, but it is limited, because in anti-de Sitter, in three-dimensional boundary, this three-dimensional boundary, it has at most 10 conformal killing fields. So you cannot construct so many charges. This is extendable in Ricci flat space-time, and this is actually more interesting, because in that case, you construct an infinite tower of charges, and this is the very last part of the talk, which has no formulas. I just describe what is the output of the analysis. So I focus here in 4 dimensions, bulk, so 2 + 1 boundary, Carolian boundary, and now you try to reconstruct this bulk Ricci flat space-time out of boundary data, which are living on a 2 + 1 dimensional Carolian boundary. So these data are as follows. This is the list. Well, the first piece of data are the Carolian geometry, as we had the metric in the Riemannian case. This is the degenerate metric and the Ehresmann connection. This is 6. Next comes what, in quotation mark, replaces the relativistic fluid, and here is the Carolian fluid. But it has the same number of degrees of freedom. There is an energy density, and you have momenta. Then there is a velocity field, Carolian velocity field, the U, the previous U, will here translate in some other vector. And what comes next was absent in the anti-de Sitter. There is a Carolian dynamical shear. There was not such an object in the anti-de Sitter. And there is a further infinite number of Carolian data. At every 1/r order that you go, you need something new. In the anti-de Sitter case, everything was captured by the first one. Here, the deeper you want to enter, more data that you need to know. These are actually, this is a main difference between anti-de Sitter and flat, and between the dynamics of the boundary in the Carolian case and in the ADS case, Riemannian case. So the features that all these things obey are the following. Well, first of all, Weil invariance and Carolian covariance with respect to the boundary are clear. So this is, we have reached this goal that I have announced in the beginning. So there is a boundary Carolian fluid, and this comes with a bunch of momenta. These obey an equation, which is a conservation equation, but in this case it is not conserved because of the shear, the bulk shear, and this is due, this is due to the gravitational radiation, as opposed to the case of anti-de Sitter, this gravitational radiation that reaches the boundary and that makes that the fluid feels an external force. If this is absent, then there is conservation. Of course, the conformal Carolian group is always BMS4, And this coincides with the asymptotic symmetry group that we have in Ricci flat spacetimes in 4 dimensions. And there is a boundary Carolean cotton, so the relative of the Riemannian Carolean cotton, which actually comes in 2 copies. Now, why this is coming in 2 copies? This is because we usually expand in 1 over c squared. With c squared, the velocity of light goes to 0, and then there are several pieces that come. So there is a doubling of these degrees of freedom there. And the spin-off, this is the last, is that we are able in this way to recover infinite towers of charges, because you remember that the group of conformal isometries is infinite. We have infinite number of charges which come in the following way. Well, there is an electric tower, but those are conserved on shell, and not always. They are conserved in the absence of shear. If there is gravitational radiation from the bulk, these are not conserved. And there is also a condition. You remember in the Carolean case, not everything is systematically conserved. This comes from the fluid, but we have also the cotton, and the cotton brings a magnetic tower of charges. Again, these are conserved under some condition. And there is a self-dual tower of charges that comes from the doubling of the cotton. But that's not all. We have also an infinite number of towers, because remember that we have an infinite number of degrees of freedom that you need, and each of those things will bring its dynamics, which combined with the symmetry will give towers. So that's where, in particular, the famous Penrose charges, the ones that were found again by Godatzgar brothers and Pope, that's where those are sitting. And this is here constructed from a purely boundary perspective. This is the final comments, which I have split in 2 pieces, right? There are things which are facts, so that the n-dimensional Ricci flat bulk is related to n-1 dimensional Carolean boundary. These are facts, that we can reconstruct the bulk, but we need for that an infinite number of degrees of freedom from the boundary. We have towers of charges, which are associated with the Carolean isometries and the dynamics. And of course, in n equals 4, I have stressed that there is the cotton which plays a role, and the group which is BMS4. Now, this electric magnetic. So if we want to go a step further, you may now say, what's the hints for holography? Well, there is somehow an expected duality from flat 4 to conformal Carolean field theory in 3 dimensions. Well, I don't know if this is a local theory, because, as I said, you need an infinite number of degrees of freedom. And it certainly requires a Carolean conformal field theory, in particular in the quantum level, and this is somehow in limbo. We don't know how to construct these things. Now, there is, of course, an alternative approach, which I think should be stressed here, is this flat 4 CFT2, celestial holography. Well, this is mostly describing the scattering amplitudes. And it is mostly based on a subgroup of the BMS4. So whether this approach is a subsector of the one that I have advocated previously, and how this subsector could be obtained from first principles, starting from the first one, is still under discussion. Thank you.
Thank you very much. Maybe time for a couple of questions.
If you go to the single space, you can say that the cosmological horizon is the envelope of
in the case of de Sitter space, you see, you'll have a space-like in that case.
Sorry, you have?
A space-like surface. You know, K, in that case, the cosmological constant is positive, all right? So, so you will not, what will qualify for a boundary will not be a null surface, will be a space-like surface.
This is global.
This is global.
The question of
Yeah.
is the static patch.
Ah, the static patch. Okay, then, okay. No, well, presumably you may try to find, well, you have to analyze the limit and see whether, you know, I have not in mind any trick to reach this limit. I understand what you mean, but I cannot answer about the, well, let me put it differently. You can certainly formally repeat the reconstruction method, right? So this part can be done, but it has not been done to the level of accuracy that I have presented here. You can go through. Now, what you can conclude and what part of what I have said here will remain, I don't know.
Thank you for this very nice work and talk. If you include torsion, would you get, I mean, what would you get in your case with a boundary? I mean, where, of course, as you said, the Cotton tensor would not be conserved. Would you get something?
Okay.
I mean, you would break holography, or you know what I mean? That's
well, actually, let me answer as follows. You could ask the same question for anti-de Sitter, right? Because actually here, if you compare anti-de Sitter with flat, anti-de Sitter you have a Riemannian boundary, which is equipped with a Levi-Civita torsionless connection, and this, in the limit, naturally brings you to a similar connection for the Carolian. So you could, of course, introduce torsion in the first case, and then you will also have a connection with torsion in the Carolian. But maybe, so that's all. I'm just delivering whatever I know. I haven't really worked it out. Now, what I can say, as an addition to that, is that for Carolian geometries, there is not the idea of a unicity of a connection without torsion and metric compatible, as it is for Riemannian, is no longer true in Carolian. In Carolian, you have a much bigger spectrum of connections that you may consider. So I would never say that even without introducing the torsion, you may have even more freedom. So the one I presented here is the one that naturally appears when you solve bulk Einstein's equations.
Thank you.
Okay, I think we should thank Mario.
So, ladies and gentlemen, welcome to this afternoon session of the SUSY conference. Now, we have the pleasure of inviting Professor Miriam Svetic from Penn State, University of Pennsylvania. Sorry. Sorry, apologies. Who is going to, the editor of Physical Review D as well, all right, that compensates it. We are going to talk, she's going to give us a talk on gauge group topology and higher form structures in consistent quantum gravity.
Thank you.
My apologies again.
Do I need a microphone or?
I think if you speak,
okay, I'll speak loud.
try louder and try to show it.
Right.
Because if you go away, then I think the acoustic.
Okay, great. Well, thank you to the organizers for inviting me here. It's such a wonderful thing to come back to Ioannina. I believe it's for me the third time now. So it's a great pleasure to be here. So what I want to talk about is some progress we have made in more formal theory about understanding the origin of the topology of gauge groups in quantum field theories, the way it's connected to higher form symmetries. And what I'm going to talk about primarily is within the constructions that also include consistent quantum gravity. Well, we understand that quantum field theory that is coupled to consistent quantum gravity should be subject to some additional constraints that are beyond the standard quantum field theory anomaly cancellation constraints that we are dealing with. So identifying these additional constraints in consistent theory of gravity goes under the program of Swampland. On the other hand, as string theorists, we can construct globally consistent compactification of string theory, which of course automatically includes gravity as a quantum theory. And there, these constraints emerge due to actually geometry of compactified space. So natural question that one would like to ask, does string theory as such, as the only game in town as far as quantum gravity goes, really realizes all consistent theories of quantum gravity through these geometric constraints of compactified space? And this proposal goes under the name of string universality. As a card-carrying member of string community, I do believe that at some point we'll tie those things well enough to argue that string universality is really universality. Well, in this talk, I would like to focus actually on finding these additional physical conditions in consistent quantum gravity that somehow reflect the geometric conditions that we expect from string theory. But these physical conditions that reflect this geometry really don't necessarily have to rely on string theory per se. So this approach has by now quite a long history, and our effort at Penn is also part of trying to formulate these physical conditions that reflect geometry of consistent quantum gravity. So what I want to focus on in this talk is really highlighting the constraints that we get on gauge symmetry topology in consistent theory of gravity. That would be actually for minimal supergravity theory and in large dimensions, because that's where we can do things better. Okay? So that would be in A dimensions. Sorry, I'd love to talk about 4, but this is where we are. Okay. Right? And so we'll focus on these effects, how gauge symmetry topology actually emerges as gauging of one forum symmetry in this gauge theories with consistent gravity. Okay. As a byproduct, in this analysis, we also ended up with complete top-down classification of all 8D and actually connection to 9D n equal 1 supersymmetric string vacua by using the string junction methods, and not actually using, but refining some of the aspects of it. Okay. So again, a guiding principle in this approach would be first geometry. Well, geometry from string theory. Geometry, what one would say when we have a handle on large as a number of aspects of non-perturbative physics, which would go under the name of F-theory compactification. So that will be my crutch for geometric insights, okay? Well, the physics side I'm going to approach from the perspective that any global symmetries that we have in quantum field theory coupled to consistent gravity, including higher form symmetries, have to be gauged or broken. Okay? So this goes actually under the no global symmetry hypothesis, and it's expected to apply precisely also to higher form symmetries. Any questions? Yes?
When you say broken, you mean spontaneously or explicitly?
Broken at the level of the full spectrum of the theory. Could be massive spectrum, you may not see it, but broken. And that's the hard part in string theory, to know that. Okay? So this is a work based on a program we've been pursuing over the past 2 years or so, and was initiated about 2 years ago. It's together with Marcus Dirigal, who was visiting postdoc at Penn, now at LMU, Ling Lin, who was postdoc at Penn, now at CERN, soon to be at Oxford, and Hao Zhang, who is a student at Penn, working closely with Jonathan Heckman and myself. So those works are all in this quartet. And so what I want to highlight is 2 aspects of it. First, how we initiated really the gauging of one-form symmetries that would constrain tremendously the global group structure of a-dimensional n equal 1 supergravities. We advanced some of this more top-down approaches in string M and F theory, also direct construction of so-called CHA, Chaduri-Hockney-Leaken vacua in 8 dimensions. And the last work, where actually we covered all bases by using string junctions in top-down constructions. And so those are the 2 aspects I want to highlight here. Okay. Right. Well, I mentioned for the geometrical perspective, I'm going to use a crutch of F-theory compactification. So I have 1 slide where I'm going to say a few key things about that. Okay? So first of all, F-theory is considered as a powerful framework where we are geometrizing the S-duality symmetry of the axiodilaton field in type 2B language by making it part of geometry. So axiodilaton field is modular parameter of 2 torus. So 2 torus plays a crucial role in those constructions. And so when we are talking about F-theory compactification, we are compactifying on elliptically torus fibered Calabi-Yau spaces. So in 2 dimensions higher that we would naively mean because we are attaching the 2 torus to this construction. Okay? So these spaces are in general singular, but they result in lower dimensional supersymmetric theories where gauge degrees of freedom are associated with the type of singularities we encounter in these elliptic fibrations. In particular, the gauge symmetry, non-abelian gauge symmetries associated with PQ7 branes, non-perturbative 7 branes in this context, are associated with the type of degeneration of this fibration along a divisor in the base. And this type of degenerations were classified in terms of ADE singularities, and they produce, in effective theory, precisely the gauge symmetries associated with the ADE gauge groups. Okay. Furthermore, the abelian nature of gauge symmetry in F theory is a bit different. It's actually associated with arithmetic structure of two torus. In particular, it's associated with the so-called Mordé-Weil group of rational points on two torus. In vibration, that would be rational sections. So the rational sections of this Mordé-Weil group in elliptic vibration signifies the appearance of abelian gauge symmetries. So the divisors associated with U1 are actually Poincare dual divisors of these rational sections. Another important geometrical property of F-theory compactification is that torsional points, torsional sections in vibrations actually tell us something about gauge group topology, which is focused on my talk. Okay? So the type of torsion that we have will determine what is the global gauge group topology. Okay? So this is sort of fast geometric side. Well, I can't help myself because, and that also would justify sort of my talk here at SUSY. We can use F-theory compactification to construct four-dimensional n=1 supersymmetric vacua by employing geometry of elliptically fibered fourfolds. So this is torus over 6 dimensions. Everything is complex, so it's 4 complex dimensions, right? And a particular choice of this elliptic vibration that one can choose actually with toric technique. Oops, this is not, I think the battery has gone. I think. Okay. So produced actually, no, I'm not interested in, I'm interested in pointing, yeah. Okay, yeah. So in any case, it produced precisely the singularity structure that has the SU3 cross SU2 non-abelian gauge symmetry and the Mordé-Weil rank 2 rational sections that produce U1 gauge symmetry. Furthermore, there is a, yeah.
Can put this?
Thank you. There is a global topology that is also geometric in nature, and it turns out that in these constructions, the global gauge group topology is modified out by Z6. And that's also related how we map these rational point sections onto physical divisors of physical U1s, and that produce constraints, again, geometrical on the global structure. So it's somewhat intriguing that even in 4 dimensions, we get these geometric insights. Now, choosing the 3 complex dimensional base in this elliptic vibration to be toric and using Skarke-Kreutzer classification of the toric bases produce for us unprecedented number of globally consistent models with precisely this gauge group symmetry, precisely 3 families of chiral families, and when we chose the gauge divisors to be on anti-canonical divisors of the base, got precise gauge group unification. So this is an unprecedented number of consistent constructions due to power of toric techniques. But what is at the end right now crucial and we are struggling with is to determine the exact matter spectrum, not just the chiral spectrum in the theory, including the number of Higgs pairs. And that involves much more involved studies of the so-called bundles restricted to the curve. In our case, everything is anti-canonical divisors with, that play a role, and the bundles that determine the number of matter fields, exact matter fields, turn out to be proportional to, associated with the bundle that is some fractional number power of anti-canonical divisor restricted to the curve. We refer to such bundles as root bundles. And those are very hard to study, okay? But we managed to actually analyze all such root bundles in a special limit, okay? of the so-called nodal deformation of matter curves. We change complex structure in this construction so that matter curves become nodal, and there mathematicians taught us how to construct those root bundles precisely. So, for example, in particular, we developed algorithm to determine the full number of, for example, quarks, and by chirality also the number of antiquarks on particular nodal matter curves. And for this particular polytope that has many triangulations, namely many non-equivalent bases associated with this polytope structure, we actually got huge number of root bundles that have precisely H03, exactly 3 number of, say, left-handed quarks and no vector pairs, because chirality is 3, okay? We also see a statistical analysis of such root bundles for other polytopes is more involved, but we see really major prevalence of examples where those quark matter curves have precisely 3 numbers of matter fields and no vector pairs. Study of Higgs nodal curves is more involved, and we want 1 vector pair to get MSSM, hard stuff. So now it took too much time to go that way, and now I have to go to my core point, but it was still the advertisement that there is serious effort in string theory to connect string theory to particle physics and technical advances there. Anyway, let me now focus on the key part that I wanted to tell you about, which is talking about gauge group topology in 8 dimensions. And let's start first from geometry, string compactification. Okay? So we want to identify whether the theory has the property that the gauge group has topology, non-trivial topology or not, namely that there is non-trivial discrete Z that sits in the center of the gauge group that determines the total topology of the gauge group. So for simplicity, let me take an example when I'm dealing with the product of unitary factors. So this would be just SUN for the case of describing a prototype. There, the center is, of course, product of the corresponding ZNIs for each SUNI. And I'm trying to look at the possibility of having a global topology associated with the Z that sits inside this center and is represented by these generators, integers Ki's that sit inside ZNIs. Okay? Now, I already told you that actually in string theory, in particular in F theory, I will be now doing construction of F theory, and this compactification of F theory, the Z, the global structure, would be encoded in the geometry, namely in the so-called Mordell-Weil torsion. Okay? So I'm in 8 dimensions, I'm doing F theory and elliptically fiber K3, right? Calabi-Yau twofold, leading to 8-dimensional n equal 1 supergravity. And there, the analysis of Mordell-Weil torsion can be done very explicitly, and obtaining this explicit arithmetic constraint that having compactification with that type of gauge group, the global structure is actually determined by Z that satisfies this particular constraint. So this combination of these generators that sit inside ZIs and determine Z, and the NIs of each SUNI have to satisfy this constraint. Okay? So this is geometry, and in K3 it can be done through arithmetic methods, and looks beautiful. And we were staring at this expression and tried to see how can we do that now from physics side. Okay? So from physics side, it was realized that actually the global gauge group structure of that type is associated with gauged one-form symmetry. Okay? Now, we know that if we have this gauged one-form symmetry, there could be anomalies. So we have to identify actually constraints, okay? Or make sure that there are no anomaly obstructions to gauging this global one-form symmetry. That would make the theory really consistent with the no global symmetry conjecture, okay? In any case, so for a gauge group G in general, there is the so-called fractional instantons that could be parameterized in terms of a one-form symmetry background field. This is two-form field potential that is discrete valued, okay? And it's a generator of one-form symmetry. It acts, it transforms F in through this transformation. And if we evaluate those instantons, we would get some fractional number times the so-called Pontryagin square of the C2 field, which is typically an integer value. Okay. Now for SUN gauge groups, the contribution of this one-form field to the instanton density has this fractional prefactor of that type for SUN. Doesn't that ring a bell? Okay? So what we went to then is realizing that in n=1 supergravity, we also have an important term in supergravity theory that couples a tensor field before in gravity multiplet that has a large U1 symmetry to field strength. So that is a term in supergravity, Lagrangian, that involves F square, where the one-form symmetry produces this fractional pieces, okay? But before also has this large U1 symmetry. So what we were able to show is that this term is responsible for anomalies, okay? So it should not contribute with a phase in path integral once we perform a mix, large U1 transformation and one-form transformation. So for the prototype example I show you, product of SUNI groups, the center symmetry generated by KIs, we would get this contribution from this term that would be of that form. This fractional p's, the rest are integer, and KIs for each SUNI. And this combination is of that form, and it has to be integer, because that would really remove the local anomaly, right? The mixed anomaly that we are dealing with, so this has to be the integer. So we got from one-form symmetry and insisting that there are no anomalies due to gauging of one-form symmetry in this case, okay? We got this condition, but that's the same condition which I just showed you from geometry. So physics gave us that, and geometry gave us that, and it's a perfect agreement, okay? So the...
Is this like an index theorem in a sense? Or?
Well, it's hard to say, right? Yeah. I mean, this is it's really, in the spirit, it is a generalized notion of anomaly effects. In any case, my time is ticking, so let me go on. I may not cover all the things I wanted to tell you about. So this condition of having no anomalies, mixed anomalies due to gauging of one-form symmetries in AD supergravity really constrains very much the allowed global symmetries. Okay? So for example, if we are looking for product of SUNIs, my prototype, and looking at rank 18 gauge groups, these are independent constraints that fix the allowed ranks of gauge groups, but now we are on a global structure, right, topology. So this constraint turns out for ranked 18 gauge SUNI products to be quite constraining. For example, if we are talking at ZL global constraint, for L bigger than 8, there are no anomaly-free solutions. For L7, we get only limited ones, and so on. So it's quite constraining, okay? We can also, there are other possibilities of the rank of gauge groups in 8 dimensions, like rank 10 and rank 2, for example, and then we confirm that actually all those string compactifications that have this rank 10 and rank 2 global structure of certain types are precisely compatible with gauging of one-form symmetries. Okay. Last but not least, we were actually able to advance string junction techniques and get all the D=8 string vacua and their global structure, including those rank 2 that nobody else could do before. So that's the first work on that. Since my time is ticking, and I had a whole section on string junctions. How this work? Unfortunately, I don't think I can say too much, because this long digression, cannot be long. Okay, so so maybe I should just say in few words that actually using string junctions, which are actually strings that stretch between PQ branes, which are in this perpendicular directions. They are just points in internal two-dimensional space, okay, are actually precisely modeling the geometry of the corresponding two cycles in F-theory description. And so we see that we have the type of strings that stretch between the 7 brane stacks. They basically, they quantify the roots of the corresponding gauge algebra lattice in this case. And then we have another set of strings that go to asymptotic direction. They just have, in principle, attachment to one stack. And these external junctions with external asymptotic products actually quantify the corresponding weights that are there in this gauge lattice constructions. There's an analogous story with the dual magnetic fibranes, and it's really, in particular, talking about these weights that are non-compact, that stretch to asymptotics, and the corresponding co-roots that are between branes. So modding out by compact two cycles, the non-compact ones, that really turns out to be shown to correspond to determine the corresponding global symmetry of the gauge group. That's actually work that initiated a lot of effort using this two-cycle analogy. Okay. So we are using precisely this map here, and our important construction is with this non-root junctions, those that carry the weights that go to asymptotics, and they can be described in terms of the part that encodes directly the weight part and the so-called loop junction. So the fractional weights in the weight junctions are related to the properties of this extended weight of the loop junctions, and we call those loop junctions fractional loop junctions because of the fractional coefficients, and then we use in constructing from this local non-root junction also now the full compact construction of allowed string junctions, namely by insisting that these junctions in asymptotics have no leftover charge, so no asymptotic PQ charge. This gluing of local loop junctions into resulting one. Fractional null junction actually is associated now just with magnetic side of these constructions, and then that's the one that encodes the global property of the gauge group. Total gauge group inconsistent construction. And so we were able to see that for rank 8 vacua and find all the constructions. They match perfectly with the corresponding heterotic constructions. But we also went beyond F-theory. We were also including orientifold planes of the so-called frozen singularities, 07 plots, yes. And when we included that, those are the so-called non-trivial frozen 7 branes that have the same ordering of SO16, but expected to have some non-trivial flux on them that would freeze them. So we replace the stacks of branes there in the construction of rank 18, now with 07 frozen guys that gave us rank 10, and with 2 07 planes rank 2. Some further constraints, and actually we got both. With just insertion also of positive oriented 07 planes, we got all the global structure of rank 10 and also new things. These things were found also by some dualities, but this one is the first one. Okay. No time. We also found how this construction can reach the boundary of moduli space in the decompactifications, and we found actually all the 9-dimensional uplifts that have some no time. But the point is, in particular, nobody has understood this 9D uplift of 2 O-planes in particular, and how this disconnected solutions in 9D, now that we understand how they are really connected in modular space through D equal 8. Okay. I am at 0 minutes, so I actually did not want to say any more things, except that actually there is effort to understand the role of mixed one-form gauge anomalies also in lower dimensions. Also, I already highlighted the top-down constructions themselves in 8 dimensions, also ties to 7 dimensions. Important work on understanding its role also in 6 dimensions. And also, this is a subject that on its own is very important just in non-compact example of superconformal CFTs by themselves. So there's term that causes anomaly in supergravity actually can be viewed as being put in this generalized SCFT theory and should play an important role there. So what I have shown you is that actually, yeah, all the punchlines are gone. So in any case, so I hope I gave you some feeling about the progress we have made in understanding from bottom up how gauging of higher-form symmetries actually fixes gauge group topology and how tremendously constrained a-dimensional supersymmetric vacua coupled to quantum field theory. On the other hand, we use all the technology of string theory, including the string junction part that I tried to just give you a glimpse of, that completely fixes all the 8 non-perturbative n=1 supersymmetric string vacua, and this tying to gauging of one-form symmetry actually turns out to be in 1-to-1 perfect agreement. Well, I focus on AD. I said there is some work in lower dimensions, but there is one other topical subject that actually the structures, one-form symmetries that I focused on, can be enhanced by higher form symmetries, or more recently also the interplay of zero-form discrete value symmetry and one-form symmetries that in some cases produce a new type, not trivial, two-group structures. Very hot subject in formal theory, but our group actually, that's with Jonathan Heckman, Max Hübner, also at Penn, and student at Penn, Ethan Taurus, managed to shed light on the origin of such higher group structure by using geometrical constructions on non-compact spaces, so actually relevant for SCFT. So geometric origin was really clarified in this context, and we are working hard to see what remains there from those structures as we go to compact spaces and start including quantum gravity. Thank you.
Thank you very much. Now, questions and comments, please. Yes.
Ioannina, thanks for a nice talk. And I've, precisely in the setup of minimal supergravity supersymmetry in 8 dimensions, you can have also construction with symplectic groups.
Yes, those are the one with 07 plus.
Yes, precisely. So you, maybe I missed, you have something to say also on the...
We constructed all of them.
Okay.
It's in the appendix B of this paper, and it's on a few pages.
Okay.
All of them. Okay. It's not rank only, it's not a group only, Rayleigh algebra. It's actually the whole global aspect that we focused on that is encoded in this fractional loop junctions. Anyway,
but in that case, you need junctions? No, because symplectic...
No, you can use CHL constructions,
okay.
Right? And that's also Anna Maria Font et al. Also related effort. We just have quantified it there. Okay. Now with 207 plus, nobody has done, then you have only rank 2 here, there, right? And there is not much of the structure, but it's very detailed now. And you don't have dualities to do that.
Thank you.
Other questions? Don't say that. I have one question.
Okay.
I've seen that in your classification, of the 10 to the 11 vacua, you excluded exotic vector like...
to high percentage.
To a high percentage.
Very, very, very high. I didn't go, again, no technicalities.
Because these could have some experimental signatures, am I right? So
yeah, to us it was really surprising. That you see, one hopes, okay, maybe generically, yeah, you have this, but actually we found, irrespective of how we tune complex structure, such huge percentage of no exotics.
That's impressive.
Yeah.
That's impressive.
This to us was quite,
That's really nice.
Yeah.
Okay, well, if there are no further questions, let's thank Miriam again.
Thank you.
And let me invite Professor Emilian Dudas. So who is going to talk to us about causality in nonlinear supersymmetry and inflation?
So the pointer is here. This one. Okay, thank you. Okay, and to change
this.
Yes. So. Okay. First of all, I'm very grateful for the invitation to come back here. I was also, like a lot of other people, here in 2015, and it's very nice to see in person again after all these complicated years. So the paper I'm talking about today... Now? Sorry. So this work is based on a paper which appeared yesterday on the archive in collaboration with former student Quentin Bonfoy and my current PhD student. Quentin, who is in DAISY, will go to Berkeley in the fall, and Gabriele Casagrande, who is a new PhD student in École Polytechnique. And it's also based on a paper which you wrote last year with Keith Olive and Marcos Garcia, Mambrini, and Marco Pelosa, and Saunas Werner, but will be mostly about the first paper which appeared yesterday. So, and the subject is causality and nonlinear supersymmetry in inflation, and there is some relation, as you'll see, with the talk of Karim this morning. I didn't know that there were some connections before prepare my talk, but there'll be at least the historical part, there is some overlap in historical part. So that's my plan. I first of all talk about a story which actually Karim already described, the spin 3/2. I'll not be interested in coupling to electromagnetic field like him, but still there is a history about problems how to deal with spin 3/2. And then I'll discuss about specific problems which were discussed from a certain point of view last year. And I were adding here a new viewpoint on these problems of the gravitino sound speed. And we relate some of these problems to causality and positivity bounds. And I'll end up with proposing some minimal model of inflation supergravity, minimal you'll see in which sense, which are free of all these potential problems. And I'll add to some perspectives. So first of all, something which I think I can go very fast. As you know, supergravity is supersymmetry plus gravity. And we have the gravity multiplet, and the hero is the gravitino. Rita Schwinger spin 3/2, as Karim discussed in detail, and Dieter also discussed this in detail, and various matter fields. And for us, we'll be concerned today mostly with some scalar fields, which could be inflatons, or could be some fields which have time dependence. But just to be specific, I'll be interested in some scalar field which will be inflaton. Now, as we all know, in supergravity, the gravitino becomes massive when we break supersymmetry by absorbing the Goldstino. And the Goldstino, therefore, provides the helicity plus or 1/2, and the gravitino provides the helicity plus or minus 3/2, and that's the massive gravitino. And that's the super Higgs mechanism. And now, this I could skip because Karim discussed in some detail, but let me just remind you very briefly the story. So the consistency of the low energy actions for spin-3 half Raytasch-Wingers has a long history. First of all, after Raytasch-Wingers in '69, Velos-Wanziger pointed out, as Karim described, a potential acausal propagation for a charged gravitino and in electromagnetic background. Then when the supergravity was invented in '76, immediately afterwards, Deser and Zumino proved that gravitino propagation minimum supergravity is causal. And much, much later, Deser and Waldron, and Karim talked about this paper, proved that gravitino propagation in gauge supergravities is causal. So the upshot here is that, and then last years or various recent works about the gravitino, one of them that you heard about from Dieter, gravitino mass conjecture, and some things that I'll introduce later on, it doesn't matter the name. The upshot of this history is that you have to be careful when you deal with the spin-3 half field. And the safe way to deal with such a spin-3 half Raytasch-Wingers field is to use supergravity. But if you want to have something to take home from this is that standard supergravities have no problems. Standard supergravities are free of these problems. Even if there is no formal proof, we believe the standard supergravities have no problems of this type I'll discuss, which will be essentially a causality. But when you start to do, for example, nonlinear realizations, and that's what I'll talk about today, you have to be careful. This will be, if you want, the upshot. You have to be careful when you do nonlinear realizations. You can have a causal features, and I'll discuss a little bit what's happening. So as I said, the history strongly suggests that usual supergravities have no problems. And what I mean by standard usual supergravities is the linear realizations, which have the same number of bosons and fermions. And what I'll be mostly concerned today will be nonlinear realization in which number of bosons and fermions are different. Why we are interested in these models, for example, in the context of supergravity, one of the interesting features of such models is that we can have minimal models. You want to get rid of some scalars because you want just one real scalar to be in the inflaton. You want to get rid of some partner of the inflaton because it creates some problems in the evolution of the universe and production of gravitinos. So you can actually eliminate to have fewer and fewer fields. And it's even possible to construct minimal models, which are still supergravity models, in which the only physical degrees of freedom are graviton, massive gravitino, and an inflaton, which is a real scalar. Of course, this cannot be standard supergravity because the number of bosons and fermions do not match. So this has to be nonlinear realization. And this will be the subject if you want. But what I'm going to say today will be more general. I have inflation as an application in mind. I'll come back to it in the very end. What I was saying today is a bit more general. So just to give you an example, the simplest nonlinear realization was invented, the first nonlinear realization is Volkov-Akulov seminal paper in '73, but the simplest for formalists to use nonlinear realization, in my opinion, is so-called constrained superfields, just because you are using the standard superfield approach, and you just impose some constraints on a superfield. Probably the simplest and well-known example is was proposed by Rocek in '78. You just have a Lagrangian, which is like this. If you want a Polony like Lagrangian, which would be a purely free theory, completely boring and uninteresting if you are doing it as a linearization supersymmetry, but you impose such a constraint, s squared equal to 0. In superfield, this does not imply s equals 0, like for a usual function. It gives this solution here, which means that the scalar, which you call Golstino, the partner of the Golstino, this G object here will always be Golstino in my talk, is eliminated by the constraint. Eliminated means that if you want in the ultraviolet, you had a very, very heavy mass, like in the nonlinear sigma model. You start from a linear sigma model, you impose a constraint, phi square equal to 1, you eliminate, if you remember, the Higgs-like, and you are left over is Goldstone boson. So I think everybody knows how to go from the linear to nonlinear sigma model. And this example here is the supersymmetric analog of this. And this turns out to be equivalent to a highly nonlinear Volkov-Akulov model, even if you started with a such a simple Lagrangian. So that's the simplest example of a constrained superfield method to construct nonlinear Lagrangians. This object will appear in what follows all the time, and it contains the Gostino. We can call it Gostino superfield if you want. Now, the main point I'll try to discuss is the Gravitino sound speed. So the Gravitino, the Gravitino has a certain propagation, for example, again, if you have inflation or more general time-dependent solutions, and the Gravitino sound speed, which I'll define in a minute, has to have values between 0 and 1. And recently, two problematic behaviors were discussed in the literature, starting with this paper in 2017. People realized that the sound speed can become 0 at particular points on the inflationary trajectory. And this will will generate a large catastrophic production of Gravitino. And this is all discussed in several papers. This one's here. Also in the paper I mentioned with Keith Sullivan, by paper by Ignatios, Karim, and a third collaborator. I'll not really be interested in this problem today. This led to so-called Swampland Gravitino Swampland conjecture by these people. I'll be mostly concerned by something else, which is a bit more esoteric, which is you can have acausal behavior. So if this sound speed to 0 and this large production of gravitinos is debatable, and I'll not discuss today, but it's debatable if it's really a consistency problem or not. It could be just a phenomenological problem, large back reaction, things like that. This one, it's inconsistency of the theory. And the question, how comes that theory like supergravity can become inconsistent like this, just out of the blue? So we realized, and again in this paper with Keith, that we can have a causal behavior at particular points on the inflation trajectory in very specific supergravity models. And I'll try to argue these very specific supergravity models. You have to understand the origin of such potential problems. So the sound speed is defined like this. The frequency, if you want, of a mode as a function of the momentum. A is the scale factor here. You are in FRW background. And it turns out that the transverse components of the Gravitino always propagate with the speed of light, but the longitudinal components can have various sound speeds. It can be propagated slowly, and this was, I think, proposed, as far as I know, by Karim with Luc Darmen and Yaron Oz some time ago. But what I'll be again interested in today will not be this one problem, but the fact that for some particular, very particular nonlinear supergravity models, you can even go beyond. So speed of light, you can get acausality, and that's very puzzling. Again, I remind you that in standard supergravity, we believe this is not possible. So I not insist on this, but every time you see a sound speed, the logic is very similar. You compute the pressure and the energy density in a supergravity model. It's very simple to compute. You compute the gravitino mass in this supergravity model, the time derivative, and that's a formula which is relatively easy to derive starting from the equation of motion of the gravitino in supergravity. This is the supergravity formula, so it's very easy to compute the sound speed for the longitudinal component. For the transverse, it's always 1. Now, if you work a little bit, you'll find that explicit formula in supergravity with some one or two technical assumptions, which I'll skip here because they are irrelevant. For me, it will be true. Everything, this formula will be exact for what I'm going to discuss in what follows. You can write in a very compact form like this using a certain compact notation here. So you contract, you have a kind of scalar product with a scalar metric if you want. So this is the full supergravity expression. And actually, what's nice about this formula is that this is valid, first of all, in standard supergravities. It's not valid for these nonlinear versions that I'll discuss later on. For nonlinear versions, I have to use this more general formula here. This is a bit more general, actually. This is completely general. This is valid for the standard supergravities. And then from this formula, if you remember the Cauchy-Schwarz inequality, you can see that all the standard supergravities, the causality is respected. But I'll not discuss. There are one important assumption here, which I skip here. So it's not a full proof, but let's say for inflation, one field inflation, this is a full proof. One field inflation, this is a full proof. The standard supergravities have absolutely no causality problem. And for the large majority of supergravity model we investigated, this was in the past, this paper with Keith, we found no problem. Sound speed is between 0 and 1. And the only problems, that's why I'll be interested in what follows, the only problems we found is what people call in the literature minimal model inflation. You impose some constraints which eliminate, so you have this Golstino multiplet which contains just the Golstino physically speaking. You add a chiral multiplet which you can call inflaton multiplet, but to impose a constraint such that only one real scalar is physical and the rest are unphysical. The imaginary scalar is removed, it's unphysical. The inflatino is unphysical. And actually what's something very strange, so even the auxiliary field is determined by the constraint. That's something very strange. We know what it means to eliminate a scalar. It's very heavy. Eliminating a fermion means it's very heavy. What it means to eliminating the auxiliary field is not very clear. And I'll try to argue that the problem could come from this very peculiar feature of this, it's called orthogonal constraint. So as I said in particular, even the auxiliary field is not given by the usual expression supergravity that you are familiar, but it's completely determined by the constraint. It is just fermion bilinears. Now, what are the consequences of this orthogonal constraint? First of all, there is no inflatino, because the inflatino is removed by the constraint. And in this case, you can have this problem of sound speed equal to 0. And again, we'll not discuss this problem today. What I'll be interested in is this Cauchy-Schwarz argument is not true, and we found really examples with sound speed larger than 1. On the other hand, as I already mentioned in our last year paper, in this case, the orthogonal constraint, the UV origin is not clear. We tried a long time ago with Gianguido Dall'Agata and Farrakos to find the ultraviolet Lagrangian. What I mean here by ultraviolet, it means the two derivative supergravity Lagrangian. If we start from two derivative supergravity Lagrangian, we are not able to find in the infrared this orthogonal constraint. So this is rings some bells that probably something is strange with this constraint. And as you see here, we'll have another viewpoint. But before coming to this is a pathological behavior. Now, talking about the swampland program, it's probably, I don't really need to mention the swampland, it's just inconsistency. CS bigger than 1, I don't need to invoke swampland. Maybe this one we can talk about sound speed 0, but bigger than 1 is just an inconsistency, strictly speaking. Now, so the new viewpoint we give on this paper yesterday is that the potential causal behavior, again, as I said, concerns the longitudinal component of the gravitino. And as we know very well, from the gravitino equivalence theorem, at high energy gravitino, longitudinal component is described by the Golstino. And since the problem was for this gravitino, it means that we should be able to understand at least in the decoupling limit, Planck to infinity, the problems we encountered in a low energy Lagrangian describing just Golstino. In other words, not supergravity, but Golstino Lagrangians. And it turns out that the answer is yes. And the framework is the following. The Lagrangian for this orthogonal constraint. So if you write this chiral superfield, which contains only the inflaton, as I said, the degrees of freedom as the real and imaginary parts, so these are still superfields, you can write something which is a Keller potential. S is this Golstino superfield. And again, A, B are real imaginary parts of this inflaton superfield. This is superpotential, contains two functions, f and g. And again, the question is, can you understand this acausality, or is acausality captured by the low energy Lagrangian of the Golstino in the decoupling limit where mass Planck goes to infinity? This is the question. And the answer is yes. Now, the answer has several steps. And let me talk only about this constraint, and then I make some comments at the very end about more general cases. The answer is yes. If you write the Golstino Lagrangian, and if you manipulate it a little bit, you realize that after some Fourier definitions, for example, that's the simplest way to see the problem. After some Fourier definitions, you can find the higher derivative operators. This field phi, it's a scalar. Let's call it the inflaton. But again, the problem is more general. Let's call it the inflaton, couples to the kinetic term of the Golstino, if you want, with some functions depending on this f, g, and h, which are the functions which were appearing in the Keller potential and the superpotential. Now, an operator like this is known from the dispersion relations from the 60s that it has to have a precise sign in front of this operator. With my conventions, this has to be positive, actually. Now, strictly speaking, the dispersion arguments, the positivity constraints, if you want, so give something like that. And now if you compute the sound speed from the formula I gave you before, this is precisely implies that the sound speed should be less than 1. Now, the question, so the first comment is that the positivity constraints, strictly speaking, only are valid in the ground state. Dispersion rates are valid really if you are at the minimum of the potential. Here, it is obvious, first of all, from the supergravity point of view, we saw it just looking at the solutions during inflation. So during the whole inflationary trajectory, this sound speed should be less than 1. So it should be, so the supergravity condition is stronger actually than the just the positivity constraint. And actually, probably even in the low energy theory, you can understand if you just look for time-dependent solutions, for a speed of this object phi dot as small as you want, the sign of this should be positive. So you don't really need the inflation or supergravity. You can see it also here. Now, the issue, we believe, arises to the peculiarity of this constraint that you are eliminating the auxiliary field. And actually, so this I already said, you can see this either from inflation and the conditions for inflation, the supergravity condition is stronger because this operator has to be positive during the whole time evolution, and probably you can also see it from the Agostino point of view. The fact that the causality condition, so again, for me, just to be clear, the fact that you have a non-trivial condition means that something is not completely right. If you start with the two-derivative theory, and if you just integrate out some massive particles, you don't find any causality condition. It's automatic. So this means that something is strange here. And actually, one way to check that something is strange is the following. We showed in this paper with Zalagat and Farakos that actually this orthogonal constraint is reducible in the sense it's equivalent to 3 different constraints. One which eliminates a scalar, one eliminates a fermion, and one which eliminates the auxiliary field. It's really a reducible constraint, and we propose a constraint which always eliminates just one component. So this eliminates only a scalar, only a fermion, only auxiliary field. So what we are proposing, and we have several proposals, but one of them is just to use these 2 constraints here. So if you impose just these 2 constraints, you have the same minimal spectrum for inflation, still a graviton, massive gravitino, the inflaton, but the auxiliary field is you don't touch the auxiliary field. You don't impose any constraint on it. Now, if you work out the same Lagrangian that you wrote before for Agostino, you realize that the coefficient of this operator is just positive definite for any effective Lagrangian you want, always positive definite. And therefore, the problem comes from this elimination of auxiliary field. There is an alternative approach that I'll not describe here, which we believe is completely equivalent, in which you start from a Lagrangian, you enforce the use of the orthogonal constraint, but you have to start from the very beginning from a higher derivative Lagrangian. So you can use the orthogonal constraint in the original form, but you have to add some specific higher derivative operators already microscopically. What you find is completely equivalent to the approach I'm giving you here. I don't have the time to discuss why. What's the difference between, let's say, using this orthogonal constraint that people used relatively extensively for inflation and our alternative approach? In the orthogonal constraint, as I said, the auxiliary field of the inflaton did not appear in the scalar potential. So you have just the auxiliary field of the Agostino and the usual minus 3w squared in supergravity. For us, this potential is the usual superpotential, the usual scalar potential supergravity. It's the standard one. And therefore, the models are slightly different. I'm not insisting on inflation models. So the models are different not only in the details of all the couplings, but even in the scalar potential, the models are different. Now, so the conclusions are the following. It's important, I think, indeed, to impose these conditions. Sometimes, I believe that having subluminality, I believe it's automatic and usual supergravities. When you start to have nonlinear realization, it's as if supersymmetry, it's in some sense, part of it is lost in some sense. It's a bit like in usual low energy supersymmetry. You don't talk about nonlinear supersymmetry to address the hierarchy problem because you don't cancel quadratic divergences. Here also, it seems that nonlinear realizations, there are some restrictions. For most of the constraints, there is no problem. For example, for this Golstino constraint as the square equal to 0, there is no problem. The only problems we found are for constraints that eliminate auxiliary fields. That's the only problems. And we looked at the other constraints like this. And indeed, every time the auxiliary field was eliminated, there was a non-trivial causality conditions we found. But all the time you can propose an alternative which has absolutely no causality problem whatsoever. Another thing that I wanted to say is that in the case of the orthogonal constraint, the sound speed in the Golstino version, low energy and supergravity were exactly the same. Supergravity didn't add any 1/m Planck corrections to the low energy. In this case, there is an exact relation. In other examples, the supergravity contains 1/m Planck operators in the sound speed, whereas in the Golstino there are obviously no such operators. In this case, it's interesting because it means that if you apply against these positivity constraints, you could violate a little bit the positivity constraint, but with terms which are 1/m Planck squared. And interestingly enough, things like that were discussed in the recent couple of years in the literature. People know that in gravity you could allow a little bit of causality breaking just because of the time delay in gravity, which forbids really to violate causality. Here we see it just by comparing sound speed in Golstino, low energy, and supergravity. So the conditions coming from sound speed are stronger than just positivity constraints. And by the way, the positivity constraints, you can see it in the standard way by looking at the amplitudes. So you can just look at the amplitudes, Golstino, Golstino, Golstino scalar. You can apply standard techniques of amplitudes to see this positivity constraint. But supergravity condition or the sound speed of Golstino are stronger because it also applies to time-dependent backgrounds. We propose alternative models which have no causality issues whatsoever. So for any effective Lagrangians, there is no non-trivial condition which you have to impose. And my general interest, if you want more general, is inflation is of course one possible application, but I think that you have to be careful with non-linearizations from this point of view, just because it is known, as Karim described this morning, that spin 3/2 is tricky. So if you just do an arbitrary non-linearization, you can have problems. And also from my personal interest, I'm also interested to see how these things fit with the model with strings with broken supersymmetry, in which you break supersymmetry, for example, the string scale, and then you have a setup which is similar to these Lagrangians, which if you want, superpartners are not there. You don't have an order parameter. Thank you.
Thank you very much. Questions? Yes.
I have a question because this discussion about gravitino, inflatino, this has already been discussed 20 years ago in a question. I think you should not use these nonlinear models for inflation because they might be wrong. Because the point is, in typically Volkov-Avrulov, you should understand as a low energy effective theory, you have integrated out some fields.
Yes.
And that's in all these cases. You integrate some fields, and these fields, of course, in the high energy effective theory, they appear in the potential. Mm-hmm. If you now use a nonlinear realization, you define what is the field.
Yes.
And if this is inconsistent with the potential in higher energies, then you get some inconsistency.
Yeah.
I think the point is you should not use this nonlinear realization in this way in order to do explicit calculation.
Okay, I have mixed feelings, yes and no. No, in the sense that we had a discussion 8 years ago on this, and you remember probably this class of models proposed by the Lagrange-Wiener, in which the gravitino mass during inflation was way, way, way higher than the gravitino mass in the vacuum. It's true that you have to be, when you impose a constraint, you have to check that the superpartners to decouple are really very, very heavy, also not in the vacuum, but also during the whole inflationary trajectory, for example. And this is indeed not easy, but it's possible to realize for some models. For example, when we decouple scalar for this Golstino-less model inflation, this you can do. Now, if you can do this, for example, for this orthogonal constraint, I also have some doubts that we can discuss. Maybe in this case, I would agree with you, but it depends, I think.
No, I think it does not necessarily go wrong, but it can go wrong.
It can go wrong. It can go wrong, absolutely. You have to check that these fields are heavy all the time. Yes, yes,
but what if you were doing, because I had long discussions with Renata Kalos on that in 2014.
Yes,
actually.
yes,
we had this discussion here when we had been here in 2015, that in some way, I guess,
but I was
take
here.
a supergravity model, take a supergravity model and just integrate out fields if you like, but first define from your potential what actually is the Goldstino. Because from the potential you have a Goldstino, but then you integrate out something where this Goldstino is included, then you might get problems.
There are various issues. This is one issue which I think was addressed to some extent. There are other issues like the unitarity scale when the theory loses unity. There are various issues, I agree with you. But what we address here is that even if supposing that all this is fine, then you still have to be careful about problems like of this type, yeah. So I agree.
Other questions?
It's a very related question, which I didn't understand. Can you find a model in which the starting from standard supergravity, you say, in which you can send parametrically the masses of the fields that you don't have there to infinity, and keep in your low energy spectrum?
So I have two answers to this. The first answer is that in some sense, you know very well that there are models in which the supersymmetry is broken already at the string scale. In this case, you have no choice, and you don't use supergravity in the standard sense. I mean, superparticles are just not there.
My question is within
supergravity. I know. Within supergravity, we addressed this some time ago with Lucien here and other people, and we show that this was for these S²=0 models, and we show that it is possible, but it's hard. So it is possible to have really inflationary models, supersymmetry breaking, very heavy Goldstino during the inflation trajectory, such that you can use the constraint all the time. In the vacuum, supersymmetry should still be broken, otherwise the constraint becomes inconsistent. It is possible, but the range of parameters it is possible, but it's hard. But it is possible, yeah. For the orthogonal constraint, nobody did it, and I see more complications we can discuss. I don't know if it's impossible, but I think for orthogonal constraint it's even more complicated, I believe. For the other, it was done, and it is possible. It's hard, but it's possible.
I can see a way if you, for instance, gates.
I think we are running a bit of time, so I believe that this discussion is not going to be resolved here. So the last question. No, not yet. We don't know what he's going to ask, so let's not.
It's going to be short. Yeah, I'm wondering, so if you protect causality in models of inflation which would use this constraint previously, does it affect the inflation dynamics, and would that
so again,
first
of all, we have a proposal in which you don't have any constraint at all, first of all. You just impose, as I said, these alternative constraints here which eliminate exactly the same fields as before.
So the potential that you get is the exact same?
It's the usual supergravity potential. There is no causality condition whatsoever at all. And we have two ways in the paper to realize this, either by these constraints or by starting with a higher derivative ultraviolet, and you have no constraint at all. Now, if you use the standard orthogonal constraint, maybe I should be more specific. I'm not saying that they are necessarily inconsistent. I'm not saying this. If you have a certain models in which this condition, this condition is automatically satisfied. For example, you take gravitino mass, which is this function G, to be constant, just constant, and then this is automatically satisfied. If you have a microscopic series which gives you precisely this, you can have problem with the other constraint, CS=0 in this case, actually, but you don't have superluminarity. So I'm not saying the orthogonal constraint is, by definition, is inconsistent, but the fact that it generates some non-trivial condition means that something is strange. It probably does not arise from a two-derivative standard supergravity theory, that's all.
Okay, thank you. I'm afraid I have to we will be back at 4:15.
Yeah, you also received in your email information about the dinner and the place where we go. Okay? Any more, you just ask us.
begin the cosmology session. The first speaker is Konstantinos Dimopoulos. He's going to tell us how to produce observable primordial gravitational waves. Costa.
Thank you very much. I'd like to thank the organizers for giving me the opportunity to visit beautiful Ioannina again. So I'm going to tell you a model of mine based on a recent paper, this one, on which manages to produce observable primordial gravitational waves. But I need to do some introduction first because I'm fully aware that this is a diverse audience. Okay, so, oops. Okay. Right, so the history of the universe requires special initial conditions which are arranged by cosmic inflation. In a nutshell, inflation can be defined as a period of accelerated expansion in the early universe, and what it does, it produces a universe which is large, flat, and uniform according to observations. But of course, the universe cannot be perfectly uniform because we need to form the galaxies. So in order to do that, you need to have some, oops, initial perturbations of the density, okay? So, and inflation, of course, fortunately generates also the primordial density perturbations, which are reflected on the cosmic microwave background. And so this is a picture of the latest observations, which you can analyze in spherical harmonics, and you get this here. The dots are the beam data, and the line is not the line that goes through the dots. It actually corresponds to the predictions of cosmic inflation. So you see that the agreement with observations is spectacular. There is a lot of emphasis on perturbations generated by inflation because they can discriminate between inflationary models. For example, these are the latest observations here, and you can see that previously acceptable models, these are the old data. Now these are the new data. So this orange strip corresponded to monomial chaotic inflation, for example. This is excluded. This purple strip corresponded to natural inflation. This is also excluded. Okay? So, but we are not going to talk about the density perturbations today. We are going to talk about gravitational waves. So inflation also generates a scale invariance perturbation spectrum of primordial gravitational waves in a similar manner as it does for perturbations. However, typically, these gravitational waves are too faint to be observable. There is, of course, a possibility to have enhancement of these primordial gravitational waves in a way that I will describe in non-oscillatory inflation. What is non-oscillatory inflation? To talk about non-oscillatory inflation, I need to actually discuss briefly the inflationary paradigm, which says that the universe inflates when dominated by the potential energy density of a scalar field, which is called the inflaton field. The Klein-Gordon equation of motion of the homogeneous inflaton field in the expanding universe is this, where the dots are time derivatives. The prime corresponds to derivative with respect to the field. So it's like the equation that governs the roll of a ball down the potential V in field space. Okay? Since the inflationary paradigm requires potential energy domination, this means that the field should slow roll down a relatively flat part of the potential, which is called the inflationary plateau. But at some point, the potential becomes steep and curved, so there is a critical value where inflation ends. And afterwards, the inflaton actually oscillates around its vacuum expectation value, and these coherent oscillations correspond to particles, inflaton particles, that decay into the standard hot Big Bang, into the standard model particles of the thermal bath of the hot Big Bang. Now, this is oscillatory inflation. Non-oscillatory inflation is characterized by a runaway scalar potential in which the minimum is displaced at infinity. Okay? Such models, non-oscillatory models, are usually used in quintessential inflation, which actually attempts to unify early and late universe accelerated expansion. Okay? And they actually correspond to potentials that feature two flat regions, the inflationary plateau and the so-called quintessential tail. So The inflaton field, therefore, does not decay after the end of inflation, but it needs to survive until the present to become the quintessence field and explain dark energy, which means that reheating, heating of the universe, actually needs to occur without the decay of the inflaton. And fortunately, there are many methods to do this. Okay, but before talking about gravitational waves, I want to talk about a particular phase of the universe expansion after inflation that appears in the non-oscillatory models of inflation, and that's kination. When the field actually falls from the inflationary plateau down the potential cliff, it soon becomes kinetic energy dominated. So the Klein-Gordon equation reduces to this, becomes oblivious to the potential, okay? And as a result, the equation of state parameter, the barotropic parameter, is approximately 1. So because it's the kinetic energy of the field that dominates, okay? So being kinetically dominated, the field actually rolls down to the quintessential tail. Now, if there is some radiation present as well, because as we said, there are mechanisms that produce this radiation without the decay of the infraelectron field, then because of the following, the radiation comes to dominate. What is the following? The following is that the kinetic energy, if you solve this equation, you find immediately that actually reduces as the scale factor to the -6. The radiation density, provided there is some radiation after the end of inflation, reduces as a to the -4, which means that, I mean, this is a log-log plot explaining what happens. During inflation, the density of the field is actually roughly constant. After the end of inflation, it becomes kinetically dominated, so it falls as a to the -6. If there is some radiation, even if it were originally subdominant, it actually comes to dominate at some point. This is the point, the moment of reheating. And after reheating, the hot Big Bang begins. All right, so you have the radiation and matter eras. Okay, so the field continues to roll after reheating for a while, but eventually it stops down its potential, it freezes, and it has a constant potential density. And this potential density is the dark energy today. That's why non-oscillatory models are used for modeling quintessential inflation. Okay? Now, let's talk about gravitational waves and kination. Okay? As I said, primordial gravitational waves from inflation are typically correspond to a scale invariant spectrum. But that is only true for the modes that re-enter the horizon during the radiation era, because the radiation energy density and the energy density of gravitational waves decrease in the same way as a to the -4, which means that if you are in the radiation era, it doesn't really matter when a mode of gravitational waves re-enters the horizon. But that's not true during kination, all right? Because as we said, the density in kination reduces as a to the -6. So instead of a flat spectrum, you actually produce a spike. And the longer kination lasts, the bigger the spike. Okay, so we can quantify this if we look into the density parameter of gravitational waves per logarithmic frequency interval, which actually behaves as a power law compared to the frequency, where the power is beta is actually determined by the barotropic parameter of the universe. Okay, so during kination, as I said, the barotropic parameter is equal to 1, which means that this beta is 1. Therefore, this density parameter per frequency actually behaves as such. So you see, if beta is 1, then omega is proportional to f for kination. All right? During radiation domination, because omega is equal to 1/3, this actually becomes 0. So the spectrum is flat because the density parameter is constant. So that's how it looks. Okay. So this flat patch corresponds to the modes that enter the horizon in the radiation era. But earlier than that, there is kination, and this is the spike that I mentioned before. All right. Now you can see here some of the projected near future observations, and you see that they cannot make connect with this. Maybe if we could extend kination down to frequencies lower than these, such that this amplification can hit the observable frequency, the observations. But that's not true, because the more kination lasts, the bigger the spike is, all right? And this horizontal dotted line corresponds to a constraint that should not be violated. This constraint amounts to too much gravitational radiation that affects the process of Big Bang nucleosynthesis, which is the sacred cow of cosmology. So basically, you see here that there is some point beyond which we cannot have inflation, kination to continue. Okay? So that's the problem. Kination corresponds to very high frequencies because it's right after inflation, and inflation happens at very high energies. However, if this stiff period, all right, actually were milder from kination proper, then it could potentially be extended to observable frequencies without disturbing BBN. So that is the idea. And in fact, there was a recent paper from Figueroa and Tanin who showed that observable parameter gravitational waves cannot be achieved if the barotropic parameter instead of 1 is actually lying in this region here, and the reheating temperature is actually rather low. Okay? So if now, let's say the barotropic parameter is 1/2, which is actually in the middle of this range, okay, then this beta here is 2/5. So the density parameter of gravitational waves, instead of being proportional to F, it's actually given by F to the 2/5. All right? So the spectrum now looks like this. Okay, so let me show it here. Right, so you see that the spike is much more mild, and therefore you can prolong this stiff period much more without disturbing BBN, which is this dotted line. And as you see, you can actually start making contact with observations. So that's the idea. But of course, you need to realize this idea somehow. And this is the model that I have, I'm presenting. So this model considers two scalar fields. They are directions in field space that meet at an enhanced symmetry point. The scalar potential is this. This is the standard hybrid inflation scalar potential, and we heard from the talk of Kaiser how one can obtain this from supersymmetry. Okay, but there is a crucial difference. So first of all, this sigma here is the inflaton direction. This var phi is actually the so-called waterfall field, and big M is its vacuum expectation value. All right, there is a crucial difference with standard hybrid inflation because the kinetic term is actually non-canonical, the kinetic term of the waterfall field. All right, there is a pole at the web, okay, following the alpha tractors construction. So it can be obtained if, for example, one considers a non-trivial Keller metric and so forth. Okay, so what does this mean? We can assist our intuition by switching to a canonical normalized waterfall field like that. So the canonical normalized is the phi. The var phi is the non-canonical normalized. And if you do this, you immediately see that they are related as such through the hyperbolic tangent. So you can use this to rewrite this potential in this form. All right? So, so this term is now this, and the interaction term is this. Okay, this is the interaction coupling, which is of order 1. Okay, the first thing to note is that the hybrid mechanism operates as usual. Why? Because provided the inflaton field sigma is actually very large, then you see that there is an effective mass squared, which is positive for the waterfall field phi. And this would drive the waterfall field phi to 0. But if phi is 0, then this term becomes canonical. All right? So you see that near 0, so during inflation, during hybrid inflation, the waterfall field is canonical normalized. So the hybrid mechanism proceeds as normal. But after we assume that the inflaton potential is such that provides a gentle slope for the inflaton along the inflationary plateau that we said before, so that it gradually diminishes, slow rolls. When it falls through a critical value, then this effective mass squared becomes negative, and there is a phase transition. And after the phase transition, the waterfall field rolls towards its VEV, but of course, the canonical waterfall field has its VEV displaced at infinity. So it rolls down this scalar potential. So let's see what this means. Okay? So this is a pictorial representation. That's the inflaton valley. You see here that at some point there's a critical value where there's a phase transition that releases the waterfall field from 0, and then it rolls towards infinity. Okay, so that's the potential. Immediately after the phase transition, you can approximate this potential as such. So basically what this says is that there is a period of hilltop inflation along the waterfall direction after the phase transition. And in fact, this hilltop inflation is fast roll. Why? Because this big M, the VEV, it will turn out to be Planckian. All right? We will show this later on. So there is about 13 e-folds of hilltop inflation. After hilltop inflation finishes, the waterfall field is released and grows very large. So now the potential can be approximated as such. So it's an exponential. When the field, a scalar field rolls down an exponential potential, it follows an attractor solution. For example, this was the case of power law inflation. In this attractor solution, it's not kinetically dominated. The kinetic energy of the field and the potential energy of the field are comparable. And in fact, it is determined by the slope, the strength of the exponential. And the corresponding barotropic parameter is given by as such, which you can solve for big M, and this is what you get. Okay? So, if we want to have observable gravitational waves, as I said, we need that the barotropic parameter is roughly 1/2. So if this is what we want, then we can immediately see that the value of the non-canonical normalized waterfall field, the vacuum expectation value, is actually equal to 2 times the Planck mass. Okay? So it's Planckian, as I said here. All right. So, conclusions. I was quick. Okay. Inflation solves the fine-tunings of the Big Bang and provides seeds for the structural formation, which reflect themselves onto the CMB. Another generic prediction of inflation is a flat spectrum of primordial gravitational waves. However, it is generically too faint to be observable. Non-oscillatory models of inflation lead to a surge in the generation of primordial gravitational waves. And non-oscillatory inflation, how is this done? It's followed by a period of stiff equation of state, which is typically dominated by the inflaton's kinetic energy density, and it's called kination. Kination enhances primordial gravitational waves. It actually corresponds to a spike in the spectrum, but the corresponding frequencies are too high, are unobservable at present. So, the model that I have presented, it's a model of a waterfall kination. It's kination in brackets because it's not fully kinetic energy domination, as I said, where the spike is much more mild, and therefore it can be extended to observable frequencies. The model considers 2 flat directions. They are flat directions because the inflaton is following the plateau, and the waterfall field has a Planckian value, a VEV, which is like a modulus field. Okay? These flat directions intersect in the enhanced symmetry point and give rise to hybrid mechanism with Planckian waterfall VEV, which is also a kinetic pole of the waterfall field. I hope I have convinced you that this waterfall kination may be observable by forthcoming LISA observations. Thank you very much. Yes.
Hi, okay, good talk, thank you. So I have 2 questions. One is that at some point you said that the heating temperature was 150 MeV. Yes. So in that case, what happened with the electron-weak phase transition? Okay, this is one question. The other question is, in those non-oscillatory potential, how can you reheat? I imagine that preheating is the only mechanism that...
No, there are many other mechanisms.
Oh, really?
They are both good questions. With respect to the electroweak phase transition, the energy scale, reheating happens at 100 MeV, but of course the energy of the universe is actually, if we go back right here, is actually much larger before. So here you see for example, this is the moment of reheating. But if we go backwards in time, you see that the radiation bath actually has a higher and higher temperature. Okay? So even the thermal bath has potentially higher temperature than the electroweak scale at some point.
Where did it come from, thermal bath?
Sorry? Yes, I have okay, since I have time, I can actually go there. I can present a particular mechanism for reheating, which is called rich reheating. There are many, but in the paper I have used that mechanism. So rich reheating basically corresponds to considering a non-minimally coupled spectator scalar field. Spectator means it doesn't affect the dynamics of inflation. There is a phase transition, I'll tell you where it comes from, at the end of inflation, and this results to particle production of this scalar field, spectator scalar field, due to the tachyon effect. And the produced particles decay into the thermal bath of the hot Big Bang and reheat the universe. I came up with this with Tommy Markkanen, and then these other people have actually developed it even further. And the most importantly, of course, they coined the name. We didn't come up with the name. So this is the spectator scalar field, the psi. There is this non-minimal coupling here, okay? And this is a perturbative potential. The idea is based on the fact that the Ricci scalar is actually given as such. So W is the barometric parameter of the universe. Now, during inflation, W is -1, which means that the Ricci scalar is this. And therefore, this means that the non-minimal coupling term corresponds to an effective mass square, a positive effective mass square for the psi. And this would send the psi to 0, all right, during inflation. But after inflation, we have kination. In kination, W is 1, and therefore R is actually -6, so it basically corresponds to a negative mass squared, which actually results to a phase transition. So this is what happens. The field during inflation, the spectator field is actually sitting at the origin, but after inflation, it actually finds itself on top of a potential here. So there is an outburst of tachyonic perturbations of psi particles, which immediately decay on the thermal bath of the hot Big Bang. And in this scenario, the reheating temperature is actually given as such. It doesn't notice that this psi field does not interact with the inflaton at all. And also, the whole mechanism does not depend on the initial conditions. So it only depends on the non-minimal coupling psi, and of course on the energy scale of inflation. And I passed very quickly. Okay, so here, because I didn't know that I had the time to actually go through this, the correct reheating, so the 150 MeV, is actually obtained for the non-minimal coupling of about 30. So it's very natural, I would say. Earlier. Yeah. During the kination period. Or the modified kination in this case.
Any other question? Okay, let's thank Kostas for his
Okay. Thank you.
Go ahead and present your.
Okay, so it's a pleasure to be back in Ioannina, and for that I thank the organizers for putting on a very nice meeting. I'm going to have to apologize in advance because my talk will be classical in 4 dimensions, which doesn't seem to be in keeping with many of the other talks so far, but hopefully it will nevertheless entertain you. So, as you can see from the title, I'll be discussing a possible method for detecting axion dark matter. So if you don't believe in axion dark matter, this is your moment to go find a different session. It's based on these works, and you'll notice that I've also put a reference here to a paper that is to appear in the next couple of months on gravitational waves, and given time, I will explain a little bit how this can also work for gravitational waves. So before I get into the meat, let me just give you a high-level summary of what I'm going to tell you with respect to axions. So the idea is that rather than doing a traditional haloscope type experiment looking for axion dark matter, where the axion comes in, interacts with a static background magnetic field, and converts into an oscillating electromagnetic field, which is then detected on resonance, we're going to imagine that you can set up a situation where you have an oscillating background magnetic field. And so what this corresponds to is really what people in radio do all the time. In your car radio, which you probably don't use anymore because you probably stream from your phone, the radio actually heterodynes two signals. It takes a carrier signal and the incoming signal and combines them into a signal that you actually measure. And that's exactly what would happen in this setup. You have a carrier signal, which is omega naught. You have a signal frequency, which is MA, and you will try and read this out at omega signal, which will be some combination of those two frequencies. So you might ask, why would you go to the trouble of doing this? And the reason is rather simple. It's that we're interested in hopefully accessing very small axion masses. And as you go to smaller and smaller axion masses, static background field haloscopes tend to lose detection power. However, in this heterodyne approach, as you can see from this middle equation that I've shown you here, the SNR actually scales favorably as you go to smaller and smaller axion masses, driven by that first term, and I'll explain where that comes from. And the outlook I will actually come to towards the end. And also, in the meantime, how this works for gravitational waves. So as a sort of lightning introduction, let me remind us of what the axion is and why it's interesting, besides it being a good dark matter candidate. So of course, it was introduced to solve the strong CP problem, which you can think of classically as being the alignment of the quarks in a neutron. And as it turns out that if you had given this to, for example, to a kid, you ask him to put 3 quarks in what looks like a sphere, they would not have aligned the quarks in that manner. And yet somehow nature has selected what classically looks like an alignment of quarks that is just along a line with no electric dipole moment. So of course, Pechet and Quinn introduced a dynamical solution to this problem, which basically promotes this angle to a field which relaxes it close to 0. This is the connection, of course, to this conference of supersymmetry, which is that actually it is well known that in many string compactifications you get axions sort of as a byproduct de facto. And indeed, we heard earlier this morning about how the dual of the Kalb-Ramond field is an axion and has the couplings that I'm writing here, in particular to something like GG dual, or the one that is useful for detection, FF dual. So indeed, the coupling to FF dual, when written in terms of classical electromagnetic fields, is just a coupling between an electric field and a magnetic field. So you can immediately look at this Lagrangian and say, okay, if I introduce a static background magnetic field, that axion is going to produce a collinear electric field, which I can then go away and detect. And indeed, if you went through the exercise, you would go away and derive Maxwell's new and improved equations, which contain additional terms. And in particular, I would ask you to look at the second line on this pink boxed equation, where you see a term that looks like the coupling of the axion to photons times the magnetic field times the time derivative of the axion field. And this looks exactly like a current. In fact, it's written next to what a standard model current would look like in Maxwell's equations. And indeed, you should think of this as being sort of an effective current that will source electromagnetic radiation due to the time variation of the axion field, which, if it's dark matter, is non-zero, because we're assuming that this is some axion that has been produced either through misalignment or through some other mechanism, and I think we'll hear about some other types of mechanisms later today, where you get all of the relic abundance of dark matter, rho dm, from this oscillating classical scalar field. And it's classical because we're going to be talking about very light axions, and so the occupation number is enormous. So, as promised, you can think of this as giving an effective current, which looks roughly like the equation that I've written there. And so, of course, this will induce a time-varying axion-induced magnetic field, B sub A, which is going to be proportional to this effective current. So, taking this effective current and imagining what this means in terms of an experiment, you should remember from Faraday's law that if you have a time-varying magnetic field and you have some sort of loop of some area which is volume to the 2/3 power, this looks like an EMF, right? And we know how to measure EMFs. In particular, we know what the power from an EMF looks like when it's applied across a resistor. So again, really apologies, this is almost engineering talk here. So you get a signal power that looks like the EMF squared divided by the resistance times some factor which depends on how long the coherence time is of your signal relative to the coherence time of your resonator. In terms of the physical parameters, you should think of the coherence time as being set by the fact that the axion actually has some spread in its frequency. It's not just oscillating at MA, right? It has some spread associated with the fact that it's a virialized field in the galaxy, and so it has some distribution. And so that distribution actually can be approximated as sort of like a quality factor, and again, apologies for the engineering terminology, of the axion field, which goes like 1 over the average dispersion velocity squared. The coherence time of a resonator is simply how long does it take for a resonator to saturate at the maximum energy stored inside that resonator. And so that just goes like the quality factor of your resonator divided by the signal frequency, or for the inverse time, the inverse of that quantity. So if you look at this equation on the right-hand side in particular, you would immediately think that what you want to do is you want to maximize omega signal, right, the frequency of the signal that you're trying to read out. You would try to maximize the axion-induced magnetic field, but from looking at the equation at the top there, there's really only one parameter that you control, which is the applied magnetic field in the background, and you're going to want to enhance the volume to as large a volume as possible. Of course, experimentally, these things are often linked, and so this statement of wanting to maximize these quantities together comes with a massive warning sign. So this is what people have been doing for the last almost 40 years, and indeed probably the experiment that you are most familiar with is ADMX, where here you just apply a static background magnetic field collinear with the axis of a cylinder, and so an incoming axion field, or just the permeating axion field, will convert with some probability into electromagnetic radiation at the same frequency. And so your omega signal is proportional to 1 over the radius, or the length of your cavity, and so goes like volume to the minus 1/3. So when I said that these things were linked, I meant it. An approach that has been proposed in the literature in the last few years to try and access smaller and smaller axion masses is to use an LC resonator. Now, the reason why you would want to do this is because if you think about the setup on the left, if you want to go to smaller and smaller axion masses, and in particular if you wanted to access, for example, the fuzzy limit of dark matter, you'd have to have a resonant cavity the size of a dwarf galaxy. Clearly, that's not going to happen, so you're going to have to come up with something else. So indeed, people have come up with something else, and that comes in the form of these LC resonators, where you take a box of experimentally manageable size, but then you put inside an LC circuit whose resonant frequency is no longer attached to the volume of your cavity. And so now your signal frequency is the signal associated with the LC resonator. But as you can sort of see from this pictorial depiction here, there's going to be a mismatch between the wavelength of the electromagnetic radiation that is being produced from this interaction and the size of the box where you're actually capturing that radiation. And so at smaller and smaller axion masses, this approach actually gets penalized. So enter what we proposed for the first time in late 2019, and since the pandemic I haven't actually been able to present this at a conference, is the idea of heterodyning the signal. So as promised, instead of having a static background magnetic field, you have a time-varying background magnetic field, and I'll explain in due course what that implies for signal sensitivity. But where now you can have very, very small axion masses, and as long as there is a signal resonance in your cavity that is matched to the difference or the sum of those two frequencies, you will be on resonance, and you will not have the same penalty as you go to smaller and smaller axion masses that you do in the case of the LC resonator. So what this might look like in the context of an actual experiment is you would want to leverage the fact that we have produced very good superconducting radio frequency cavities with extremely high quality factors. So you remember from a couple of slides back, I flashed to the fact that the signal power could be enhanced by the quality factor of the resonator. And superconducting RF cavities can have quality factors up to something like 10 to the 12, maybe even 10 to the 13 in a sufficiently large cavity. You would have a background resonating field at order of a gigahertz, and for small axion masses, the signal field is also at the order of a gigahertz. Of course, you want these two frequencies to be always, the difference of these two frequencies to be always the axion mass, and so you need to be able to tune the resonant frequencies, and this can actually be done in physical cavities. For very small separations in frequency, you can literally just deform the cavity by pressing on the sides using piezoelectric actuators. For large frequency splittings, you might have to introduce something like a plunger. So really imagine a plunger that you just vary the length of the cavity. And the reason why this works is because you can actually go away and look in Jackson or Hill or any of your other favorite classical electrodynamics textbooks and find that in the section on electromagnetic cavities, you would find that you can have degenerate modes, so omega 0 equals omega 1, if this condition here is satisfied, where these p's and x's are constants associated with which mode you're interested in. As it turns out, we also suggested the possibility of just setting omega 0 equals omega 1 and then doing your experiment anyway, no tuning whatsoever, and you still have interesting sensitivity, and I invite you to look at that paper. So of course, no experiment comes for free, not in monetary costs, but also not in the terms of noise. Right? And so most resonant cavity experiments deal with, in particular, thermal noise, which you see here on the bottom left. But by introducing this background oscillating magnetic field, which of course carries a lot of energy in it, so there's a lot of energy already inside the cavity where you're trying to measure a very, very small signal at a frequency that is not so far away from the frequency of your signal, there's going to be a whole host of other sources of noise as well. And these I invite you to look at the papers for all the details, but they come from the fact that when you actually load the cavity, you never get it at exactly the frequency you want. There's a little bit of spread associated with how you load the cavity in the first place. There's error in the fact that you don't actually read out the mode that you think you're reading out. So remember that the E that was produced in the E dot B interaction is parallel to the B field that is applied. And so that means that if you're reading out just the E's and you're just loading the E's, these things are perpendicular. And so the degree to which you're able to measure that perpendicularity is also not going to be perfect, and so that is also going to lead to the introduction of noise. As it turns out, there's also vibrations of the walls, which introduce additional noise. You get phonons coupling to two electromagnetic modes and spreading energy across frequency. And then, of course, there's the issue that is special to cavities with material with large electric fields near the edge, where if there are discontinuities in the material, you can strip electrons off. And these electrons will whiz around the cavity and radiate and source additional noise. So what this looks like in terms of the noise power is for rather optimistic parameters where the rejection, so how orthogonal I'm able to measure these modes, is 1 part in 10 to the 7, and I'll explain where that number came from. And where the intrinsic quality factor of the cavity is sort of at the maximum of what's been achieved so far of 10 to the 12, this is what the noise looks like. So for a large range of axion masses, you would be thermal noise limited in the same way that you are in, say, ADMX or Haystack or some of these other experiments. But you can see that as you go to lower and lower axion masses, you're going to start getting hit by the noise associated with the fact that you've got this great big source of energy inside your cavity. So just to give you an idea of how much power this is and how it scales with the relevant quantities, here are the equations. And if you have questions about these, I'd be happy to answer them. But in the interest of time, I'll keep moving. So to give you an idea of the experimental precedent, to motivate the fact that these numbers that I've shown you are not just pulled straight out of thin air and shown in front of you to make pretty plots. Here is a plot taken from an experimental paper by the group at Fermilab, which is really pushing the forefront of development of superconducting RF cavities, where they've shown that for accelerating gradients, because of course these people are interested in accelerating, not not in axion detection, although now they are interested in axion detection. For acceleration gradients going up to about 30 megavolts per meter, they've achieved quality factors of 4 × 10 to the 11 at a magnetic field inside the cavity of 0.1 Tesla. So for reference, ADMX has a magnet of 8.5 Tesla. So clearly this is a much smaller magnetic field, but the quality factor enhancement means that this will actually be interesting and competitive. In terms of the mode rejection that's been achieved, remember this orthogonality of the loaded mode and the readout mode in terms of how you actually load and read them out, a rejection factor of 1 part into 10 to the 7 was actually achieved in this specific cavity setup, which comes from these papers, which is described in these papers, which was actually looking at the possibility of detecting gravitational waves. Hence, more on this in just a few slides. Then, of course, if you want to go to very, very low frequencies, so very, very small axion masses, you might worry about low-frequency noise from the vibrations or from seismic noise causing vibrations of the cavity. And for that, in fact, the same group at Fermilab has demonstrated control of the central frequency of 1 part in 10 to the 10. And since that control actually comes from controlling wall displacements, you can characterize the wall displacement parameter, which was this parameter delta that I flashed on the previous slide, of 1 part in 10 to the 10. So that also aids the experimental prospects. So in terms of actually calculating what the signal to noise looks like, you typically express it in terms of power spectral densities, right? So how much power is at what frequency in the experiment that you're actually conducting, and then you integrate over all frequencies. And since these cavities really only have resonant peaks near the frequency of interest, that integral over all frequencies is dominated by what's in the bandwidth of the cavity. So if you're thermal noise dominated, which as you saw from the plot I showed you just a couple of slides ago, was in much of the parameter space, this is how the signal to noise ratio scales with the relevant parameters. So you see that it's strongly dependent on the magnetic field, it depends on the mass, it depends on the quality factor of the axion, which is something like 10 to the 6, right? Because there's a dispersion of roughly V is 10 to the minus 3c, and remember that QA was 1 over V squared. It goes like the intrinsic quality factor of the cavity, which you'll recall there's experimental precedent of more than 10 to the 11. The amount of time that you're willing to spend at any given frequency, which is the TE, so the E-fold time, and the temperature of your cavity. And of course, the volume and the amount of dark matter and so on as expected. So how does this compare with the nearest competitor, the LC resonator, which is the only other proposal that can reach small axion masses? Well, this is the equation that I showed you earlier, but now you kind of understand where these parameters come from. And let me just walk you through how these things compare. So clearly, in terms of the first two parts of this equation, the heterodyne approach compares extremely favorably, because omega naught is much greater than MA as you go to smaller and smaller MA. Likewise, the quality factor of an LC resonator can be maybe 10 to the 6, 10 to the 7, possibly 10 to the 8 if you push it, whereas the quality factors here can be 10 to the 11, maybe 10 to the 12. So clearly on that factor, heterodyne approach will win. In terms of the temperatures concerned, the LC resonator probably wins because there's no great big power source inside there already. Remember that in the heterodyne case, you do have a power source, and so there's a lot of energy that has to be extracted by whatever cooling mechanism you have. And so the temperature in an LC resonator can probably be much smaller because they can use a dilution refrigerator, which has a maximal power extraction rate. So here we would imagine that we'd be at cryogenic temperatures, so something like 1.4, 1.8 Kelvin, whereas a dilution refrigerator can be something like 0.1 Kelvin. And of course, finally, as far as the magnetic field is concerned, the heterodyne approach loses enormously, because remember that I said that the peak field was something like 0.1 Tesla, whereas in a static experiment, you can have a much, much larger magnetic field, up to maybe 10 Tesla. But what this looks like in terms of the reach to axions, so there you see a couple of interesting bands phenomenologically. So there's the QCD axion in sort of a gold color. You see where ADMX and the other haloscopes are, which is sort of focused on the region where we think the QCD axion gives you the right relic abundance. You also see a line here that I think will be discussed in a couple of talks from now on the standard ALP misalignment dark matter. So this is if you have a sort of order 1 initial misalignment angle, that's where you get the right relic abundance. And you see that actually with a 50-liter prototype, which is already under development at SLAC, you will be able to probe new parameter space. So maybe not the most theoretically motivated parameter space, although if somebody has a theory that lives up there, I'm all ears. But nevertheless, we hope to probe new parameter space with an already funded prototype that is under development, not yet construction. In a future setup, maybe going up to a cubic meter or pushing all of the parameters as far as we can go, which is the futuristic line, we would certainly have new sensitivity to the QCD axion and an enormous sensitivity to ALP DM across a number of orders of magnitude. So this is very exciting. So what about gravitational waves in the last sort of 2 minutes that I have? This here is the classical action for electromagnetism in a curved background. But I am in a pretty flat background, and so I can just expand this around flatness. And what you would see is that you get a Lagrangian that has terms that go like hf squared. So given the start of this talk, this should immediately ring alarm bells because it looks very much like the form of the axion Lagrangian, which is AFF dual. And indeed, this similarity is not noticed for the first time by me. Instead, it was indeed used to great success like 35 years ago by Rafelt and Stodolsky, and it's also been noted by a more recent paper that the reference is there, and I invite you to look at it as well. So you would get something very similar to the Primakov effect, where now instead of having an axion in the background magnetic field converting into a photon, you would have a graviton. The form of the effective current is a little bit more nasty than that of the axion, and indeed you can see that if you have a time-varying background field, this is going to be really nasty. But we first applied this to a static haloscope because those already exist, and we wanted to know, do such experiments actually have sensitivity to interesting BSM sources? Because remember, these are operating at gigahertz, so this is certainly not a standard model source. And the answer is the following. So these are the sensitivities of current experiments if they reanalyze existing data in the mode that they read out for axions and look at for gravitational wave signals instead. And you can see that the best that exists currently is ADMX, as expected, since it's the best currently for axions as well. And the strain sensitivity is maybe 10 to the minus 22. In terms of how this compares to sources, if you think about primordial black hole inspirals, pretty hopeless. In fact, if you rescale to the distance that gives you an h of 10 to the minus 22, it's around here in the moon. So pretty hopeless. For superradiant signals, which would be a BSM squared signal, it's also kind of hopeless. But if you go to a heterodyne approach, I promise you that the dominant signal is actually from the vibrations of the wall. I won't explain how or why. And there, if you're on resonance, the sensitivity might be much better. So I will leave you with the Outlook slide, which is the same as the high-level summary, and so I won't repeat it. And thank you very much for your attention.
I understand, I mean, I have some background from axion telescopes from my master supervisor, but anyway, so really, I mean, you did not give any details about your prototype, whatever, right? You did not give any sizes, frequencies, and all that stuff. And, or maybe you give, but I was too fast.
It's 50 liters.
Yeah.
So it's sort of 10 centimeter length, 10 centimeter width, and the stored energy is something like, I don't know, 50 joules.
And in your scaling, okay, it looks not so smaller size than a typical helioscope. That's what you are saying. So
ADMX is, if I remember correctly, more like 100 liters, so about double the size.
Okay. So that's one. Okay. The other question I have is about these quality factors. I don't know if it's, you have to control very well your omega naught, right?
That's right.
So, and I'm not so sure how well you can control it, or you have some mechanism.
It's right there.
Okay.
Delta omega over omega is controlled at 1 part in 10 to the 10 by the dark SRF collaboration. So that's a very recent data point, and it's because before then people didn't need to control it to such great precision. So these were the first people to actually try, and they managed quite well.
Yeah, that's okay. That's the important.
Yeah.
Okay, thank you.
There's one in the back there.
Okay, thanks for the nice talk. Actions coupled to the, the photon basically, like a dark photon, right? It's the interactions are kind of similar.
Like a what? Sorry, could you speak up?
It's like a dark photon sometimes.
Not exactly, but similar.
Not exactly,
yeah.
but you still have this effective current, basically.
Right.
So can you observe a dark photon with this device?
So with the heterodyne device, you probably can, but not through the coupling to electromagnetism, because you don't have that same linear term coupling the dark photon to the electromagnetic radiation, right? So in the case of the dark photon, the effective current goes like MA times square root of rho dm, right? So there's no background field in the game at all. But in fact, if you have a source of electromagnetic radiation inside there, which you do, then there is a small amount of dark photon that you're necessarily generating anyway, right? Because what couples to currents is, let's say, E plus epsilon E primed, right? And so you would actually expect that there would be a small amount of, on top of the background field, oscillating dark photon component that exerts radiation pressure and induces mechanical noise, actually. And so you might hope to look at what looks like mechanical noise and see if there's a characteristic frequency associated with that. So that's actually something that we're investigating at the moment with Raffaele Dagnolo and his postdoc Gabriele Rigo.
Okay, thanks. So you can distinguish basically between axions and dark photons, right?
Well, yes. In the case of yes, because the characteristics of the signal would be quite different. In both cases, just turning off the cavity would also kill the signal, so that's unfortunately not a distinguishing feature. The characteristics of the signal would be totally different. So there's many handles that one has, mainly because one is an electromagnetic signal and the other is a mechanical signal.
Yeah, okay. Thank you.
Could you tell me how to use it?
Yeah.
First pointer. Okay, thank you.
Okay, please go ahead.
Okay. First of all, thank you for giving me this kind of a nice opportunity. I'm Shuntaro Aoki from Chuan University in Korea. Today, I'm going to talk about the extension of the so-called Higgs R-square inflation models. The Higgs R-square inflation model is motivated as the UV completion of the Higgs inflation. And today, I want to discuss the two directions of the extension. First is the supersymmetric extension, and another one is the introduction of the dark matter. Okay, so let me start from the brief introduction of inflation. As everyone knows, the inflation is the rapid expansion of the early universe, and this is theoretically and observationally established. From the viewpoint of the theoretical side, it solved the initial condition problem of the Big Bang standard cosmology. And from the observational side, it's the recent observation of the CMB strongly support the existence of inflation. And as you know, the observation data constrained a lot of inflation models from the so-called NSR plane. So there are several kinds of inflation models, but one of the most promising one is called the slow-roll inflation, which require the scalar field that is called inflaton. So the picture is like this. Inflaton is rolling on the top of the potential, and during that time, because of the energy of the potential, the universe experiences the expansion. So I say the scalar field inflaton is necessary for the slow-roll inflation. So the natural idea is to identify the standard model Higgs boson as the inflaton. So this is called the Higgs inflation. But however, the original standard model Higgs potential doesn't work. So I mean by original, just a chaotic potential like this. We don't care about the Higgs wave during the inflation, so this is nothing but the chaotic potential. But this kind of potential doesn't work, and it's already disfavored by the observations. So we need a more flat potential to realize the inflation. So what we call Higgs inflation nowadays is including the non-minimal coupling like this. Here, psi parameterizes such a non-minimal coupling. So we introduced this kind of coupling between the Higgs field H and the Ricci scalar. And it turns out it's successful. Because of this coupling, in the Einstein frame, you can calculate the potential, and then you can show we get a very flat potential for the large non-minimal coupling psi. Actually, we have two parameters, chaotic coupling lambda and a new parameter, non-minimal coupling psi. And if we assume the order 1 chaotic coupling lambda, the CMB prediction, normalization of the power spectrum require the relatively large psi, like 10 to the 4. So this is successful, but because of this large non-minimal coupling, sometimes people claim the cutoff scale becomes lower compared to the Planck scale. Actually, in this model, the cutoff scale is given by this combination Planck scale divided by psi, and I say the psi is large, so this cutoff scale is relatively low. Actually, we need to compare this scale to the typical energy scale of the inflation. For example, the Hubble parameter during the inflation is given by this times chaotic coupling lambda. So for the order 1 lambda, this hit the Hubble scale during the inflation. So in that sense, the discussion based on the semi-classical analysis becomes questionable. This is called the unitarity issue in the Higgs inflation. So there are several solutions. One of the easy way is just to introduce a new degree of freedom to this system. This is looks like Higgs in the standard model. So without Higgs, the unitarity scale of the standard model is relatively low, but the introduction of Higgs push up the unitarity scale around the table scale. So one way is to introduce a new degree of freedom. And of course, there are another proposal, like this discussion is based on the metric formalism, but you may use another Palatini or another formalism. Then you can show the cutoff scale changed by this expression. And also, I say that we assume the order 1 chaotic coupling, but it's not necessary. So if you choose the small chaotic coupling, you can avoid this kind of problem. So this is called the critical Higgs inflation. So in this talk, I want to focus on the first option, the introduction of the new degree of freedom, and see what's happened. So there are many ways, just way to introduce a new degree of freedom. But recently, the so-called Higgs R-square inflation models has been intensively studied. So the Lagrangian is given by this form. The first 3 are just Higgs inflation with non-minimal coupling. But we add the R-square term with coefficient alpha like this. So as you know, R square contains the higher derivative of the metric. That means we gained a new degree of freedom. That is called scalaron. So actually, it is known that the introduction of scalaron push up the unitarity scale to the Planck scale and can solve the unitarity problem in the original Higgs inflation. So let's see how the scalaron appear in the Einstein frame. So I just, for simplicity, we just neglect the Higgs field and focus on the pure R square case. This is the, just Einstein-Hilbert plus R square. And you can equivalently rewrite this Lagrangian to, in this way. So I introduced a chi as an auxiliary field. If you integrate out a chi, then you can go back to the original system. So this is just the equivalent system. And you can perform the conformal transformation, just a redefinition of the metric. Here, omega is given by this form. And I redefine the auxiliary field chi in this way so that chi has a canonical kinetic term in the Einstein frame. Then you get this kind of system, and you can see the equivalence between the R square and the scalaron system in this way. So actually, we have a Higgs field, so this omega factor contain more complicated form, but the fact the scalaron appear is the same. So I motivated the Higgs R square inflation model. So in this talk, I want to discuss the two extensions. So first, I want to focus. I want to discuss the further UV emitting, that is the supergravity emitting. The another direction is actually inflation in the Higgs R square has been studied well. So we want to study the post-inflationary dynamics like reheating or dark matter production during the reheating. So first, let me focus on our supergravity embedding. Yeah, actually, the solution is very easy. So we already know how to construct the Higgs inflation in the supergravity, and we already know how to construct R-scale supergravity so independently. So the strategy is just to combine the two systems. So for the Higgs inflation in supergravity, naive embedding for the naive embedding to the MSSM doesn't work because it's produced a tachyonic instability during inflation. So, but it is known that MSSM works, so we adopt this option in the Higgs inflation in supergravity. And for the R-square supergravity, we may use the Chekotty's old work. He constructed the R-square supergravity using the superfield, and he also discussed the duality at the level of superfield. So duality means, yeah, as we saw in the previous slide, in the non-SUSY case, R-square terms produce a real degree of freedom scalaron in the Einstein frame. Actually, we can do the same procedure in the, at the superfield level, and you can show the R-square supergravity is equivalent to the standard supergravity plus two chiral superfield denoted by T and C. So unlike the non-SUSY case, we have four complex scalar field in the dual frame. So actually, the real part of the T is identified as the scalaron in the non-SUSY case. So this is the result. The Kähler potential and the superpotential are given by this form. The Kähler potential is defined through the omega function, the frame function. And here, the blue line and the red line correspond to the NMSSM part and the R-square part, respectively. So we have many fields, NMSSM field, the NMSSM singlet S, and two Higgs doublet H and HD. And we have dual scalars T and C. So in this picture, we already performed the duality procedure. So there's no R-square structure, but instead we have two dual scalars T and C. And especially, the coupling of the T sector is completely determined by the R-square structure. So in that sense, the T sector is predictive in this model. And also we have four parameters, chi, lambda, rho, alpha. But the important ones are the chi and alpha. Chi is related to the non-minimal couplings to Xi by this equation. And alpha is the originally the coefficient of the R-square term. But now we already performed the duality procedure, so alpha appear in the superpotential. So I want to go back to the question of unitarity. So I said there's no unitarity issue in the non-SUSY case, but it may be non-trivial after the supersymmetrization because we have many fields, many different couplings. And the precise study requires analysis of scattering amplitude, but it can be manifested by some specific field redefinition and conformal transformation. So as I said, scalaron corresponds to the real part of the T field, but I perform some nonlinear field redefinition, which I do not show here because it is complicated. But you can show converting the real T to the sigma and performing the conformal transformation. You can equivalently rewrite the system in this way. So you can see the all field coupled to the Ricci scalar in the conformal way, and all fields are canonically normalized. So there is no big non-minimal coupling here and also here. So, and also the important point is the sigma field looks linearizing the Higgs inflation in this form. So you can say, how to say, this is an analogy between the linear sigma model and the non-linear sigma model. So if you integrate a sigma field, you get some non-linear interaction for the Higgs inflation. So in that sense, this gives the UV completion of the Higgs inflation at the level of supersymmetry. So we don't have non-minimal coupling in the kinetic terms on, for the graviton and the scalar fields. So where chi has gone, where the non-minimal coupling has gone. So actually, it's appear in the potential in this framework. Actually, this is a potential in the our potential. This is really complicated because we have introduced many fields. But you can see chi parameter appear, for example, here, here, here. And the most important point here is the chi always appear with this combination. So here, just to remind, alpha is the coefficient of the R square term. So chi can be large, but alpha also can be large, and they compensate each other. And we can get the order 1 coupling. So in this way, in this frame, we can, how to say, visualize why unitarity issue is solved in this framework. And we thank you. And we show that even after the supersymmetrization, the unitarity problem doesn't appear in this system. So I have a brief comment on the phenomenology. For the successful inflation, we need to consider the stabilization of the all fields. Actually, the sigma field and the H field are the same as the non-SUSY case. But we have many extra fields like S and C or charged Higgs state, etc. Actually, we found some tachyonic instability appear in the linear combination of these fields. So we need to modify the omega function, Kähler function, by adding the quartic coupling in this way. And also in our naive embedding, the supersymmetry is restored after the inflation, so we need to break the supersymmetry spontaneously. So one of the easy ways is just to modify the omega function by adding the linear term. And in this case, you can get SUSY breaking at the minimum, and the scale is given by this combination. And some perturbativity constraint, it's bounded by the 10 to the 30 GeV. So in that case, you get a relatively high scale SUSY breaking scale. Of course, you can introduce another field, and you can adjust the SUSY breaking scale by introducing another parameter. So because of time limitation, I skipped some comment on the phenomenology. And so I want to move to the second part of my talk. So this part, I did not consider supersymmetry, just focus on the Higgs R square model. And discuss the reheating and the dark matter production. So I don't talk much about the reheating, but this is a short summary of reheating. So during the inflation, the Higgs field is stabilized with heavy mass, but after the inflation, sigma field, the scalaron and the Higgs start oscillate. So it becomes a really complicated system. But after some complicated analysis, it turns out the reheating is completed by the Higgs decay to the top quark pair. And it turns out the reheating temperature is given by the 10 to the 40 GeV in this model. And also we have to note that reheating is not an instantaneous process. And this statement is a general statement, but this also applies for our model. And this kind of non-instantaneously affect the dark matter production because this is a Boltzmann equation for the dark matter X, and the left-hand side contains the Hubble parameter, and it's sensitive to the evolution of the universe. So this is the time evolution of the energy density. Black one is the infraton energy density, and the orange one is the radiation energy density. So there is a crossing point which defines the reheating completion point. And after the inflation, radiation becomes dominated, and the temperature decreases like inversely the inverse of the scale factor. But during the reheating, infraton energy density dominated, the temperature becomes a complicated function of the scale factor. So we need to take into account both effects to estimate the dark matter production. And also we are focusing on the FIMP dark matter scenario. FIMP is a feebly interacting massive particle, so it's never summarized, so it's completely different from the WIMP scenario. And explicitly we introduce the dark matter X in this way. So in Jordan frame, there are only two couplings, eta, non-minimal coupling, and the Higgs portal, lambda HX. But in the Einstein frame, you get many Planck suppressed interaction between the X and the infraton or Higgs. And also, we are interested in the FIMP situation, so we are considering the conformal coupling to the dark matter and the vanishing Higgs portal couplings. And also for the right-hand side of the Boltzmann equation, we need to evaluate some reaction rate or collision process. And we take into account thermal production and non-thermal production in this setup. So for the thermal production, we take into account the scattering process from the standard model particles. And this is efficient both during and after reheatings. And for the non-thermal production, we consider the infraton. Infraton, in our case, infratons are sigma, scalar and H in our case. And we take into account this kind of non-thermal scattering process to evaluate the dark matter production. And also, as we saw in the previous slide, we have many Planck suppressed interaction. So in that sense, the graviton exchange, the effect of the graviton exchange is comparable. So we also need to take into account the graviton exchange. So this is the result. This is the restriction of the reheating temperature and the dark matter mass. And the orange line shows the effect of the thermal production, and the blue one shows the non-thermal effect, non-thermal production. And the black one is total, and the blue shaded region is already excluded by the overabundance of the dark matter. So, as you can see, in our scenario, the thermal production is the dominant source for the dark matter production. And also, this green band corresponds to the, thank you. Green band corresponds to the prediction of the reheating temperature in the Higgs R-scale inflation model. So, just watching from the crossing point, you can see this region of the dark matter mass can fully explain the correct dark matter abundance. So I don't have time, so I should stop here. So thank you very much.
This model, the infraton field is the Higgs field or the scalar?
Actually, during the inflation, the Higgs field is stabilized with a heavy mass, but it's affected as it has the non-trivial vacuum expectation value. So in that sense, it affects the inflation. But in the actual analysis, only scalaron is rolling. So effectively single field, but the Higgs played an important role for the inflation analysis. Yeah.
Any other question? Okay, let's
thank you.
All right. So it was quite interesting and nice to see that my talk ties in very well with Sebastian's talk. However, I do apologize in advance for the small overlap in some of the things that I will be explaining, and also for some of the punchlines that he already used during his own talk. All right, so the title of my talk is Action Dark Matter from Frictional Misalignment, and this is also the title of the paper that we uploaded on the archive a couple of weeks ago. So this was a collaboration between Pablo Quiles, who is a postdoc at DESY and soon to be a postdoc at UC San Diego, Kai Schmitz, who, when we started our work, was a postdoc at CERN, but since has moved and is now a professor at Munster University. And I'm a postdoc at the Institute for Basic Science in Korea. So this is the basic overview of my talk. The first part of my talk, I will give you a brief overview of the standard action misalignment mechanism, which is the standard mechanism for generated action dark matter non-thermally. In the second part of my talk, I will explain the basic mechanism that we're introducing, and I will provide the necessary machinery that can be applied in some particular models that I will then explain and present in the third part of my talk. And finally, I will conclude my presentation. All right, so the misalignment mechanism is the standard mechanism for non-thermal generation of action dark matter. We assume a pre-inflationary scenario for the scale of Peche-Quinn symmetry breaking, and this implies that after inflation, the action misalignment mechanism would be homogeneous, and it would be some random value which is of order 1. This value should not be fine-tuned, meaning it shouldn't be artificially close to 0 or pi. After inflation, the action follows the equation of motion, which I have labeled number 1, and the basic idea during radiation domination can be depicted in the plot on my slide. So you should read this plot from right to left. So from high temperatures to low temperatures during radiation domination. The yellow solid line is the Hubble friction, and initially it dominates with respect to the blue line, which is the mass of the axion. However, as time moves on and the universe cools off, the Hubble rate decreases while simultaneously the mass of the axion increases. The mass of the axion is provided by instanton effects, which become more and more efficient for low temperatures, and there is inevitably one point at which the two lines cross. When that happens, that signals the onset of oscillations, and from that point on, the axion oscillates around the bottom of the potential, and it obeys this adiabatic invariant, which is a constant from this point on. And we can use this adiabatic invariant to compute the axion dark matter abundance today. So what I just said in words, if you do it quantitatively, you get the result of equation number 4. You can plug in your favorite parameters for the axion, and you can find the final dark matter abundance. So as Sebastian mentioned before, in the MA-FA plane, where MA is the mass of the axion in EV, and FA is the axion decay constant, there is a single line, which is the black line in my plot, in which the axion predicts the correct dark matter abundance. Every point above the black line would yield too little dark matter to be the observed one, and every point below this line yields too much dark matter to be the observed one. And I will be calling these two regimes traditionally underabundant and overabundant respectively. The blue line is the QCD axion line, and as Sebastian mentioned, there is a single point at which the two lines cross, and this is the point, the unique point at which QCD axion can be the entirety of dark matter. So what did we do in our work? So the basic idea for our work is that we're coupling the axion to some non-abelian gauge field, which forms a thermal bath of temperature T prime. This gauge field is dark in the sense that it doesn't couple to the standard model, and it is also a pure gauge field, so there are no light states that are charged under it. The idea is that in this hot thermal environment of this non-abelian gauge field, strong Sphaleron transitions between the non-topological vacua of the non-abelian gauge field essentially behave as a thermal background of the topological charge. And this ultimately drains the kinetic energy of the axion. The entire effect can be captured by the inclusion of this effective term, which is capital epsilon, a function of T prime, which is the temperature of the dark thermal bath. And from that point on, the axion can lose energy through this additional friction. And this is the source of the friction that we consider in this work. So the friction coefficient that I showed you is given by equation number 8. This is a standard result. This was discovered in the early 90s by Saposnikov, McLaren, and Motula. However, in their case, they consider this effect only for the QCD axion. And for the QCD axion, there's an additional effect which induces additional suppression to this friction coefficient because of the presence of light charged states. So the conclusion in that work was that this effect is always negligible, and then this idea fell into obscurity. People didn't worry about this effect too much for several decades. Eventually, a couple of years later, this idea was revived by Berghaus, Kaplan, and Graham. And the idea was that they chose a pure gauge field, in which case there's no Yukawa suppression because there's no light charged states. And in this case, one can get a much greater signal. And they applied this additional friction to modify inflation dark energy and early dark energy. Inspired by their work, we decided to follow a similar logic, but modify the axion misalignment mechanism and expand the scope of the traditional mechanism. Right, so let's briefly discuss the properties of this dark thermal bath. The total energy of this dark thermal bath, we assume, will decay as radiation throughout, from some temperature that is greater than the electroweak phase transition, all the way to a temperature that's smaller than recombination. At some point between these two temperatures, the dark thermal bath that consists of the dark gauge field has to be spontaneously broken or confined, which implies that then the byproducts of this process themselves have to decay into light states so that they behave as radiation throughout. This is a necessary requirement in order to avoid overclosing the universe. And then to cut a long story short, since these light states will exist in the period of recombination, they have to be constrained by observations of the effective number of light degrees of freedom as measured at CMB scales. And in fact, in order to set a constraint for the temperature of this dark thermal bath, we use the Planck measurements, which constrain the contribution to be 0.3. So if you convert this inequality into a requirement for the ratio xi, which is the ratio of the temperature of the dark thermal bath divided by the temperature of the standard model, at some temperature greater than the electroweak phase transition, you find that for SU3, the highest allowable ratio is 0.86. And for our work, we will saturate this ratio, in fact. All right. So after the electroweak phase transition, the two thermal baths evolve independently. They don't communicate with each other. And therefore, they conserve entropy independently. You can use entropy conservation to relate one temperature to the other at lower temperatures as well. And in fact, this equation essentially acts as a bridge between the two temperatures, and you can convert one to the other at will. So let's now discuss what are the consequences for the equation of motion of the axion due to the presence of this thermal friction. There are two consequences, one at early times and one at late times. The one at early times is that it alters the moment at which the axion starts oscillating. The idea is that based on the Slorov solution, which is equation 13 in the conventional case in which Hubble friction is greater than thermal friction, the violation of Slorov conditions is the one that signals the onset of oscillations. And this takes place when the exponent is of order 1, which implies that the mass of the axion and the Hubble rate have to be of the same order. This is the standard result. This is exactly, what I showed you in the second slide of my talk. However, following the same idea, in the presence of thermal friction, the exponent is modified, which means that when this exponent that has this parametric dependence becomes of order 1, that's when the axion, in fact, starts rolling. If you collect these two requirements in a single equation, you get this two-branch equation, and you can choose the upper or lower branch depending on whether it's the Hubble friction that dominates or thermal friction. There is another consequence in the equation of motion of the axion that has to do with the behavior of the axion at late times. The idea is that the adiabatic invariant that one uses to make a prediction for the axion abundance is modified because there's an additional form of friction, and hence the main bulk of the paper and the main calculation that we performed is to derive a new generic adiabatic invariant using some general friction gamma. So we have done so. I'm not going to get you too far into the weeds in the details of the calculation. And this is the final result. So what is interesting in this final result is that I have separated the contributions into 3 groups. The first one is the standard result, which is the one I already showed you in the third slide of my presentation. Then there is an additional factor which yields an overall suppression. This factor is expected. We add some friction. We expect the friction to be able to take out energy from the axion. However, there is another factor which is an enhancement factor, which might be somewhat counterintuitive how friction can actually enhance the abundance with respect to the standard calculation. The point that I want to drill across is that based on the construction that we consider, we can in fact have either the suppression term, the suppression factor dominate, in which case we can open up the overabundant regime, or we can have the enhancement factor dominate, in which case we can open up the underabundant regime. And I will explain, I will give you a high-level basic idea explanation of how each of these factors can dominate over the other. So again, this is a very similar plot to what I showed you before. You should look at it from right to left, past to future. The blue line is the mass, which is increasing due to the instanton effects. The yellow line is the Hubble friction, and when the two cross, you get temperature T1, which is the traditional onset of rolling. That's in the standard mechanism when the action would start rolling. In addition to the yellow line, which is the Hubble friction, we also have the thermal friction, which is the green line. And then, in the presence of thermal friction, in fact, the rolling doesn't take place at temperature T1. It's the onset of rolling of the axion takes place at temperature T2 instead. And that is the physical reason why the enhancement factor is present. Instead of us having the start of rolling takes place at T1, we started with the same amount of energy as we normally do, only the onset of oscillations is being delayed to T2. So we escape the dilution that would have happened between temperature T1 and temperature T2. That is the basic idea. Subsequently, from temperature T2 and afterwards, that's all suppression regime. It is the regime at which the thermal friction depletes the energy abundance of the axion. So how can we isolate these two effects? How can we get the benefit of the enhancement without paying the price of the suppression? Here's where spontaneous symmetry breaking comes into play. The spontaneous symmetry of the dark gauge group that provides the friction is the equivalent of cutting off the green line at a particular temperature. So depending on where it occurs, if it occurs after T2, one gets the suppression that dominates, because the suppression is of the exponential type. It's much stronger than the enhancement. However, if spontaneous breaking of the dark gauge group takes place between temperatures T1 and T2, one enhances the overall abundance with respect to the standard calculation without paying the price of suffering the subsequent suppression. So this is the basic idea. So the idea that I just described, we apply this basic machinery that I provided for 2 particular applications. So the first application is the most minimal action-like particle scenario that we could think of. And in this case, we have a single gauge group that does both jobs. It provides mass to the axion through its instanton effects, and simultaneously, it provides the action with the friction. So as we scan the parameter space in the MAFA plane, the dashed line is the result of the conventional calculation. The black solid line is the result of our analysis that takes into account the inevitable, inescapable friction that will be there no matter what in the equation of motion of the axion. The basic idea, the basic result is that the standard calculation is only reliable up to an axion mass of about 10 to the 2 eV. Beyond this point, friction becomes important and we cannot make reliable calculations anymore. Now you might ask, why do I have 2 plots here? The reason I have 2 plots is because at high masses, the friction is dominated by high gauge couplings inevitably. And we don't have a good understanding for the Sphaleron rate at such high values of the gauge coupling. And therefore, we performed the calculations for 2 example possibilities in a sense. This calculation cannot be done better, at least for the time being, unless we get a better understanding of the Sphaleron rate at intermediate values of the coupling. However, we go at length in the paper and we explain the reasoning, and we're confident that the main point still stands, that the calculation should be understood to be unreliable at around 10 to the 2 eV mass for the axion and greater. The second idea that we consider is axion coupling to two distinct gauge groups. The first term is the gauge group that takes care of the mass of the axion through instanton effects, and then we have a separate coupling to another gauge group that takes care of the friction. This gives us more freedom because they have separate confinement scales and so on and so forth. And we also assume the possibility that there could be a hierarchy in the couplings between the two gauge groups. And this hierarchy is quantified by this enhancement parameter lambda. Of course, this in principle should be 1 because of the nature of the axion as a compact field. However, such hierarchies have been justified in the literature before through UV completions such as the alignment mechanism by Kim, Peloso, and Niles, and the clockwork mechanism by Kaplan and Ratazzi. Right, so in this next to minimal model, how do we open up the underabundant regime? T critical is by definition a temperature at which, if the axion started to roll at that temperature, it would yield the correct dark matter abundance. We're essentially converting the observation of dark matter in the present moment into a condition for the temperature, and we call that critical temperature. So the point is that the axion needs to start rolling at that temperature in order for us to yield the correct dark matter abundance, which means that the axion has to be frozen until at least that moment. This means that T2, which is the true temperature of the onset of oscillation, has to be equal to or smaller than T critical in order for us to be able to spontaneously break the symmetry at T critical. This inequality is translated in equation 24, which is an inequality for the enhancement parameter lambda. And if you saturate this inequality and solve for lambda, you find the minimum possible enhancement parameter that does the job, in a sense, and indeed can account for the entirety of dark matter in the traditionally underabundant regime. In the overabundant case, the equations look a lot uglier, so I didn't actually write them for this presentation. However, the basic idea is even simpler than the underabundant regime. The idea is that the axion starts rolling, and then since it is under the influence of additional friction, the friction simply dilutes the dangerous abundance, and we end up with the abundance that is the observed one. Again, we can come up with the same argument, with a similar argument for finding the minimum value of the enhancement parameter lambda. The argument here is different. Minimum lambda is the case in which we have the least possible friction over the longest possible period of time. So this is the basic conclusion of our hard work over the past 9 months. This is our money plot that we have in the paper. And these lines of constant enhancement parameter lambda define the stand for the smallest possible value of lambda that is necessary in order to open up the parameter space and have all of this parameter space open up, and hence all of this parameter space be consistent with the observed dark matter abundance. As you will notice, the minimum values of lambda are always greater than 1, which implies that a necessary requirement for this idea to work is that we need to somehow establish a hierarchy of the couplings using the clockwork mechanism or alignment mechanism and so on and so forth. On hindsight, we find out that this is inescapable. And this is a feature of the model, and I'll leave it to your discretion to what extent you're interested in or believe in the clockwork mechanism or alignment mechanism. All right, so what about the QCD axion? Does any of this work for the QCD axion? The answer is yes. However, there are a couple of important modifications that one has to make. The one modification is that the product MAFA, in the case of the QCD axion, is given in terms of standard model parameters, unlike the ALP case that I've been talking about so far, which is just the confinement scale squared. And hence, but this quantity is only different by some order 1 parameter with respect to this quantity, which implies that everything has to be corrected by some order 1 factor. So it requires some small correction, but it's really not all that different qualitatively. And we have an entire chapter devoted to the QCD axion in our paper, so I encourage you to look at the details there if you're interested. The second difference is that I spoke before about spontaneous breaking or confinement. In the case of the QCD axion, we cannot afford to let the dark sector confine. Because if it confines, it would provide an additional contribution to the mass of the axion, and hence we would fail to solve the strong CP problem. So spontaneous breaking is the only possibility in this case. I will conclude my presentation by saying that we coined the term frictional misalignment for this idea, and we're hoping to add this idea to an already relatively short list of existing modifications of the standard misalignment mechanism. We have a list of them in the introduction of our paper, but two honorable mentions that have attracted a lot of attention in the last couple of years is axion kinetic misalignment, in which case we artificially sort of changed the initial conditions of the axion, trapped misalignment, and so on and so forth. You can read the rest of my conclusion by yourselves. I will simply conclude by saying that the modification that I proposed is a very simple modification that's based on a set of reasonable assumptions, which, however, have a profound impact in the eventual axion dark matter abundance. Thank you for listening to my presentation.
So thanks for the nice talk. Also thanks for doing this work with the adiabatic invariant, because the literature is not clear.
Could you speak a bit louder? I can't
yes.
hear you.
Okay, better? Usually there is a kind of an harmonic factor that appears when you calculate the adiabatic invariant and changes the relic abundance by, 10, 20, up to 50%. Mm-hmm. And I didn't see it here.
Yeah, I sort of simplified this because what you mean is the initial misalignment angle. So as far as I understand, this theta I parameter. So the idea is that this theta I only changes the abundance by more than a factor, as you say, of 50% and so on and so forth, as long as it's not fine-tuned. For simplicity, I set theta 1 exactly to 1, because a factor of 50% is not the type of sensitivity that I care in order to demonstrate this point. So my understanding is that this is the factor that you mean.
No, I actually mean you use the adiabatic invariant to basically at some point stop your integration, because you integrate using a machine, and at some point you have to stop. And then use this adiabatic invariant to find the relic abundance today.
Yes.
Right? So this adiabatic invariant usually is multiplied by an anharmonic factor that depends on the initial angle. And if the initial angle is large, if the initial angle is around pi, then there is this anharmonic factor that gives you a 0.5 times whatever you have. If it's around 1, this anharmonic factor gives you 0.8 times whatever you have. That's my question. This anharmonic factor comes from the adiabatic invariant. And I'm just wondering if there is a reason that this anharmonic factor does not appear in your adiabatic invariant.
The best answer that I can give is that this modification that you mean, because it's only of the order of 50%, is not something that that we took into account for this particular purpose.
Okay, so you don't take it into account.
However, just one thing that I want to mention, this formula is actually really accurate for one particular value of the misalignment mechanism, theta I equals to 1. We actually did a detailed numerical analysis, and we matched the result of the numerical analysis to the adiabatic invariant to very high precision. But for misalignment angle of exactly 1, doing it for any misalignment angle, even non-fine-tuned ones, is beyond the scope of this work, because it is difficult. One would complicate things a lot, and the only thing that we would gain from this analysis is better precision of the order of 50%. We want more bigger picture here. We want to have the correct order of magnitude for the eventual dark matter abundance. So that's the idea.
Okay, so a second part, if I can. This extra friction term, It kind of looks like that basically it modifies the Hubble parameter that the axion sees, right? So you basically increase the Hubble parameter, because this friction is it always positive or it can be negative?
It is positive.
It is positive. So, and you don't have any entropy production or whatever at some point. So the entropy is conserved throughout.
Yeah, they're separately conserved.
Okay. So this kind of look like an extra kind of kination phase.
I would say it's the exact opposite of kination in a sense.
Really? Okay.
Right. Instead of being kinetic energy dominated, right, kination, we are freezing the axion for longer. So we're just prolonging slow roll. That's the.
Ah, okay. Yeah. Yeah. Thanks.
Yeah. Thank you for the question.
Any other question? So let's thank the speaker.
Thank you.
So the next page and the previous one, this house?
Yeah, this goes backwards and forwards, and the mid one is the later.
Okay. First, I want to thank the organizing committee for giving me the chance to present my work in this conference. The outline of my talk is as follows. I will speak briefly about some issues which faces model builder in supergravity inflation, and then I will discuss briefly the inflation in no-scale supergravity. Then I will discuss the implementation of hybrid inflation in no-scale supergravity without considering the R symmetry. And then finally, I will discuss the tribrid inflation in no-scale supergravity and how we can induce TeV inverse seesaw mechanism from this model. First, there are some issues that faces supergravity model builder, like the eta problem that arises due to the large corrections to the inflaton mass due to supergravity. This can be avoided if one considers shift symmetry or R symmetry or no-scale supergravity models. Second, the fine-tuning of extremely fine-tuning of the cosmological constant. So we need to have nearly Minkowski vacuum. If SUSY is exact, this will be easy. We just consider that the Kähler derivative of the superpotential as well as the superpotential at the minimum is 0. And if SUSY is broken, we need to tune the parameters such that we have 0 value for the scalar potential at the vacuum, or simply we can consider the no-scale supergravity, which naturally have vanishing cosmological constant. Third, we focus on single field inflation, which is the simplest option. Therefore, all other scalar fields that appears in the theory should be frozen during the inflation and don't perturb the inflationary dynamics. And finally, we need to connect to the low energy physics using the reheating. So we need to study the reheating. We need TeV SUSY breaking, and so on. A brief introduction for supersymmetric hybrid inflation. The supersymmetric hybrid inflation depends on this form of superpotential. We have 3 chiral superfields. The singlet superfield S contains the inflaton scalar, and the other 2 chiral superfields represent the waterfall field. They may be charged under some gut gauge group. For large values for the inflaton mass, the waterfall fields are frozen or stabilized at 0 during the inflation until the value of the inflaton reaches a critical value. Then the waterfall happens, and 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 all fields goes to its true minimum. However, in this case, the scalar potential is constant, and the universe is dominated by constant vacuum energy of this form. So we need to add the Coleman-Weinberg one-loop correction in order to provide the slow rolling for the inflaton S. Here in this form of this super potential, it is the most general form for a renormalizable super potential, as well as respecting the U1R symmetry. Here, U1R symmetry has very important advantages. First, it prevents higher order terms in S, which may spoil the inflation. Second, it has important role of avoiding the eta problem, where if you included the supergravity corrections, or contribution to the inflaton mass, there is some miraculous cancellation for the inflaton mass on the tree level. Moreover, it has a lot of advantages on the low energy phenomenology. On the other hand, there is another class of models of inflation which is successful and have good observables. They are the no-scale supergravity models. It avoids naturally the eta problem. Also, SUSY is broken at Minkowski vacuum. There is one important model proposed by Ellis and Nanopoulos and Olive, the INO model. The superpotential takes the form of Wess-Zumino, and the Kähler potential is of no-scale structure. Here we don't need to have R symmetry. In this case, for specific values in the parameter space, if we have mu hat is equal to lambda, we have scalar potential which has a Starbonesky form. And this potential has good observables, consistent with Planck. Now I will implement the hybrid inflation in no-scale structure. I don't need to have exact R symmetry. In this case, I will allow higher order terms in S to be available in the superpotential. But the superpotential has the renormalizable form, as you can see. The true vacuum occurred at S equals 0, and the combination phi1 times phi2 is equal to m squared. Again, the waterfall fields phi1 and phi2 are frozen at 0 during the inflation for large values of the inflaton. In this case, the effective inflation potential takes this form. In order to have canonical kinetic terms for the inflaton, we need to have the following redefinitions. Before the redefinitions, this is the mass matrix of the inflaton and the waterfall fields. As you can see, there is a mixing between the inflaton and the waterfall field. It is proportional to the R symmetry breaking term mu. Using this field redefinition in order to have canonical kinetic terms, we have the effective inflation potential of these four. If we took F to be 1 and B is equal to 0, we will return to the Starbonesky inflationary model which we had in the previous slides. So there is one limit for which, in the parameter space, for which F is equal to 1 minus B. In this limit, the potential is asymptotically flat, as you can see from this figure. So if we have F equal 1 minus B, the potential is asymptotically flat, and we will have good observables in this case. However, if we took f is equal to 1 and took different values for b, we will have, if b is equal to 0, we will have the Starbonesky scalar potential. If we change the value of b to be non-zero value but small, we will have this green curve. So if b is much larger, the inflation will be spoiled. So if f is equal to 1 minus b, which corresponds to the asymptotically flat case, the spectral index and the tensor to scalar ratio and the scalar of the amplitude of scalar perturbations will be given in this form. There is no dependence for the spectral index and the tensor to scalar ratio on the parameter b. Just they depend on the number of e-folds n. If we add some perturbation epsilon on this relation, we can do some scan over this epsilon. So that we did in this figure. The green line corresponding to a number of e-foldings equal 50, and the blue one corresponding to number of e-foldings equal 60. Okay, and this black one corresponding to the case when f is equal to 1 minus b and epsilon is 0. In order to discuss this framework in realistic example, I considered flipped gut scenario depending on SU5 cross U1 X, and also I considered a discrete symmetry Z2, which will play important role as we will see. This is the most general form for the superpotential, which is symmetric under this gauge symmetry and Z2 symmetry. In fact, the above symmetry allows this non-renormalizable term, which depends on 10 representation F and 10 H. This non-renormalizable term will allow for right-handed neutrino mass of order 10 to 14 or 10 to 13, when the 10H representation takes a VEV in the neutral, the standard model neutral direction. Moreover, it will allow for decay channels for the inflaton in order to reheat the universe. As we mentioned before, the waterfall fields has a mixing with the inflaton, so the inflaton can decay to right-handed neutrinos or S neutrinos via this mixing, using this term, actually. So this is the Lagrangian of the Lagrangian which causes the decay of the inflaton and the neutral component of the waterfall field. Using this relation to compute the reheating temperature, it depends on the total decay width of the inflaton. As we can see here, this dashed black line, it is a constraint from cosmology due to gravitino overproduction. It is the constraint on the reheating temperature. The different colored curves corresponding to different values of the scale m. So if m is of order gut scale or 10 to 15 GeV, and the coupling lambda 2 of order 10 to minus 4, we have the right-handed neutrino mass of order 10 to 8 GeV. In this case, we can use SISU mechanism to produce tiny neutrino masses of order 0.1 electron volt. The second scenario which I want to discuss, it is some modification for the tribrid inflation. The tribrid inflation contains the first term and another term depending on the right-handed neutrino as a singlet. So it is actually some kind of S neutrino inflation. The S here is not the inflaton. It plays many roles in this scenario. It is called a driving field. The F term of S will provide a potential for the waterfall fields in order to get VEV around GOT scale. Here we have a couple of chiral superfields, S1 and S2. The scalar components of them contain the inflaton, while the fermionic components will mix with the left-handed neutrino and right-handed neutrino in order to perform inverse SUSY mechanism and generate neutrino masses. Under these charge assignments, this is the form of the superpotential, which is symmetric under U1B minus L. And here we consider that our symmetry is exact, except for non-renormalizable terms, which are suppressed by blank scale. We considered also that the scalar potential is of no scale structure. And again, phi 1 and phi 2 are the waterfall fields. Here we derived the scalar potential, and we did again the field redefinitions in order to have canonical kinetic term for the inflaton field. And actually, we found that S is not stabilized at 0, as in the case of the tribrid inflation. The VEV of S is shifted slightly from 0, and this causes some kind of flattening of the scalar potential. This curve is corresponding to the inflation potential. When S is 0, they are the dashed line, and when S is not 0 during the inflation. So when S is not 0, as you can see, the potential is more flatter. So this is one benefit of the S field. Again, we did a scan on the parameters in order to see the inflation observables. So these are four benchmark points corresponding to good inflationary observables. Now we go to the most important feature of this model, which is generating the neutrino masses using TeV inverse SUSY mechanism. The first term will give the Dirac mass to the neutrino. The second term is a mixing between the right-handed neutrino N and the field S, which the field S1 contains the inflaton, as if you remember. And the last term is you saw in the inflation superpotential, the inflation part of the superpotential. And this term also is allowed by the symmetry mentioned in the previous slide. So when the waterfall field acquired a VEV of order GOT scale, and we have SUSY breaking, so SUSY breaking effects shifts the minimum of S from 0 to non-zero value of the order of the SUSY breaking scale. So it will be of the order of the gravitino mass divided by the coupling kappa 1. And also there is a shift in the waterfall in the VEV of the waterfall field from the value m by a value proportional to the SUSY breaking scale. This shift will generate the tiny value of the mu s. Okay. This shift will generate the tiny value of the mu parameter in the inverse SUSY mechanism, as you can see. The Dirac mass generated from the first term. This term is this mass term MR1 is generated from the VEV of S times YS. and also MR2 is generated from the third term. And finally, the parameter, the tiny parameter μs, S1, S2, is generated due to the shift in the waves of S and phi1 and phi2. So constructing the neutrino mass matrix, we can diagonalize it and find the active neutrino mass, which is very tiny. And the other masses of the heavy neutrinos are given in this form. And this is a benchmark point, 3 benchmark points in the parameter spaces, the parameter space. And finally, I will just show the figure which contains the constraints from neutrino masses and the reheating. So these lines corresponding to neutrino mass of order 0.1 electron volt, and this dashed red line corresponding to the constraints from the reheating temperature, which should be less than 10 to 10 GeV. So this is the values allowed in the parameter space along between these two dots. Okay, that's all. Thank you.
Which one of the two?
The
last one?
Yeah.
This one?
Yes, yes, please. Great, fantastic. All right, good afternoon, everyone. Thanks for sticking around to the end of this session. I'm really excited to talk to you about the current status of the LUX-Zeppelin direct detection dark matter experiment. Change in pace a little bit from most of the talks of the conference, so please ask if you have any questions. I'll try not to be too technical on certain things. So LZ is a direct detection experiment with the primary objective of finding WIMP-like dark matter. We are a collaboration that's ever growing. We're up to 35 institutions of over 200 scientists, shifting out of the pandemic era of collaboration meetings, and our last collaboration meeting was almost a year ago in September, partially in person, and we're hoping that we can have our first fully in-person one in the last 3 years, hopefully in the next month or so. We're based at the Sanford Underground Research Facility in South Dakota in the United States, known popularly due to Mount Rushmore, which is just about 20 minutes outside of the town of Lead, where the lab is located. It is the deepest underground science facility in the United States at the Homestake Mine, made famous for science by Nobel laureate Ray Davis, who first detected solar neutrinos in at the 4850 level, about 1.5 kilometers below the surface of Lead, South Dakota. And so that same laboratory where Ray Davis conducted his neutrino experiments, that is where we're based on currently with LZ. So how do we go about trying to detect WIMP dark matter? We do this with a dual-phase xenon time projection chamber. So the time projection chamber is a wonderful piece of technology that allows you to reconstruct not only the number of scatters that ionizing radiation has going through your detector, but also the interaction location and the original event energy. So we do this when you have a particle coming in to your detector and deposits energy at some location. You give off scintillation light in all directions, which is collected on the order of nanoseconds. But by applying an electric field across your xenon volume, you can extract the electrons to a gaseous layer of xenon where they produce electroluminescent light, and so you observe this secondary ionization signal. The drift speed's rather slow. We're talking, this whole process takes the order of hundreds of microseconds, so you get good separation between your original scintillation signal and your secondary ionization signal. And we typically correct out the position dependent, so you'll see most things in these slides are labeled S1c and S2c, and we can make linear comparisons back to the original number of photons produced from the original interaction and the number of electrons produced. And with that, then you can reconstruct the energy of the event, giving you information of what was the original interaction. Based on the S1, S2 ratio that you see out, you can also get information of what type of interaction. Was it something interacting with the electron cloud of your xenon atoms, or was it a direct nucleus scatter? And so being that most of our backgrounds are things like X-rays, gammas, and beta decay, almost all of our backgrounds will fill out this higher ionization electronic recoil band. WIMPs expected to be chargeless and non-interacting with, or very weakly interacting. Well, most likely they're going to interact with your xenon atom, will interact with the nucleus and populate that nuclear recoil band. So the whole point of building these detectors is try to find anomalous nuclear recoils. So just an overview of the detector. It's a system of 3 nested detectors with the central TPC in the center holding 7 tons of liquid xenon. It is inside 2 titanium cryostats. So we have the inner titanium cryostat that is filled with liquid xenon, and a secondary outer cryostat that are vacuum separated for insulation. But between the TPC and the inner cryostat, we have what we call the skin detector, which is equipped with additional photomultiplier tubes so that we can detect and veto ionizing radiation that's coming from outside the detector, inconsistent with a dark matter signal. The whole system is submerged into a water tank used to shield from external radiation from the cavern walls and from muons that make it all the way down from the surface. Additionally, we have constructed what we call the outer detector, which is a series of acrylic tanks filled with gadolinium-doped liquid scintillator, which allows us to capture neutrons, which also produce something that would mimic a WIMP signal. So the TPC itself was finished constructed in 2019. It is 1.5 meters tall and 1.5 meters in diameter. So the previous experiment, the precursor to LZ Lux, only had about 1/4 ton of liquid xenon. So we're talking about 30 times larger of a detector that has taken the spot of Lux in the Homestake mine. It is equipped with 4 woven grids made out of stainless steel with about millimeter spacing between the stainless steel fibers. These were constructed to slack using a dedicated looming system, and so with those we're able to produce our electric fields that allow us to drift and produce our electroluminescent signal from those ionized electrons. All of this was constructed on the surface. The TPC was bottled up and taken underground in 2019, and it was made the maximum size that we could fit in the cavern. We couldn't go 1 inch larger in diameter. We have 2 PMTs array, approximately 250 PMTs on top and bottom, allowing us to get very good spatial resolution on the position reconstruction. So after the detector was put underground and the detector was finished the construction, the outer detector construction was finished, we're able to slowly fill it with liquid xenon and level the detector off, making sure that we're getting a good ionization signals measured out across your entire diameter. Slowly biased the grids up to the nominal fields that we were expecting, 190 volts per centimeter in drift and about 7.5 kilovolts per centimeter in gas. And things have been working well so far. Our whole data processing chain was exercised and working well, being able to fully realize our S1 and S2 signals from low energy events. And our PMTs are working as expected within the gain range we require, and our ability to reconstruct single scatter events like this is more than 95% efficient. So calibrating the TPC, making sure it's working as we expect, we have done various calibrations. The two most important ones I'll focus on are our tritium calibration, which is a low energy beta decay that is spatially homogeneous through the detector because we use tritiated methane, which diffuses throughout the liquid xenon. This has a range of 0 to 18 keV, which essentially populates your entire expected WIMP region of interest in your electronic recoil band, giving a good characterization of your expected backgrounds. We use deuterium-deuterium fusion to produce monoenergetic neutrons, which is then are shot into the detector to produce nuclear recoils to mimic your WIMP signal. That way we know what our expected signal region looks like. All of this was reproduced with the Noble Element Simulation Technique, which is a third-party software to reproduce light and charge yields in liquid xenon, allowing us to get good measurements back on our detector gain so that we can reconstruct energies properly. We can do additional calibrations due just to natural backgrounds that are in the detector. So the first one is knowing what your purity is, which we use the metric, the electron lifetime, to measure. So that's essentially the survival probability as you extract electrons through the detector. If you have dirty xenon, you're more likely to lose those electrons in the drift process. And so we ended up with an electron lifetime of about, varied between 5 and 8 milliseconds, which is far more than the entire drift length of the detector. We only have about a millisecond drift length. This is currently the highest purity that for dark matter results in the previous decade. Additionally, a popular way to cross-check what those detector gains are, those G1 and G2s I flashed on the previous slides, is to take that energy reconstruction equation that I showed a while back and reconfigure it so you can get a linear response between your differential S2s and your differential S1s using a series of, if you know what the energy of the decay you're looking at, you can end up creating this nice linear fit to get out your detector gains. And using this method is in very good agreement with what I showed on the previous slide using the Noble Element Simulation Technique. So that's one used for backgrounds, but in principle we don't like backgrounds because it muddies potentially seeing a WIMP signal. There are many, many sources of backgrounds in direct detection experiments, and so we went through many different methods to reduce these. Nothing went into the detector without being screened or radioassayed. We had quite a dedicated radioassay program to make sure that every single nut, bolt, piece of Teflon that went to line the TPC, nothing was unknown. We had 4 major sites to check what our radon backgrounds, radon being a beta emitter and a noble element ends up being the biggest background in these experiments. And so there were 4 major screening sites across our 35 different institutions to make sure we knew what our radon rates were and what the played out from those decays was on our detector components. To remove other noble elements that are naturally difficult to remove from xenon were specifically removed using charcoal chromatography at SLAC, which I'll show on the next slide in a second. And I briefly mentioned the xenon skin and the outer detector and the water shield to reduce the rate of cosmogenics, and I'll talk slightly about a little bit more about this in a moment. So the krypton removal system was a pretty impressive machine to see in person. These columns are about 20, 25 feet tall. And so the process was to slowly diffuse your xenon gas through these huge charcoal columns. And because of the different masses, you'd have different drift speeds. And so you could actually get very clean separation between the krypton that was contaminating your xenon and the xenon you wanted to keep. So we ended up pumping all 10 tons of xenon through these charcoal chromatography towers. and we end up to reduce the krypton levels to less than 0.1 parts per trillion, gram per gram. And argon being lighter, easier to reduce, was easier to remove, was reduced to a negligible level. Just talk briefly about the skin system, because it's the first time a dark matter TPC has attempted to do this. So again, this is inside our titanium cryostat, which the TPC rests within. So this is looking down into that cryostat. You can see we've lined it with Teflon, which is reflective to xenon scintillation light, and lined it with PMTs on the bottom. On the bottom of our TPC itself, we've added more 2-inch PMTs, and then along the top of the PMT, we've added 93 more. So we essentially have a whole, or pretty much a good view of the entire layer of xenon between the TPC itself and the cryostat. And this is important because, so this event here is similar to the single scatter that I showed earlier. If you did not have the skin veto system, this would be a background in your WIMP search. That would end up in your final data set. However, because we have the skin, we can see that it's deposited energy in there. It's a multiply scattering particle which is inconsistent with a weakly interacting massive particle. So we know that this is not dark matter, and we can veto it. The outer detector is, you can see the 6 acrylic tanks here, or you can see some of them, but 6 in total, 4 side tanks, 1 top, 1 bottom, each filled with a liquid scintillator doped with gadolinium, specifically gadolinium because it has a high neutron capture cross-section, so that way we can understand what our natural neutron rates are coming from the cavern itself. We have very good efficiency of capturing and rejecting neutrons that end up producing single scatters in the TPC. We can figure this out from calibrations with NR sources. And fortunately, we've been seeing lower backgrounds than what we were expecting originally, so we were able to reduce the thresholds from what we were planning a few years back. So with all of this, and with these veto detectors and our background characterization and screening processes, we've been able to stay on track with our expected background rates for our full 1,000-day run that we plan. The vetoes are particularly important because it allows you to really clean out your expected volume of xenon. The stuff coming off detector components is mostly going to scatter along the walls, but being able to veto that, you end up getting a nice, clean, quiet region of xenon, which allows you to increase your exposure in a dark matter search. We only expect on the order of 1 nuclear recoil event in 1,000 days, and then on the order of 1,000 ER events, so 1 per live day. However, based on the ER-NR discrimination, very few of these end up looking like a WIMP signal. I think I'll go quickly through this. I just wanted to show how we're characterizing our radon background, as it's the most prominent ER background in these experiments, because the daughter from radon 222 and 220 is lead-214, lead-212, which each give off what we call a naked beta, being that it's untagged, it doesn't have an additional alpha or gamma coming off of it to show that it's lead or not dark matter. So we can use, though, going down the radon chain, the various alphas, and use the branching ratios to construct back on what our expected radon rates are inside the WIMP region of interest, and we end up finding out we are on track with what we were predicting from our original plans. I talked briefly about removing other noble elements because they're radioactive, so radon, krypton, and argon. Xenon itself has radioactive isotopes, and so it's important to characterize these, especially because the xenon-127 decays by electron capture, giving off low energy X-rays, which occasionally can fall into your WIMP search region. So understanding your xenon-127 activation rates is important. It's naturally produced when we had the xenon on the surface, and it's cosmogenically activated, so it's slowly decaying away over time, but it's, in early science, it is a prominent background. And so, but you can get an understanding of what those rates are by looking at the high energy components of them and use the branching ratios once again to understand what the WIMP search impact of these isotopes is. So I've gone through all of the backgrounds that we're expecting through our 1,000 days mostly, and so we are currently taking science data, and on our way to completing this goal, we are planning on crossing the 1 neutrino event level and more than halving the distance down to the neutrino fog over the previous decade of direct detection experiments. And so we're plan on trying to be the leading dark matter sensitivity experiment over the next decade, and really hoping that we're finding some sign of a weakly interacting massive particle in this region of phase space. So I'll just conclude here. So I predominantly talked about the LZ being primed to detect WIMPs, but we are a multi-physics experiment. I didn't have time to talk about that today, but we plan on trying to set limits on axion couplings, neutrinoless double beta decay, and much more. We have successfully built and commissioned the detector, and we've been collecting science data for quite some time now. And so I'm very excited that our first results are going to be coming out very soon. So please stay tuned. I'm hoping that this summer will be a very exciting time for the dark matter community, and I hope that we're on our way to finding dark matter and trying to put a signal into this phase space. So thank you for sticking around and listening, and thank you to our sponsors.
Thank you for a very nice talk. Questions?
What are the differences to other direct detection experiments, for example, when we compare LZ with xenon Nton, for example?
Yeah, so xenon Nton and LZ are both second generation dark matter experiments. You know, we are the precursor, or the second generation of Lux. Xenon Nton, second generation of xenon 1-ton. So we're larger detectors. Xenon Nton is one of our competitors. We're essentially set out to do the same goal, different approaches. Xenon Nton has a slightly smaller active volume than LZ does. And that's probably the biggest difference. They also don't have a skin, and their outer detector is not doped with gadolinium, so we're hoping that we can do a far better job of rejecting backgrounds.
Okay, and my other question, is it also possible to go beyond the neutrino floor, or is this background known in a really, can you estimate this background and basically subtract the signal?
So with this generation of detectors, no. Just because trying to carve out this more and more this phase space requires having a larger and larger exposure, which is essentially your number of target atoms versus at the time you're collecting data. We're not going to, LZ and xenon Nton, their sizes are set, so the only way to go farther and farther down is to take more and more data. To get another order of magnitude down, it would require you to take data for another order of magnitude, which is not very feasible. However, the third generation of liquid xenon direct detection experiments that are being proposed now plan on having the exposure to reach the neutrino floor and a little below. We won't have the ability to really differentiate a WIMP signal from events coming from the neutrino fog, because that elastic scattering will look identical to WIMPs. For that, you would need a directional detector to try, because you should have, being that we're moving through essentially a homogeneous wind, there should be, at any point of the year, the wind's coming from a certain direction, so a directional detector would be more primed to to push through the neutrino floor. However, the technology is not there just to get to the exposures that we need.
Yeah, thanks.
You're welcome. Thank you for the questions.
So if I understood correctly in the beginning, you said you will be sensitive to both WIMP nuclear reactions and WIMP electron scatterings. Is this true?
So there are models where we consider electronic recoils to be signal-like. What I'm talking about in this presentation and what we typically consider for a spin-independent WIMP is a nuclear recoil producing interaction. So in this paradigm, we're not considering WIMPs producing electronic recoils. But there are various models and signal types for other interesting physics where you are looking for new physics in this. The Xenon 1 ton recently put out a paper on potentially new physics, potentially solar axions or axion-like particles, or neutrino, yeah.
But so for those kinds of models, like you will not be competitive, setting competitive limits on the leptophilic dark matter cross-section?
I'm not sure off the top of my head.
Okay.
I believe we are competitive for world-leading sensitivities in some regions of phase space, but and I don't know off the top of my head, but I can let you know.
Okay, thank you.
So approximately when, you know when the first data set is expected to be available? First question. And second question, will the data set will be public?
I would love to tell you. I absolutely would love to tell you. But because we have competitors, I can't tip my hand too much. I will simply say, stay tuned and be excited.
And will the data set will be available publicly?
Oh, the data will absolutely, yes. Okay. We will, everything that we plan on, once our first analysis, once we've stopped collecting data and taking and performing the analysis, everything required to reproduce those results will be public. Absolutely.
Okay, thank you.
Any other question? Yeah.
Yeah, so just to follow up the previous question, I didn't understand. You have electron. I mean, you can see you can get some recoiling electrons or not in the end.
I'm sorry, I'm having a hard time hearing you.
Can you? I mean, can you see recoiling electrons or electrons that coming off?
Yeah, absolutely. That's.
What is the threshold of those?
I'm sorry, the first.
What is the threshold?
Yeah. This plot might be the most useful. So here I plotted the contours for the reconstructed energy of these events. So this is the tritium electronic recoil calibration. And we're getting down really close to about 1 keV in threshold.
Okay.
The thing that eats away most at our low energy threshold is, I didn't talk about it here, but when it comes to trying to tag an S1, maybe this is the right picture to show. When you see a pulse like this coming through our data acquisition, when do we call it an S1? And so our minimum requirement is that it triggers at least 3 different PMTs with a scintillation response, and that is very difficult to do below 1 keV in a detector this size.
Okay, thank you.